Welcome to Beginning Game Programming with C#. I'm Tim Dr. T. Shamillard, and I'll be your instructor for this course. I'm an associate professor in the computer science department at the University of Colorado at Colorado Springs, where I teach our undergraduate game design and development courses. I'm also the program director for our Bachelor of Innovation in Game Design and Development, a complete bachelor's degree designed to get people ready to start their own indie game development companies. I also spent 5.5 years as an indie game developer in a company that I started with my 2 sons. So why Dr. T? Well, I teach a lot of freshmen, and freshmen are trained in high school to call their teachers Ms. Smith or Mr. Jones and so on. So the first time that one of my students accidentally calls me Mr. T, everyone knows that it's wrong. As a visual reminder, yes, I am Dr. T. No, I'm not Mr. T. I have 3 important course learning objectives for this course. The first is to teach you basic programming concepts, independent of game development. Assuming you've never programmed before, there are lots of ideas behind programming, developing software that applies to video games, but also applies to any other software. And so we will cover those foundational ideas as part of the course. The second learning objective is about basic object-oriented concepts. C# is an object-oriented language, which means that we build our C# programs as sets of interacting objects, and they collaborate to make our program do whatever we want. The object-oriented paradigm is really useful for game development because if you think about games, we have lots of interacting game entities that make our game run. And so these are important core concepts for C# programmers in general, but also for game developers who are doing their development in C#. So we'll learn about important things like classes and objects and so on. The last learning objective is about using the XNA framework to actually build games. Now, those of you who are aware of the XNA framework will realize that Microsoft stopped adding additional functionality to XNA several years ago, but we're going to be working with Monogame, which is a cross-platform open source implementation of the XNA framework, which is really awesome because we can build games for Windows and Mac and Linux and iOS and all kinds of different operating systems, which is even better than what the original framework was set up to do. So how's the course structured? Well, this is an on-demand course, so you can work through it at your own pace, but the suggestion is that you spend about 12 weeks doing it. And if you spend about 12 weeks doing it, as a beginning programmer, you'll probably be looking at around 10 hours or so a week to actually really get the material internalized. So there are 7 weeks of new material. We also have 4 weeks of recovery weeks. And then there's a final week where you take the final exam, but you also do a final peer evaluation and you can do an optional project and so on if you'd like. If you're curious about why we have new learning and recovery weeks, you should look at the reading for week 1 that talks about flow and course structure, and I explain in more detail why we do that. How do you earn your grade in the course? Well, there are 3 components. There are the programming assignments, and there will be 6 of those. There's a single project that you'll complete, but you'll complete it in 5 separate increments because that's how we develop games. We don't just bang it out all at once. We develop it a small piece at a time. So that's what we'll do. And both the programming assignments and the project increments are peer-reviewed activities. So you will generate your solution and submit it, and then you will be peer reviewing a number of your peers to actually figure out what grade everyone has deserved in the class for the work they did on that particular assignment. The final piece is a final exam worth 22%, and that is a multiple choice exam that you will take in the final week of the class. So the thing about programming is it's important that you practice doing it, and lots of practice is required to get good at it. So I have provided some optional assignments as well that you can complete in addition to the graded work. And that optional work consists of 16 different optional labs you can do, smaller pieces of functionality that you implement as you learn new topics, and that optional game project that I mentioned that you can do at the end of the course to prepare for the final exam. Here is a book that I wrote, full disclosure. I wrote this book about beginning C# programming with Monogame, and I wrote this book for this course. So this book covers the topics, assuming you've never programmed before, and applies to all the things that you'll be doing in this course. I strongly recommend you get it. It is only available on Amazon. There are free Kindle readers for PCs and Macs in case you don't happen to own one form of Kindle or another. But I do want to be clear. You can absolutely complete the course without the book. You do not have to buy the book to successfully complete the course, but I should also warn you that you will probably spend extra time searching the web or posting on the forums or doing a variety of different things to try to find out answers that are in the book. It's impossible for me to teach. I think the book is like 550 pages or something. It's impossible for me to cover everything in the book in video lectures. And so this is a useful resource, but you are absolutely able to make the money versus time trade-off, deciding not to buy the book and just surf the web when you're looking for answers to your questions. So I want to be clear. This course does not assume you have any previous programming experience. We are going to start at the very beginning, and we're going to go through all the topics that you need to know to be able to successfully complete the course. Periodically, once in a while, even if you do have the book, you might have to go look something up in the book or online if you don't have the book. But we're going to make sure you have the appropriate foundation to successfully do what you need to do in the course. I also want to be clear, though, that beginner, this is a beginner course, beginner doesn't mean easy. Some people perceive that beginner should mean easy, but this is hard work. Learning to program when you've never done it before is really hard to do. And so it's kind of like learning to ride a bike, right? The first time you tried to ride a bike and it was really hard, you didn't claim that the person who was teaching you how to ride the bike assumed you already knew how to ride, right? It was just difficult to learn because sometimes it's hard to learn new things. So you may struggle with some of the material. That doesn't mean it's not for beginners. It just means it's hard. Just like learning lots of stuff is hard for the first time. Now, it is perfectly natural for you to feel frustration and to swear at your computer or at me or any other, I'm not an inanimate object, but at any entity you need to swear at as you struggle with this. The struggle is part of it, right? We fall down sometimes when we're learning to ride a bike, and we fall down sometimes as we're learning to program. And so that's a natural part of the process. You'll get frustrated, and then you will feel so rewarded when you actually solve particular problems. This is worth the struggle. Programming is a blast. Programming games is really fun, but programming anything, if you're geeky like me, let me adjust my glasses. If you're geeky like me, programming anything is fun, but it's hard work to get to the place where it is fun to do. And so if you work through that frustration, you can get to the place where you can do some really cool things. You do have to actually do the programming. You can't learn to program just by watching the videos and reading the book and saying, there, now I know how to program, right? That would be like watching a snowboarder and reading about snowboarding and saying, there, now I know how to snowboard because I've watched somebody else do it and I read about it. It doesn't work that way. You actually have to do it. And that's why there are plenty of programming assignments in the course. And in fact, there's that optional material as well. So what happens if you get stuck? Well, there are a number of places to go. And this is, of course, not like a regular course, right? This is based on our freshman college course at UCCS for beginning game programmers. So it's a challenging course, like a regular college course, but it's different in that you don't really have access to me, right? In the previous sessions, we had over 200,000 people enrolled. You can't send me an email and expect that I'll answer it. Even if you can find my email address, you should assume I'll ignore your email. And you can't, well, you can call me, but I won't answer the phone. All kinds of things. You don't get the sort of professor attention that you would usually get in a course. So where do you go for help? Well, one place you can go is the web, but use caution there. I will tell you, and you may not already know this, but so I'll tell you that not everything on the web is true, right? There are people who are going to give you advice for how to program and they don't know what they're talking about. And in fact, I actually had a student in one of my classes one time. He came to me with a problem, his code didn't work, and he had done it exactly opposite from the way I had taught him, and the way it said in the book, and the way I had discussed in lectures and everything. And I said, well, why did you do it exactly opposite from the way I said to do it? And he said, well, I found somebody on the web and they told me I should do it this way. I may be more credible as a source for learning to program compared to an anonymous guy or gal on the web, so you might want to take that into account. The other thing is we have a class forum where you can go and ask questions and post responses and help each other. In previous offerings of this course, the forum was fantastic. People were really, really helpful for each other. And so that's a good place to go. You should read the Coursera Code of Conduct before you start posting on the forum. And, we're all in this together, or you're all in this together. And so help each other. Right? You can be mean to people online if you need to be. Go on an online game, camp where the noobs spawn and headshot them if that's what you have to do to sort of get satisfaction. But this isn't the place for it, right? This is the place to help each other learn this sometimes difficult material. So I'm not trying to scare you away, right? It's hard work to learn to program, but it is fantastically rewarding to actually be able to program and start creating the games that you envision. To actually turn them into reality is a fantastic thing. And this course is designed to help you on your path to getting to where you can do exactly that. In this lecture, I'll walk you through navigating through the course page so you can find all the things you need as you work your way through the course. So let's go right to my desktop. This is the course info page for the course, which is probably where you'll end up when you go to the course. You won't get the you're an admin stuff, so you should ignore that, but it'll look something like this. If you click home over here, you'll get my welcome message and you can scroll down through the course information each of the weeks in the course. Let's actually go to course content because this is probably where you'll go most of the time. And as you can see, I have selected week 2, but of course you can select all the different weeks in the course. Usually the way a particular week is structured is I have a message at the beginning. This is called a reading in Coursera. So I have a reading at the beginning about the week, and then I have a number of video lectures. And let's actually go to this Intro to XNA lecture, and I will show you that it will start playing and you can make all kinds of adjustments for subtitles and the video quality and the playback rate. In case I speak too slowly for you, you can speed me up. And if, of course, I'm speaking too quickly, you can slow me down and you can make it full screen and so on. You should also scroll down, though, because you'll see that you can download the lecture video if you prefer to not watch it online, and a transcript and the subtitles and so on. I also always provide the slides, if there are slides to provide. And in this particular case, I've given you one of the chapters from the book, so you can go read about XNA and monogame in that particular chapter. You can also see that for each week that requires it, I provide resources to you. It turns out that the Coursera platform does not let me attach zip files to lectures for downloading, but I can put them in a separate reading, which is what I've done here. So some of my students in the past have found it valuable to start with the start code that I have at the beginning of the lecture and actually follow along with the lecture, typing along as they go. And so I've provided the start code to you for Windows, Mac, and Linux for each of the video lectures. And then I have the final code for you too. If you choose not to type along with me, you can always download the final code to see the end result of that video lecture. The other thing you'll notice as I scroll down is there are optional labs, as I talked about in the course introduction. And so sometimes there's just lab instructions, like down here for lab 5. These are optional, remember, so you do them if you want to. So sometimes there's a PDF for the instructions. Sometimes I'm giving you some materials as well as the instructions, so there's a zip file for you to download to get those materials in addition to the instructions. Each week has an assignment, so you can click on the assignment and you can get the instructions for that assignment to find out what it is you want to do. If you need to, I give you an attachment for downloading materials for that particular assignment. And of course, then there's submission stuff too, where you can actually do your submission and so on. All of the required assignments are peer reviewed. So you'll submit your own assignment and then you go review the work of your classmates. I have it set for 5, so you'll go review 5. You can review more if you want, but you'll review 5. And so that's how you get at the assignments. You can also get at the assignments by clicking on the assignments over here on the left, and that will bring you to all the assignments for the course. And so you can get at the assignments a variety of different ways. The last thing I'll point out is if you click on discussions, these are the course forums. There'll actually be more forums by the time you're actually looking at this. We'll have a forum set up for each of the programming assignments and the project increments. So as people run into trouble, they can post in those particular forums to try to get help. And if they really understand what's going on, they can go to those forums and help other people by posting answers. So that's how you navigate through the materials in the course. Now we can actually go get to work. Last time, we talked about the course structure and the things you need to do to get the most out of the course. And really the things you need to do are write a lot of code. So this time we're going to actually talk about that process. What does it mean to write code and how do we go through that whole process? Before we do, think about writing a novel. And say you wanted to write a novel in French because that was the language you were familiar with and you felt it was very expressive and so on. So you write your novel in French. Now it turns out that I, who don't speak French, might want to read your novel. So to do that, we'd need to translate your novel from French into English, a language that I understand. And once that translation happens, I can read your novel and we move on from there. So the process we go through to generate source code and to generate an entire application is exactly the same. So first, we type in some source code. We actually write a program using some programming language. In this particular class, we're going to use C#, but there are lots of programming languages people use. So this is a language that we as humans are comfortable, well, programmers, are comfortable with, and you'll be more comfortable with C# by the end of this class, I hope. And so we type this code in to some document. And now we've got source code, but we've got source code that's in a language that the computer can't understand. So the next step is to actually compile and build that source code into an executable, something that the computer can actually understand so that it can be executed. After we've done that, we can now run the executable to play our game or run our program or whatever. And sadly, I'll underline this 3 times. A lot of times, we actually need to debug our code as well. So we have to go through our code and find the mistakes we've made and fix them so that the game runs properly the way we intended it to. You should now go take an in-lecture quiz before we start talking about IDEs. So go take that quiz and I'll be waiting for you when you come back. All right, so you told me what you understand about IDEs and how can they help. Well, it turns out that we could, without an integrated development environment, we could develop code. We could type in our source code into Notepad or WordPad or something like that because it's just pure text. That's why later in the course, you'll be submitting source code by copying and pasting into text boxes because it's just text. So we can use any text editor we want. We would then need to go to a command prompt window, which we can get to through accessories in Windows, and type in a command that says, okay, now compile and build my code. And then we could type in another command to execute it, or we could navigate through our folder structure and double-click the executable. And then if we had to debug, well, that's a problem. And we'd have to figure out a way to try to find the bugs and fix them. An IDE like Visual Studio and Visual C# 2010 Express is just one of the versions of Visual Studio. Lets us do all that stuff from within a single environment. So let's take a look. I'm going to start up Visual C# 2010 Express, and I'm going to create a new project. Now, to start with, I'm going to just pick a Visual C# project. The third one down is a console application. This is an application that will run in the command prompt window. And I'm going to change its name to Intro. When I do, the environment generates a template of the code it knows I need to start with for a console application. Because this is hard to read in a video, I'm going to zoom in on it. You're probably not going to always do that when you type in your code, but it's helpful in a video. So now I'm going to do that first step. I'm going to type in some source code, and I will tell this to WriteLine a message. A nice, supportive, early in the course message, "Hi, noob." So that's typing in some source code. Now I'm going to build, and I'll press F6 to build. And we see over here in the lower left-hand corner, we get a build succeeded. That's great. It's converted, translated our source code into a language that the machine can understand. If I don't, in fact, build successfully, I'll press F6 again, and you'll notice I get this error message, hard to miss, red circle, X in the middle, says, something is wrong. And in this particular case, this is an easy one. A semicolon is missing, and expected a semicolon, so I'll add that back in so that we can get a build succeeded. And now I can do that third step. I can execute my application. Now, there are two different ways we execute applications within Visual C#. We can press F5, which we'll do with all our X and A games, or we can press Control F5. So we're going to use Control F5 for a console application, and when we do, we see we get this output, "Hi noob, press any key to continue." So find the any key and press it, and that's it. We've executed our program. Just so you know, if we pressed F5 instead in a console application, it flashes that output and immediately disappears, which is not very useful to us. I don't have to do any debugging here because this message is exactly what I wanted it to be. So I'm going to say that we've done all the steps we need to do for this console application within the IDE. So I'm going to close it, and usually you are going to click Save because you want to save the work that you've done. In this particular case, I'll discard it. Don't worry, I'll save it next time. So that's it for using the Visual C# 2010 Express environment to go through those steps of writing, converting, and executing code. However, we want to do some game development stuff. And if we want to do game development, one of the great ways to do that is using XNA. So go do another in-lecture quiz to tell me what you know about XNA, and then we'll talk about it some more. Okay, so we're back. XNA actually isn't an acronym. XNA is a game framework that Microsoft has provided for a few years now. And it's good for building games in Windows, on the Xbox 360, and the Windows Phone 7. In this class, we're going to focus on Windows. That's what we're going to develop games for. Now, like any tool, especially in technology and game development, XNA will not be around forever. But it's really useful to learn XNA because it uses C#, which is a language that is becoming more used in game development, especially in engines like the Unity game engine. It lets us understand how game development works in general. We're always going to be, updating our game world and rendering our game world, and XNA does that. And there are other tools that are being built right now on top of XNA. So the monogame framework uses those XNA IDEs and lets you develop for other platforms like Android, iOS, macOS, and others. And so it's really useful to learn XNA to develop games. So let's actually go back to our development environment and use as XNA briefly. This time I'm going to create a new project, and I'm going to pick XNA Game Studio. I'm going to build a Windows game, and I'm going to do two things. First, I'm going to rename it just like I renamed before. I'll call this Intro Game. And second of all, I'm going to actually browse to the place where I want to save this game. So I'm going to select the default folder because I made sure it was set up beforehand, but it's important for you to know where you're saving all this stuff. So make sure you know what location it's saving these games to so that you can, later go back and run those again, maybe debug if you have to, and so on. So I'm going to say OK, and it's going to build me another template that I'm not even going to zoom in on. It has a whole bunch of extra stuff in it, but I can build it. Build succeeded, good news. Doesn't mean it works, although in this case it does. But the build succeeded, and now I'll F5, not Control F5, I'll F5 in my XNA game, and I get this beautiful cornflower blue screen with a weird aspect ratio, and I'm all done. So I'm going to exit out of here. It actually automatically saved my game when I created that. And that's really it for the new stuff for today. So what you should do for next time is you should go and install Visual C# 2010 Express. Don't pick a different version. 2012 won't work, 2008 won't work, something else won't work. It's got to be 2010 Express. And so download, install that, do the documentation, make sure you have that available, then download XNA Game Studio 4.0 Refresh, install that, and you should be able to follow the same exact steps that I followed in today's lecture to use the environment. The instructions are included in the appendix of the book, and they're also included on the Coursera webpage for this course, and it's in the Setting Up Your Development Environment page. So before you go, one more question for you, one more in-lecture quiz. So go do this next in-lecture quiz. And we're done for today. Next time, we will actually start doing some other stuff. There's an optional lecture for meeting the instructor if you want to find out some more information about me. But if you don't, you could just move on to the next lecture. This is the totally optional, doesn't contain any content at all, lecture, Meet the Instructor. So you can safely skip this lecture if you'd like to, and you won't miss anything in the course. But if you want to find out a little bit more about me, then go ahead and keep watching. So I'm Tim, Dr. T. Shamillard, and I grew up in Massachusetts. And after high school, I went off to Georgia Tech for a year in electrical engineering. So pause the video if you'd like to try to decide why I left after a year, and then move on. As one of my past students so colorfully put it, I left for the love of a good woman. So I spent about a year and a half in a shipping department in a company, mostly handing boxes to the UPS guy when he came in the afternoon. And then I enlisted in the U.S. Air Force, went off to basic training and technical training school, and after 4 months, I got married. So if you want to pause the video again, you should decide whether I married the same woman or not. Yes, the answer is I did marry the same woman, and we are still married. So our first assignment was to Omaha, Nebraska, and after 16 months, the Air Force decided to send me off to finish a bachelor's degree in electrical engineering at Georgia Tech. So I went off and I did my bachelor's degree, and then I went to officer training school and got my commission. I then spent 4 years at Los Angeles Air Force Base where I managed contractors who were developing software to fly satellites. While we were there, we had our first 2 children. My oldest son is a computer scientist, so he got a bachelor's degree in computer science, and he now works as a software engineer. My younger son is working full-time in tech support. While we were in Los Angeles, I also went to the University of Southern California to get a master's degree in computer engineering, and I got that doing nights. Then we went to the Air Force Academy, where I started teaching computer science topics. While we were in Colorado Springs, we had our 3rd child, a daughter this time, and she is an author. She has self-published a collection of short stories, and she's also written a novel she's looking for a publisher for. Now, the Air Force Academy is typically a 4-year tour, but we were only there for 2 years. So again, if you'd like to, pause and think about why I might have left after 2 years, and be as creative with your imagination as you want to, and then unpause the video and see the real answer. Well, it turns out that the Air Force Academy every year sends off 1 or a few people to get a doctorate. And so I was one of those lucky few who got sent off to get a PhD. So I went to UMass Amherst and spent 3 years getting a computer science PhD. So that means I'm a doctor. I'm just not the kind that helps people. And my entire family loved it during the Treasure Planet movie when the non-medical doctor says, "I just sit around and am useless." And we saw that movie in the theater. And at that point, every single member of my family leaned forward and looked at me. So everyone takes great enjoyment in the fact that I'm a doctor, just not a real doctor. So I finished my PhD at UMass and went back to the Air Force Academy, this time for a 4-year tour. And after that, I had about 2.5 years left in the Air Force, so I was sent to Washington, D.C., where I spent that time managing contractors, developing web applications and databases. When I retired from the Air Force, I came to the University of Colorado at Colorado Springs, which I call UCCS all the time, and I got there in January of 2003. I started off teaching graduate-level software engineering classes, undergraduate computer science classes, and undergraduate game design and development classes. And now I pretty much exclusively teach game design and development classes. I am also the program director for our Bachelor of Innovation in Game Design and Development. And that is a bachelor's degree, a full bachelor's degree designed to get people to be indie game developers. I also spent 5.5 years as an indie game developer in a company that I formed with my 2 sons, and that was Peak Game Studios. We've since shut down that company because my sons, grew up and moved on with their lives. But we had great fun developing games as indie game developers during those 5.5 years. So here are some of the games we developed. The left 2 pictures are for a game called Ket. Ket is an actual board game, and we got the license to do a Windows version of that game. And so we sold that commercially while the company was active, and it had, online servers, and you could go play online and all kinds of stuff. Since we shut down the company, we shut down those servers. But if you go to burningteddy.com, you can download the game for free and play the single player version on your own computer. The picture on the right is for a game we didn't quite get finished. It's called Battle Paddles. And so if you think of Pong with weapons, that's the game that we were working on. I'm actually hoping to get that game finished up and released on the burningteddy.com website, also for free, but that will be sometime in the future. I've had that hope for a while and haven't gotten to it yet, but it's pretty close. We also, as a company, we also won some contracts to do some work for hire stuff. So the leftmost image is for 8th graders to learn about physics. So we had some orbital stuff and we had some other laser things, some interesting games to teach 8th graders about physics. The bottom center image is for a game called Freakin' Sweet Robot. And that was, well, we called it FSR, and that is for kids to configure robots to accomplish particular missions. I should have mentioned the game about the physics is actually called Physics with Neat Details. And if you think of what that acronym is, you'll realize we had fun as a company doing contract work for people who were not gamers. The upper right-hand corner is a game that was intended to teach fourth graders about Colorado history, and that's actually the only game that we implemented in Flash and ActionScript. All the other games we did as a company, we coded in C#. And so that was our language of choice. We use the Microsoft XNA Game Studio as our framework, but I'm starting to explore doing indie game development in Unity as well. So what do I do when I'm not teaching and doing indie game development? And I'm also an author. I've written 3 programming books. Well, here's one of the things I do. The blue bike on the upper left is my oldest bike. And I have ridden a number of centuries on that bike. So a century is a 100-mile bike ride. One of those rides at the time was rated as one of the 10 toughest rides in the country, the US, by Bicycling Magazine because it had over 10,000 feet of climbing in the 100-mile ride. The bottom bike is my mountain bike. So I actually used to only have the blue bike. And one of my friends took me mountain biking. And the very next day I bought that mountain bike. And then on the top right is my triathlon bike. So that's a carbon fiber beam that offers suspension basically as you race. One of the things that happened is after doing centuries and, hard centuries, I decided I ought to try running too. So I've done a number of running races, including a number of marathons. And there's actually a running race that goes from the foot to the peak of Pikes Peak. And I've done that 3 times as well. After you've biked and run that much, you probably decide, well, you're missing one thing. If I started to swim, I could do triathlons as well. So I decided to do that as well. And I've completed a number of triathlons all the way from sprint distance up to 1 Ironman distance race. That took me a long time to complete. So perhaps your last question is, what kind of games do I play? And you should think for a moment about what you think that might be, and then I'll move to the next slide. And there you go. That shows you what kind of games I play. And if you think that racing rig might be a little bit extreme, you don't know the half of it, you should go, if you're curious, you should go to the supplemental resources for this lecture and get all of the details about all the stuff I have for driving racing simulators, mostly on the PC. I do some 360 driving, but mostly on the PC. So there you have it. You didn't learn anything new related to the course material, but hopefully you found it a little interesting to find out more about the person who is teaching you this course. Okay, so we've talked about the course structure, and we've talked about how, Visual Studio and XNA and how you're going to use that to develop code in the course. So it's time for us to talk about that first C# program that you're going to build. Before we do, we're now into the second module of the class. I've broken the course into modules so I can collect together topics that are similar to each other and sort of go together. And for each module, I have a set of learning objectives that I expect you to meet to succeed in that module. This particular module only has one learning objective, and that learning objective is about developing a simple console application. So for each of the lectures from now on, the second slide in will be a reminder of what the lesson objectives are for that module. Now, you'll notice on the very far left, there's a column called Bloom Level, and this particular one is Bloom Level 3 for Apply. So let's talk about Bloom for a moment. So Bloom's taxonomy is all about different levels of learning. And the lowest level is remembering. So that's called level 1. And it's just about, can you memorize facts and sort of parrot those back when the time comes. All the way to the highest level, which is creating. And so there's a pyramid of different sort of levels of understanding, if you will, or learning in terms of how you can take what you know and either synthesize it or just explain it to somebody else or actually apply it in practice and so on. So those are the different things that we consider when we talk about Bloom's taxonomy. So each time I have an objective, I try to figure out where that falls in Bloom's taxonomy. And in this course, you're going to see that almost everything falls under understanding or applying. So most of our stuff will be you either need to understand something so you could explain it to somebody else, for example, or you need to be able to apply it. And there's tons of application in this course. You need to be able to do a lot of stuff. And that's application. That's applying on the Bloom's taxonomy. So we're going to do a couple of in-lecture quizzes right off the bat to warm you up. We talked last time about what process we go through to actually develop software. So you should go do the in-lecture quiz about software and what that's all about. We also talked about the fact that you program in a particular language. In this class it's C#, but in other courses or just on your own, it could be one of many, many different programming languages. So now you get to do another in-lecture quiz talking about programming languages and what your preferences are. Okay, so I've done this before, but we're going to start up Visual C# 2010 Express to actually do a C# program. As before, I'm going to start us off with a console application and we'll move towards XNA games once we get to really next week. Next week is when we'll start really hitting XNA games. So as you recall, new project. I'm going to pick the Visual C# here on the left. Third one down is the console application. And I'm going to name this first C# program and click OK. Last time I showed you a quick and dirty typing in one line of code. This time I'm going to do it a little more thoroughly. First thing I'm going to do is I'm going to add comments. Now comments, different people have different opinions about comments, so there's a totally separate lecture about comments. So I'm just going to do it now and I'll talk about it in the next lecture. So I'm going to add a comment above the class that says a class that prints a message. I'm going to add a comment above what's called the method. This main thing is called the main method. Main method to print message. And I'm even going to put in here command line args. So the chapter in the book talks about all this structure and how it works. Basically, this right here that I'm highlighting, let me zoom in so you can see that better. This right here that I'm highlighting is actually information that can get passed in if in fact you do use a command prompt when you run the program. The template automatically puts it there, so it's going to be just fine if you leave it alone. I'm going to say print a message, yet another comment, though it's a slightly different kind. These are documentation comments because they can actually be used to generate documentation for other people using the software. These are called line comments because they're just inlines within the program. So I'm going to print a message like I did before. Although I will be nicer this time. Last time, you know, I called you noobs and that was really mean. So I should really say hi smart noob because that's much nicer. And I'm going to add one more output here, but I'm actually going to not have it print anything. It's just going to output an empty line, which will look a little nicer. I'll show you when we get there. So now, now I'm going to press F6, which, as we know, does something important, and you should go do the in-lecture quiz to tell me what that thing is. Okay, now I press F6. I get build succeeded, which is great. So I've done that second step, right? I've built the software, so now it's in a form that the computer can understand. And next, I'm going to actually run it. So I'll do Control F5 to run it, because this is a console application. Before I do, you should go do an in-lecture quiz. Okay, Control F5, and this time, of course, the much nicer message, right? Hi, smart noob. But you'll notice that console.writeLine put a blank line here, which is kind of nice because it separates this standard prompt to continue from the actual message or the output from the program. And so I'm also going to save this time. So I'm going to say File, Save All, and now I'm going to save it somewhere. And I will browse to the place where I want to save it. People always laugh at me about my folder structure because it's very complicated, but that's because I have an awful lot of stuff on my computer. So we'll go to lesson 3, which is right here, and that's where I'll save this particular program. Remember last time I didn't save it, I discarded it. And when you work and have done some productive stuff, you definitely want to save it. So that's what I just did. So let's close down the environment. And one last thing that I want to comment on before we close out this lecture. It's important to understand that so far I have solved really simple problems. I've solved the problem of printing an interesting message to the screen. In general, we're going to solve far more complicated problems as we develop games. And it's important that you understand that the problem-solving process is very iterative. We're going to do a little bit. We're going to try it out and make sure it works. We're going to go back and do a little bit more. We're going to try and make sure it works. We're also going to debug when we discover it doesn't work. So you shouldn't feel disheartened if in fact you find yourself going back and fixing things or adding pieces one at a time, because this development process is hugely iterative. If you're writing 2 million lines of code, which we won't do in this class, but if you're writing 2 million lines of code, you're never going to just pound on the keys for a few months, typing all the source code in, and then hope it all works. That's not how programming works at all. We do tiny pieces and check them, because when they break, not if, when, we have a tiny little bit of new code to look at. So just remember, programming is this really iterative process. Okay, so that's it for today. Next time, we're going to actually talk about commenting and why it's useful and important. Last time, I promised we'd have a lecture on commenting. And just to remind you, the lesson objective for this module is to learn how to write your first C# program. And that's not just whack one together, it's do it right. And doing it right means using comments. So to kick us off, you should go do an in-lecture quiz about your opinions about commenting. So no matter what you said on that in-lecture quiz, there are a couple of reasons that we actually use comments. They're all about communication, and it's communicating with two different populations. The first population is other programmers. So we want to communicate with other programmers, and we do that through comments in two different ways. The first way is with the documentation comments that you saw me write at the top of the class and method last time. So they start with 3 slashes and they have XML like summary and so on in them. And we use those to actually generate documentation for programmers who might be using the code we've written when we don't provide the source code to them. So Microsoft certainly doesn't give people the source code to Windows, but they provide programmers who want to use the Windows application programming interfaces to actually use documentation so that they can figure out how to do it. If you wrote a game engine that you wanted to sell to people, or even just to give away for free, you wouldn't necessarily give away the source code. You'd give away DLLs, and you'd give people documentation so that they could actually use your engine code. So writing documentation comments as we write our code lets us generate that documentation so people can use it. The other way we communicate with other programmers is through the line comment that I showed you, the one that starts with 2 slashes and has a bunch of green. The comment is always green. And of course, programmers who want to read those comments actually do have to have access to the source code. But we've actually learned over time that software lasts much longer than we expect. So somebody might end up years later going into your code, or code that you wrote. You no longer work at that company or whatever. You're on a different project. Who knows? But they go into your code and they try to maintain it. Add functionality, fix bugs that you left in there by mistake, or on purpose if you're really mean, those kinds of things. And so comments, line comments, are the other way that we communicate with other programmers. We comment our code to say, this is what I intended to do here, so that they can understand the code better. The other population we're communicating with when we write comments is you. So you might say, well, I'm writing the code and I'll remember from 1 minute to the next what I'm trying to do. And that's hopefully true. But you may not remember 1 week to the next, or 1 month to the next, or 1 year to the next. There are certainly times when because life gets in the way or a new game comes out or whatever, we stop working on our code for a while and then we get back to it. And when we get back to it, it really helps to actually have comments available to us so that we can understand what we were trying to do before we took that break. So comments are great for communicating with other programmers and for communicating with ourselves as well. So you should take another in-lecture quiz about comments. You should also know that there are numerous rants on the web about comments and why they are evil and bad. And those rants fall into sort of 2 different arguments, if you will. The first one is that if people write really stupid comments, they don't help. And gee, that is in fact correct, but that doesn't mean commenting is a bad idea. That's like saying, if you build a house wrong and it falls down, that means we should never build houses because it's possible to do it wrong. That's ridiculous, right? If we do something stupidly, yes, it's stupid. No kidding, right? So commenting in an appropriate way is really helpful. Commenting in a stupid way is not helpful. This should not be a newsflash to anyone. This applies to lots of things, not just commenting. The other argument is that professors, like me, ruin beginning programmers by making them comment. Because, go back to argument 1, comments can be done incorrectly, and when they are, it's bad. So, good professional programmers comment their code, period. It's not an academic exercise that we go through just to sort of make you do stuff that you never should actually do when you're writing real games. That's ridiculous. There are, I will admit, some things that you do in a beginning class that are not professional rigor, if you will, because we have to ignore a lot of detail to sort of get at the core concepts. But commenting isn't one of those things. Real programmers who are good at their job comment. And so I actually went and gathered some information about Peak Game Studios code. Remember that game company I ran with my 2 sons for 5.5 years? And a big chunk of this code was written by multiple programmers. Some of it was just written by me. But I went and collected all this data about all that code we wrote, industrial strength professional programming. And you'll notice the important part is there. So it turns out that in this code that we wrote, the minimum percentage of code that was comments was 23%, and that was in tools We sometimes don't comment our tools as well as we comment other code that we expect to last a long time. All the way up to 36% of the code we wrote was actually comments in the Peak Game Studios engine, because we expected that engine to last a long time, and we needed to be able to document to other programmers and to ourselves what we were doing in that code. So again, commenting is not just an academic exercise. It's what good programmers do. They do it wisely. They don't do it stupidly, but I shouldn't even need to tell you that, right? Okay, so you should do the last in-lecture quiz for today. So, comments, there are a couple of answers there. If in fact you do your comments incorrectly in your code, so you put 1/ instead of 2 or 3, for example, your code will not compile. You won't get a build succeeded. You won't be able to run your code. So it is possible to really mess up and make it so your code doesn't run at all when you try to comment. That's fairly unusual, and you'll know how to fix it. The other correct answer is comments do not affect the speed or the size of the code that gets generated in any way. The stuff that runs on the machine. Obviously, your source code's a little longer because there are extra lines of text. But the compiler is smart enough to say, oh, comments are not for me. They're for humans. I mean programmers. And so there are no bits generated in the executable from comments. The compiler just ignores them. So it doesn't make your code run faster, doesn't make your code run slower, doesn't add to the size of your executable. There's no impact whatsoever in the end product that people run when you add comments. Okay, to recap, comments are really useful, and you should use them. Professional programmers comment. They comment wisely, not stupidly, but they comment wisely. And so this is a really helpful thing, and you should do it. So next time, that's the end of Module 2. So next time we will move on to Module 3, and we will start talking about ones and zeros. So, this lecture is the first lecture in Module 3. We're going to talk about data types, variables, and constants. So, as I showed you before, here's a list of the learning objectives for this particular module. This module has a number of lectures, so it's going to take us a little while to get to meeting all these objectives. But these are the objectives we're trying to meet for this module. It's important to remember that everything in a computer is represented as binary. It's just ones and zeros. And so we need to think about how this actually works in practice to get a good understanding of how data types work. So the question is, why do we care? And we care because ones and zeros are used to represent anything. We can represent pictures, we can represent music. This is why computers can store all this incredible information, is because everything can be encoded as ones and zeros. But the question is, say we want to store something, and this is what's really going to matter for this particular module, is if we want to store something, how many bits do we actually need to represent something? And that question is sort of deeper than it seems at first blush, because the question really comes to, well, how accurate does the representation need to be? Can I actually store this beautiful picture of a mountain using only 8 bits for each pixel? Or do I need more bits than that to store all the colors that the eye can see, and so on? So we need an understanding of how many bits we need to represent stuff, so that we can really understand how the different data types and the different accuracies that they have sort of matter. So, of course, a story. On Christmas morning, my family was trying to decide who would get the first present. And there were 4 of us there at the time. One of my sons wasn't there yet. So we wanted to figure out who gets the first present, and we wanted to do it by flipping a coin. So my son and I, remember, my son, the computer scientist, and I came up with one answer, and the non-programmers in the room came up with a different answer. So you should now pause for a minute and go do the in-lecture quiz to try to figure out how you would use coin flips to figure out who out of 4 gets to open the first present. There are a number of reasonable solutions to this problem. One of those solutions is to treat this like a tournament, your standard basketball tournament or pick your sport, but it's the playoffs. And so you can do this with 3 flips. You do one flip to pick between A and B. You do another flip to pick between C and D. And you do a third flip to figure out who of the winners of that first round actually finally win and get to open the first present. So this is a really intuitive way to think about it, and obviously people use this approach all the time. But it turns out that we can, I want to do this very dramatically, we can use the power of binary. We can actually do this in 2 flips. But we do it by thinking about how we encode things using zeros and ones. And as you can see from the image on the left, we can represent 4 different things using 2 bits just by using the combination of the 0 and 1. So we can actually do this with 2 flips by, just set 0 to tails and 1 to heads, flip the coin twice, and whatever encoding you get from those 2 flips, that determines the person. So let's step back for a second and think about, well, if I have 1 bit, how many different things can I represent? And the answer is 2 different things. A 0 means one thing, a 1 means another thing. If I have 2 bits, as we've seen here, I can represent 4 different things. And so there's got to be a general mathematical equation that we can use to say, if I have this many bits, how many things can I represent? And of course there is, and we're going to actually look at a biggest font slide of the entire course. Probably, we'll see. And it's n equal 2 to the b. So what that means is we need b bits to represent n different things. And that's important because the more bits we have, the either larger numbers we can represent, or we can represent numbers with greater accuracy. And that will matter as we decide to figure out which data types we want to use in our programs. So this is a pretty short lecture. Let me recap. N is equal to 2 to the b. So given b bits, we can represent n different things. Now, you might know n, right? You might say, I have 65,535 things to represent. How many bits do I need? That's just the opposite equation. So it's b is equal to log base 2 of n. That's how we do these calculations. So that gives us an understanding of the relationship between how many bits we have and how many things we can represent with those bits. Next time, we will move on and actually start talking about data types and why the number of bits actually matters to us when we consider data types. Okay, here's our second lecture in Module 3 where we're talking about data types, variables, and constants. This time we will be addressing a little more thoroughly what data types are all about. So here's a reminder of the learning objectives for Module 3. So remember from last time that the key idea is that anything can be represented in the computer in binary. So it's all ones and zeros. And you should start off with an in-lecture quiz to make sure that you remember one of those critical points from last time. Let's dig a little more deeply. We talked about how ones and zeros can be used to represent a bunch of things, and we even talked about how we can calculate how many bits we need to represent a certain number of things. But what does a set of zeros and ones really mean? And the answer is it depends on how we choose to interpret that set of ones and zeros. So this set of ones and zeros that I've given you here could be considered to be 65. If we think of these ones and zeros as an integer, then in the binary number system, this is actually 65. However, if we thought of those ones and zeros as representing a character instead, they mean capital A. So we end up with a bunch of ones and zeros in memory, but we need to understand how to interpret those ones and zeros so that we can process them appropriately in our game, or any computer program for that matter. So the thing that lets us say how do you interpret those ones and zeros is called a data type. So when we pick a data type for a location in memory, we are saying the ones and zeros at that location in memory should be interpreted as an integer, a character, whatever. So that's an important component of data types, is it tells us how to interpret those bits. Data type also determines valid operations. So we've said, let's say that we've said a set of bits represents an integer. Well, there are some valid operations that we can do on integers. We can add them, subtract them, and so on. But not every possible operation on bits is valid. And the data type determines what operations we can apply and which operations we can't. The good news is the compiler will tell us with an error when we try to do something wrong with a particular data type. So let's say the sequence of bits is actually a pixel value. And what a horrible pixel, we only get 8 bits for, red, green, and blue for it, but how sad. We'll say it represents a pixel. Now, adding an integer to a pixel value usually doesn't make any sense at all. There are always exceptions, and in fact in this particular case, if we wanted to shift the color, add a little bit of green to a pixel value, we would in fact add an integer to that pixel value. So there are exceptions to these rules on occasion, but in general we use the data type to determine what we can do. So one more example, perhaps it's better to have a non-exception example to continue forward. If in fact we had a character and an integer, it doesn't make any sense at all to subtract A from 65. There's no math that makes that work, at least in this beginning programming class. Okay, so data types determine operations and they determine how we interpret the bits in memory. So let's actually look at memory for a second, and this isn't precisely what memory looks like, but it's a conceptual model, if you will, of what it looks like. So we have a bunch of locations in memory, and they all have zeros and ones, and they're numbered. Now, real hardware geeks would never talk about location 40 in memory. They'd get the hexadecimal value of 40 and they'd talk about it that way. Way back in the, come with me in the Wayback Machine, when people dealt with base 8 called octal, you would actually figure things out in octal. But this is a good enough model to say, hey, look, there are locations in memory. They're numbered. They have addresses, just like houses on a street have addresses. And so we have these addressable places in memory. And they always have ones and zeros. A beginning programmer mistake is regularly, oh, that memory location has nothing in it. And it's impossible for memory to have nothing. It's a bunch of switches that are either flicked on or off. You can't say there are no switches. They're all zeros and ones. Okay, so here's our conceptual model of memory. We got a bunch of ones and zeros. We have a bunch of memory addresses. That is hard for us as programmers to deal with because we really do not want to, in general, refer to memory addresses by their actual numerical value. That's really hard, right? What we'd really like to do is say, you know what I need? I need a space in memory, and I want to call it by name. I want to call it score. I want to call it 2,413,212,816 because that's really hard to code with. I want to call it score. So I want to have a place in memory that has a name and I can refer to it by name. And I want to say I'm going to interpret that space in memory as an integer. Let's say your score can't be, decimals. It will be, in fact, an integer. And so that's what I need. I need to get a space in memory that I call by name that's interpreted with a particular data type. In lecture quiz. We're going to start seeing examples of actually doing this in C# next lecture. So right now I'll give you the general idea. We declare a variable by giving its data type, so that's how we interpret the bits in that memory location, and by giving it a name. And that's the name that we'll use instead of the actual memory address. Optionally, we can give that variable a value as well when we declare it. If we don't give it a value, then it can be subtle in C#, but let's just assume, because this is the safest assumption, let's just assume it's a random set of zeros and ones. Well, if you're starting a game and you've declared a score variable and you say it's going to be an integer, some players would be thrilled to start with, 1,000,000 points just because. But you really should start it at 0. Right? And so we can optionally give variables a value as well. But the core part of variables is we give it a data type so it knows how to interpret the bits, and we give it a name so we don't have to refer to it by its memory address. We also have this concept of constants. So constants, we have to give it a data type, same reason as for variables. We give it a name, same as for variables, and we also give it a value when we declare it. And so there's an in-lecture quiz to test your understanding of how variables and constants work. Hopefully you enjoyed that one. I love the tautology kinds of variables are variable and constants are constants, but it's true, right? If all you have to do, so there's lots of terminology, right? New terminology in computer programming, but so much of it makes sense. A variable is variable. It can change. A constant is constant. It cannot change. And, programmers can be mean to each other sometimes, but picking terminology, usually it makes sense if you stop and think about it. So, data types give us two things. How do we interpret bits in memory and what operations are valid for the value of that data type? And we have variables and constants that we can declare to give us access to memory locations by name. And next time, we'll actually start looking at specific data types available to us in C# and how we, in practice in C# programs, declare those variables and constants that we've been talking about today. We spent the last couple of lectures talking about how we use bits to represent different values in the computer. And we talked about data types and how they determine how we interpret those bits and the operations we can perform on variables of those types. So it's time to actually finally talk about some concrete data types in C#. Before we do, a reminder of the Module 3 learning objectives, still all about data types. And so we're going to talk about, in this lecture, various data types that we can use to represent integer numbers in C#. Before we do, we should talk about an important distinction about the two different kinds of data types we have in C#. And those two kinds are value types and reference types. Reference types are all about classes and objects, which we're going to start learning about next week, so we'll defer a discussion about those for now. Value types are called value types because the bits that are in that memory location associated with the name of the variable actually represent the value of the variable. Now, that may all seem intuitive to you at this point because that's how we talked about it last time. So that's great. We'll see when we get to reference types that it's slightly different, but it's important to have this terminology nailed down. Value types, the memory location is the actual value of the variable. So let's talk about integers. Integers are numbers for which there's no fractional or decimal part. And they include positive and negative numbers, and they include 0. So all the numbers that are non-fractional, non-decimal, positive and negative and 0, are the integers. And in C#, we actually get 4 different kinds, 4 different data types we use to represent integers. We get byte, short, int, and long. And the difference between these 4 different data types is how many bits are used to represent a variable that has that data type. So perhaps not surprisingly, the byte data type uses a byte to store the information. A byte is 8 bits, and so we know from what we've already learned in previous lectures that n equal 2 to the b. So if b is 8, n is 256. So we can represent 256 unique values in a byte. Turns out the range is from 0 to 255. And then we move up to short, which is 16 bits long, int, which is 32 bits long, and long, which is 64 bits long. So because these different data types have different numbers of bits used to represent the number contained in them, we know that that means that the long data type can store a wider range of these numbers than int can compared to short, compared to byte. So that's what we know given these different data types. In this class, we're going to pretty much exclusively use int to represent integer numbers. But if you're in a very memory constrained environment and you are just dealing with small numbers, you might choose short or byte instead to save on memory. Let's look at an actual example of doing this by opening up XNA. And we'll start a new project, continuing with console applications at this point. And I'll say integer, I'll call this new project integer data types. And I am going to zoom in before I forget. I'm also going to add comments. So it's easy for professors as they go through a lecture to say, oh, well, I don't have time to comment, but you always should, so do as I say, not as I do. I'm just going to write the comments, and if you get bored while you watch me do this, you can sort of go to your happy place and come on back when I tell you to. But it's always easier to just skip doing the appropriate thing with the comments, but we're not going to do that. So I'm going to declare both an integer variable and an integer constant. The integer variable, first we start with the data type, and then I'll call it seconds played. I'll even call it total seconds played. So this is how many seconds you've played a game. Give you all of 100 seconds. I'm also going to declare a constant, and the difference is we say const, int, and let's see, seconds per minute. That will be useful to us. So the seconds per minute is a constant because as we run this program, we shouldn't be changing how many seconds there are in a minute. That doesn't make any sense. The total seconds played, we're also not going to change that one as we go along here, but we could. we'll discover later on that we could, ask the user for how many seconds they've played the game so far and so on. So we need that one to be a variable. You'll also notice that I took advantage of that. Optionally, we can in fact provide a value to a variable when we declare it. Constants, we have to provide a value when we declare it. Variables, we can choose to, and I chose to. Okay, so at this point, I have declared these variables. Let me caution you. I've had at least one student do this before. They said, well, you talked and talked and talked about declaring variables, so I forgot. And I went and looked on the web, and I discovered I can do this. I can do var seconds played, and I'll give that a value, and the compiler lets me do it, and I can, it'll all work and everything. Don't do that. For those of you who are familiar with scripting languages like JavaScript or ActionScript, you can not decide on the data type for the variable and let the compiler figure it out and perhaps even change it as you run the program. That's great for scripting languages, but don't do it in C#. Take the time to think about what data type you actually need and then use it. So I'm going to get rid of this because I showed you bad, don't do it, and I don't want to leave it there as an example. Okay, so I said that the operations for integers are largely as you'd expect. We can add things, we can subtract things, we can multiply things. The one area where it may feel unusual to you is when we talk about integer division. So let's actually do some integer division and see how that works. So I'm going to take this information that we have right here, and I'm going to calculate minutes and seconds from it. So I'll have another integer variable called minutes, and instead of putting a literal, this is called a literal because it's literally that number, I'm going to put an expression on the right hand side of this equation, and I'm going to say that the minutes that have been played are the total seconds played divided by the seconds per minute. And let's do some output. I'm going to label the number that I'm printing, so I'm not just printing out a slew of numbers. And so we've seen this console write line printing stuff before, like this, and now I'm going to concatenate. I'm going to slap another string next to this one, and it will be the string that represents the minutes. And I'll add the extra blank line that I like at the end of these programs, and finally I will Control F5 to run it, and we'll see that the result says minutes is 1, and that just doesn't feel right? The minutes should be 1.667 or something. And so this is where integer division is different from the division you might expect to occur. Integer division, division between two integer variables or two integer values, ends up returning just the whole number, not any remainder, if you will. So what if you need the remainder? Well, it turns out that we have an additional operation available to us. So I'm going to calculate seconds, and seconds will be total seconds played, but now I'll say the percent sign in C# means give me the remainder. So what's going to happen now? I'll print those results as well. What happens is we can take advantage of the fact that the integer division only gives us the whole number result, and we have this remainder thing, so that we can in fact Control F5 and see that we can use the way that these integer operations work to sort of extract minutes and seconds from a total seconds value. This is actually really useful. I've used this in multiple pieces of code, including if you keep track of the total milliseconds that somebody plays a game, which is relatively easy to do, particularly in XNA, then you can provide player statistics broken down into millennia, okay, maybe not, at least hours, minutes, and seconds. And so using division and remainder is exactly the way that we go about doing that. I will Control S to make sure I've saved this. And I'm going to browse to the place where I want it to be, of course. This will just take a moment, but it's better to save it than not. So we're definitely in Module 3. Integer data types. This is a good place to save it. Called integer data type, so there we go. Okay. You must be very sad that you haven't done any in-lecture quizzes yet, so now it's time. And this first one is great, so go ahead and do the first in-lecture quiz. You should brag to people that you are essentially doing a college-level course online, and one of the important things you learned in the first week was that 1 + 1 = 2. All right, for people who may not be impressed by that, time to go do another in-lecture quiz. And that one's a little more interesting. So the positive number I gave you in the question is the maximum possible value for an integer. We know this because we have n = 2 to the b, and if we only have 32 bits for an integer, there's a maximum number we can store. And that was the maximum number. When we add 1 to it, because of the way we represent numbers using binary, it actually wraps around to the largest negative number we can store in an int. And so this is something that you may occasionally run into, but it's really interesting. It's an application of n = 2 to the b. To recap, we know that for value types in C#, we store the actual value of the variable in the memory location, and we'll see how that's different for reference types next week. We've also seen that we have 4 different types in C# that let us store integer numbers, and we've sort of messed around with those a little bit to see how they work. Next lecture, we'll actually look at some of the data types that we get in C# for representing real numbers. Last time, we talked about the different C# data types we have to represent integers. This time, we're going to talk about the C# data types we have to represent real numbers. Before we start that conversation, here's a reminder of the Module 3 learning objectives. So, before we actually start talking about specific data types, let's talk about a problem that we have as we try to represent real numbers with a computer. The problem is that we already know n = 2 to the b. It's also the case that the real world is a continuous domain. In other words, between 0 and 1, we have an infinite number of numbers. What that tells us, given n = 2 to the b, is that if we're going to precisely represent every number in the real world, then we're going to need an infinite number of bits for the numbers between 0 and 1, and then another infinite number of bits for the numbers between 1 and 2, and so on. And despite the fact that memory is getting cheaper all the time, we do not have that many bits available to us. So we are making choices as we represent those real numbers, and in fact, what happens is a number of real numbers get represented with the same sequence of bits in the computer because we have some rounding. We're doing approximation rather than precise representation of those numbers. So it's important that you understand that, because when we try to represent a real number, we can't represent all real numbers with the bits we have. So some of the real numbers that exist in the real world get represented with the same sequence of bits in the computer. When we try to represent real numbers in the computer, we actually have a couple of different kinds of real numbers that we're going to represent, and we'll talk about each of those separately. First of all, we're going to talk about floating point numbers, and we get 2 different data types in C# for floating point numbers. We get float and we get double. And the difference between those 2 data types is that they use different numbers of bits for their representations. So we already know what that means. We know that floating point numbers, which use fewer bits, can represent a smaller range of numbers, and in fact can represent a smaller range of exponents as well. We're going to find, because XNA uses float almost exclusively, we're going to find that we're going to use float in large part for real number representations in the programs we write, but we have these two choices. And the operations we have available to us are as you'd expect. Let's take a look at a short program that uses floats. New project, another console application, and I'll call this one floating point numbers. Zooming in before I forget and saving as well. We'll just save right there. And again, adding comments. So, we're going to declare a couple of different variables here. Let's say one of the areas where floating point numbers tend to be really useful is when we calculate averages. So let's actually calculate an average, and we're going to first declare variables that store the numbers we're going to use in our calculation. I'll make them both integers. So the first will be something you may have seen in the past in your gaming experience. We'll call it score. And we'll say it's 1,356. That may be good, that may be bad, it depends, But there's a score, 1,356. We'll also have a total seconds played, because as gamers we like to optimize our points per second, and so we'll have a total number of seconds played here as well. And let's make that 10,000. Notice I didn't put any commas in this literal, they don't go there, just the pure number. So, I've got a score, I've got a total number of seconds played, and now I'd like to calculate how many points per second I'm actually earning in this game. So I'll say calculate and display result, and I'm going to put this result into a floating point number. So float, points per second is a good name. And the points per second are the number of points, so that's score, divided by the number of seconds, so that's total seconds played. And we'll do our output. And I will add that blank line that I always like to add. So when I run this with Control F5, oh dear, points per second is 0. And that doesn't make any sense to us, right? Points per second has got to be more than 0 because we have more than 0 points. Remember though, from last time, when we divide two integers using division, we actually get the whole number result, and because our average is less than 1 point per second, the score divided by the total seconds played is in fact 0, using integer division. What we want to do is force this to do floating point division. And so we're going to use something called a typecast that says, turn this into a float. So we need either score or total seconds played to be treated as a float for the calculation to yield a float, because we're trying to force this division operator to do a floating point division, not an integer division. So the way I can tell score to be treated as a float in the calculation is I add the word float in front of it inside parentheses, and that is a typecast. That says temporarily, right here, treat score as a float. It does not convert the score variable to a float permanently or anything like that. It's just temporary for this calculation. Once I do that, though, and I run again, I see that I now get 0.1356, which is as we expected. So this is one of those things that burns beginning programmers a lot. You heard about integer division last time, and you sort of maybe nodded your head and said, sure, I got it. And in fact, it can still come back to bite you. So we've used a float to store a floating point number. It has a decimal point in it. And so that's a good thing. It's very useful to us. And that's all we actually are going to do in code today for this lecture. So I've saved and I've closed. Now, that means, since we just talked about floats, that you probably have an in-lecture quiz to do, and of course you do. So go ahead and do that now. As I mentioned, floating point numbers, float and double, have inaccuracies in them. They are an approximation of the continuous real world of numbers, and so there is some rounding, there are some instances, many instances of multiple numbers in the real world being represented with the same sequence of bits. So we get that inaccuracy that can't be helped because n equal 2 to the b. The good news, well, it's sort of a dual-edged sword of cutting. The good news is that we have the capability to have perfect precision for numbers with decimal points. The bad news is that comes at a cost. And the cost is that we have to reduce the range of numbers we can represent. But it's important sometimes to have that perfect accuracy. When we're talking about currency, when we're talking about the stock market, if you're talking about cash register machines, we do not want to allow rounding, even for fractions of a cent, or whatever your currency is. So sometimes we need perfect accuracy. And remember, this is not tricking n equal 2 to the b. This is not magic in any way. All we're doing is reducing the range of the numbers we can represent so that we can represent with perfect precision all those numbers. And so, we have this data type in C# called decimal that gives us that perfect accuracy at the cost of a reduced range of numbers we can represent. And, this is up to 28 decimal places, so it's not like this won't work for your local cash register. But it's good to avoid the rounding. So, given that discussion about decimals, you have another in-lecture quiz. I really hope you picked the correct answer on that previous quiz. All right, so the recap for today's lecture is, just as we had a variety of C# data types we could use to represent integers, we also have a variety of data types we can use in C# to represent real numbers. And those are the 3 data types that we talked about today. They're also value types. Remember, the memory location is the bits at the memory location are actually the value of the variable. But we still have a few more value types to talk about in addition to the numeric types that we've talked about last time and this time. So for the next lecture, we will finish off Module 3 by talking about the other value types that are available to us in C#. Well, we've made it to the last lecture in Module 3 and the last lecture in the first week of class, so good job. Just as a reminder, these are the learning objectives for Module 3. So we spent the last couple of lectures talking about how we can use C# data types to represent integers and real numbers. Today, we'll finish off with the value types in C# talking about how we can use bits to represent a couple of other things. One of the things that we'd like to be able to represent in the computer is characters. So for example, if we were running a game where the player uses the keyboard to enter menu choices, say it's a text-based game if you must, we will we'll read in from the keyboard a player's character input and then store it. And so characters are one thing that we like to store. And in C#, characters are stored in the data type called char. Some people will call it char, but I'll always call it char. So a char is comprised of 16 bits, and it stores the Unicode representation of a particular character. If you've been around for a while, you've heard of ASCII. ASCII was an 8-bit representation of characters, but we have moved on from ASCII, except in very tightly constrained environments, to using Unicode instead. And so we use the char data type to store characters in our programs. Given that, you have an in-lecture quiz that you need to complete now. The other value type that C# provides to us is Boolean. And in fact, the data type itself is called bool. And bools only have one of two possible values. They're true or false. Some of my students try to make me angry by saying the two values are 1 and 0, or 0 and not 0, or some other thing. But in fact, bools in C# store true or false. And we're going to find that this is really, really useful to us when we need to make decisions in our program. If we need to decide between two or more courses of action, or if we are iterating or looping for a while. For example, while a user enters invalid data, we keep looping until they've entered valid data. We'll find that the bool data type is very helpful for us to accomplish those programming actions. So far, the operations that we've talked about for data types have been fairly intuitive in what you're used to. It may not be the case that you're used to the Boolean operators. So let's talk about the three that we're going to use in a little more detail. The first is AND. So the way AND works is we have two Boolean operands. So each of the operands can be true or false. And the way AND works is AND evaluates to true if both of those operands are true. If either one of them is false, including both of them being false, AND will evaluate to false. So AND is all about they both have to be true. The second Boolean operation is OR. And OR works differently. OR is basically checking to see if one or both of them are true. So the only way that OR evaluates to false is if both of the operands are false. And finally, NOT. And NOT is kind of a fun one. It is a unary operator, and so it only is applied to a single operand. But this is one of those great times where you actually just can use logic, right? Not true is false. Not false is true. And so we can use this to do what's called negating a Boolean operand, to flip it, to change it to the opposite value. And that works, of course, because there are only two values that a Boolean variable can have. Okay, given that discussion, you have another in-lecture quiz to accomplish. This is an incredibly short lecture. So to recap, sort of over the last few lectures, we've talked about value types, and value types can be used to represent integers, real numbers, characters, and Booleans. And that's really what you should take out of Module 3, of course with some practice, doing the labs hopefully, and definitely doing the programming assignment. Next week and next time, we'll start on Module 4, where we start talking about classes and objects, which are really the foundations of object-oriented programming. Here we are in the second week of the class, and starting on Module 4, which is about classes and objects. Just to let you know the learning objectives for Module 4, here they are. This is the only module that has an objective about creating. We're going to be designing a class together at the end of this module, but we'll also be applying the knowledge you learn by using existing classes that I provide to you. In this module, we're going to talk about the foundational ideas behind the object-oriented paradigm. So here's the big idea. The big idea is that software can be implemented as a collection of objects that interact with each other. So this paradigm is very well suited to game development because if you think about it, games are virtual worlds where there's a bunch of different entities that interact with each other. If you're walking along in the virtual world and you see an orc, you might decide to interact with that orc in a particular way, with your bare hands or your sword of massive cutting or whatever. If you see a teddy bear in the game world, you may decide to interact with that teddy bear in a particular way. So you might hug the teddy bear, or you might explode the teddy bear, or you might light the teddy bear on fire, or you'd interact with that object in some way. And even non-player characters, right? The NPCs interact with each other and with you as part of the game world. So there's lots of interactions between objects or entities in game worlds. So modeling those game worlds in our software as interacting objects is a really powerful technique that we can use. We'll start off with an in-lecture quiz so you can tell me a little bit about what you already understand about software objects. Okay, so software objects have three different things. They have state, they have behavior, and they have identity. And we can relate this to objects in the real world as well. So the state of an object is the characteristics of that object. Think of yourself right now. You have a number of different characteristics. You have a height, you have a weight, you have a degree of hungriness, and perhaps a degree of boredom, how cruel. But these are different characteristics that you have that potentially change over time. You might grow taller, you might shrink, you might gain or lose weight, and so on. So the state of an object is really all about the characteristics of that object. Objects also have behavior. So there are things that we can do to objects, like we could take a teddy bear and throw it. And there are things that we can tell objects to do to themselves. So when we get to X and A in particular, we'll tell an object to, perhaps we'd tell a teddy bear to draw itself. And so we don't have to worry about the details of how a teddy bear draws itself. We just tell it to do so. Similarly, if we had a deck of cards, we might just tell that deck, go shuffle yourself. And we don't care how it happens. It's just that it happens internally to the object. So objects have behavior as well. They have things they can do or that we can do to them. And finally, objects have identity. We will end up, or we'll discover that we create objects as we go along in our software, as our software program runs. And each of those objects lives, if you will, in a different place in memory. And so each of them are distinct from each other. And so they have identity. And that's good too, right? If you are in a traditional classroom, and somebody wanted to call on a particular student, you can't just yell out the question. You have to first say which student you mean, and then ask your question. Similarly, with objects, if we want them to do something, we need to specify which object we expect to do that thing before we sort of access the behavior of that object. So identity is really important as well. So all objects have state, behavior, and identity. That's a language-independent, object-oriented set of concepts. Really has nothing to do with C#. The next slide uses some C# specific terminology. So let's actually have a concrete example. We're going to have a playing card object. And that playing card object is going to have state, behavior, and identity. And the state of that playing card will be stored in fields. Those are, that's a C# piece of terminology, but I'll tell you right now, fields are just variables. We learned in the last module how we can declare and use variables. Well, the fields in an object are just variables. Externally from the object, the way we'll let sort of consumers of this object, so the game, for example, has a playing card in it, and the game needs to know something about the state of this card. We almost never will let consumers of this object access those fields directly. That's really bad programming practice. So instead what we'll do is we will expose, that's the terminology we use, we will expose that state through C# properties. If you've programmed in other languages like Java, for example, you've written getters and setters or accessors and mutators all the time. In C#, we have this concept called properties that does exactly the same thing. It lets us access, read, write, or both, particular pieces of state for the particular object. So that's state. And for a card, the particular things we might store for state are the rank of the card, ace, king, queen, and so on. The suit of the card, depending on the game you're playing, grass, water, fire, or perhaps hearts, clubs, spades, and diamonds. And whether or not the card is face up or not, which would matter to us if we were actually drawing the card. So, you draw a face down card, nobody can tell what it is. You draw a face up card and everyone can tell what it is. Okay, so that's state. There's also behavior associated with the object, and in C#, we expose behavior through things called methods. Other languages use terminology like methods or functions. They're methods in C#. And the method that we'll have for our card will be to flip it over. And finally, cards get their identity when we create new card objects, and that's called instantiation. So another opportunity to do an in-lecture quiz addressing particularly the state of objects. So conceptually for our card, what we have is inside here, hidden inside the card, we have those fields that we don't let anyone access externally. And by the way, having the fields and around the edge here, all of these different properties and behaviors, bundling all that stuff together is called encapsulation, because we've put the state and the behavior all into a single capsule, if you will, that object that carries all this stuff around. The other thing that's important, though, is as we access things like properties, like the suit property here, or as we call a method, the flip over method here, the other thing that we know is that the consumer of this object doesn't know anything about the internal details. They have no idea how it's implemented. They have no idea what data types the rank, suit, and face up are. There are logical choices, but we don't know. And so this is another important object-oriented concept called information hiding. The implementation details are hidden inside the class. So we can change those. We could change the data type we use to store the rank of the card, and as long as we didn't actually change the property, then consumers of this class or this object could just keep using that property without even knowing that the implementation details changed. And that is fantastic for when we actually use objects in large software systems over time, because we make changes all the time when we don't break the rest of the software. So this conceptual idea of an object where we have the fields hidden inside and then we sort of have this boundary of stuff that we expose to people, consumers of the object to use, is a really powerful object-oriented idea that we will see again and again. Now, I keep talking about objects and classes, and there's an important distinction between the two, and so let's get that distinction nailed down right now. The class is actually the template for creating objects. The class is not an object itself. It's sort of the cookie cutter, if you will. It tells us what all the cookies will look like, and cookies tend not to have behavior unless you have scary dreams or something about cookies, but it tells us sort of the shape, if you will, of the objects that we're going to create. But it's not an object itself. But the good news is it's a template, and we can use the class to create as many of the actual objects as we want, just as you can use a cookie cutter to create as many cookies as you want. So it's a template that defines the state and behavior of each of the objects that get created from this class. The objects are the actual things, right? They're the actual things in memory. And so we can have a whole bunch of them. We can have a whole bunch of playing cards if we wanted to play cards. Playing cards with one card is kind of a boring game. And even though each card knows, let me put it a different way. Even though the class says that each card will store a rank and a suit and whether or not it's face up, each of the individual card objects maintains their own current information, right? So each of these cards has a rank and a suit and whether or not it's face up. But those ranks and suits and face ups can be different, right? We can have a king of spades as well as a queen of hearts. And they're still all cards. They're just different instances of the cards. So classes are a template. Objects are the actual things that are instances of, that's the terminology we use, that are instances of that class. Now, when we talk about class design, not actually using classes externally as consumers of the classes, but actually designing classes and understanding how they're implemented, we often use this notation that I've provided here. And this notation includes the class name, the fields, so these are the things that we're always going to make internal to the class, the properties for the class, so these are the things, these are the ways that we're going to provide external consumers of the class to actually find out about the state, and finally methods, that behavior stuff that we've been talking about. This notation is called UML, and clearly there's an in-lecture quiz about UML and what it means. Despite what you might have chosen in that quiz, it stands for Unified Modeling Language, and it's really the most commonly used notation these days for specifying object-oriented systems. Okay, before we finish the lecture, because we're almost done, we've hit the big ideas behind object-oriented implementations, the whole object-oriented paradigm, and we'll start using it next time. But before we leave, I need to point out that classes are not value types. Classes are reference types. Remember in the previous module I said, well, we won't worry about reference types until module 4. Well, here we are in module 4. So classes are reference types. And really, classes are each a data type. So, we had int and float, for example. Well, when you start implementing classes, you're creating your very own data types. And they're reference types rather than value types because for value types, the ones and zeros at the memory location for the variable represent the value of that variable. For reference types, the ones and zeros at the memory location for the variable represent a reference to where the object actually is in memory. So people try not to use the word pointer, but it's just a pointer to where the object actually lives. So a picture might help. Here we go. So age is an integer variable, so it's a value type. So the value 17, the ones and zeros 17 in that memory location mean age is 17. The rain message, which is an instance of a message object that you can read about in the, instance of a message class, which you can read about in the book if you choose to, but it just holds the message and lets you print it and so on. The ones and zeros there at that memory location represent 44, but 44 is not the value, it's a pointer or a reference to a different place in memory where the object actually is. So that's that distinction between reference types and value types that I said we'd get to in this module. Okay, to recap, the object-oriented paradigm, not just C#, just object orientation in general, provides classes and objects where classes serve as the template for creating objects, and objects have state, behavior, and identity. We also learned that objects interact with each other in the software that we write to actually implement our game or whatever else we're doing with our software. It might not be a game, how sad. Next time, so this was all conceptual stuff, important foundational conceptual stuff to understand how object orientation works, but next time we'll actually dig in and start using this stuff in a C# program. Here we are in the second lecture of Module 4, the module about classes and objects. And as a reminder, here are the two module learning objectives we have for this module. And we're really still working on the first of those two learning objectives. Last time, we learned the conceptual ideas behind the object-oriented paradigm in general, and we learned some C# specific terminology about how we deal with classes and objects. This time, we're going to go beyond the terminology and actually start using classes and objects in C#. So the first thing we're going to need to do if we're going to do an object-oriented program is we're going to need to know how to instantiate an object from a class. Of course, that means you have an in-lecture quiz to handle. When we need to start interacting with particular classes, we need information about those classes. We need to know how we, as consumers of that class, can interact with it. And guess what? The way we learn that is through documentation. You will spend lots and lots of time reading documentation to understand how to interact with classes and the objects we create from those classes. This particular slide shows some documentation for a deck class that I wrote. You'll notice that it is in the Lab 4 class library. So if you decide to go do that optional Lab 4, this is where this documentation comes from and where the class comes from. But you should also know that this documentation did not just magically appear. I generated this documentation using the documentation comments, those 3/ comments we put above classes and methods and properties. So this actually is generated because I did the documentation comments, so it was easy to generate, and it makes it so that consumers of the class can actually use the class, which is good. Programmers need to know how to use the tools we provide to them. So this is documentation for the class, and the heading here says deck members. Deck members are really all the constructors, which is how we instantiate instances of the class. We use a constructor, and the methods and the properties of the class. It can also include the fields if we made them publicly available and so on, but we tend to exclude those from the documentation because they're hidden. That's the information hiding thing. So we've got this documentation, and if we want to know how to instantiate a deck object, and that's going to be the example for today, then we need to be able to use the constructor. And to know how to use the constructor, we actually have to look at the constructor documentation. So I clicked on the deck link to get to information about the constructor. And here's the information you're going to care about. The constructor is public in this case, which is great because if we can't actually access the deck constructor to create a new deck, that is useless to us. Later on, more advanced programming, you'll discover that constructors aren't always public. But for this class, the constructors will always be public. We know that the constructor's name is deck, and that will always be the case. The constructor will always be the class name. That's just always going to be the way it is. And the last thing we see is right here, hard for me to get it, I think, but there were a couple of parentheses there, and there was nothing between them, which means when we call the constructor, there's no information that we need to provide to actually use the constructor. Okay, so let's actually get started. I'm going to open up a project that I already created just so that I could include the deck class and have that already built in. So let's go to that now. So I've opened up this project. It's a console application that I called using deck class. You'll notice that it is a console application, and I've added some comments, and I'll zoom in so you can see them. I've added some comments about what the program is all about and what the main method is all about, including command line args. So, first thing we want to do is we want to create a deck object. The way we have to declare a variable just like we did with value types. So we know that that started with the data type, followed by the variable name, followed by optionally assigning a value to the variable. And so that's what we're going to do here. So your first question is, what's the data type? Well, a deck of cards is definitely not an int, right? A deck of cards is not a whole number. It's, and it's not a floating point number either, nor is it a single character. So it's none of the value types. Remember I said that classes are basically their own data types. So the data type we need for an object of the class deck, the data type is deck. Now we need to give it a variable name, and I'm going to call it deck. Remember, C# is case sensitive, so lowercase d in the deck makes it different from capital D in the deck for the class name. So this declares a variable. I am going to right now use the constructor to actually create a new object. The way I use the constructor is I say new. That's a special word in C#. You can see it turned blue. It's a keyword. I'm saying give me a new object, and then I tell it the class name. It's deck. And just as there were parentheses in the documentation for the deck constructor, I need parentheses here. So I'm going to also, knowing I'm going to want that blank line at the end, I'll add it now, like so. And so I've created a new deck, and if I run this code with Control F5, it's not very exciting at all. It just says press any key to continue. Good news is it didn't blow up and break, so we can infer that it actually created the deck appropriately. So that's how we use a constructor. We just say new, and then the name of the class we're trying to construct, and then we put the parentheses. And if it required us to pass some information, we would. And we're going to see an example of passing information to a method next time, but not this time. We don't have to worry about passing any information. So I've created this deck object. The next thing I want to do is I actually want to find out information about the state of the deck. And so you should do an in-lecture quiz to see if you remember, because we talked about this last time, if you remember how we get at the state of the deck from outside the deck. Going back to our documentation for the deck, we can see that we already looked at the constructor here, and we can see a listing of all the properties that the deck exposes. And there's only one. It's empty. And so this property will tell us whether or not the deck is empty. To get some more details about this property, I clicked on the empty link. And when I did, I got this documentation. And this documentation tells us a couple of different things about the property. First of all, it tells us that the property is public. That's good news because we want to access it from outside the class, so that's great. It tells us that this property is a bool, and we are familiar with bools. We know about bools, they're true or false, which makes sense for finding out whether the deck is empty or not. That's a true or false thing. And the last thing we see is that we can get whether or not the deck is empty, which is what we'll do here, but we can't set whether or not the deck is empty. So we can find out if it's empty, but we can't say to the deck, hey deck, you're empty. I don't care how many cards you have in you, I've decided you're empty. So now we should look at the actual syntax for accessing this property. Now that we know that it's a bool property and that we can get this information. So back to our environment. Print deck empty information. So I'm going to show you two different ways we can do this. The first is to have a Boolean variable that we declare here. We can call it isDeckEmpty, and we're going to assign a value to this variable. And the value we're going to assign is finding out whether the deck is empty. So we're going to access the empty property. Before we do, the first thing we need to do is put the name of the object we care about. Again, here's an example. So I'm in a classroom and I say, are you hungry? Which student do I mean? Everyone's going to yell out something, right? And probably, why didn't you bring us food? But I'm going to need to talk to a particular student. Not that I think of my students as objects, but a student object and say, are you hungry? And so similarly, I need to know whether a particular deck is empty. Not sort of all the decks in the universe, but a particular one. Luckily, I have a deck object right here. So the first thing I do is put the object name. Just like I would say, Joe, are you hungry? Or Mary, are you hungry? I'll say deck dot, and then I access the property. Now, when I access properties, I just put object name dot property name, and that's it. And then the semicolon that I'm putting at the end of every line of code I write in C#. Okay, so that's how you access a property. Now that I have stored that information into the isDeckEmpty variable, I can print it out with a console write line. Like so. And when I run this program, it comes back and says empty is false. The constructor for the deck, you don't know this, right, because it's internal to the deck, but I can tell you, because I wrote the deck class, that the constructor for the deck generates 52 cards and fills the deck with them. So we can find out whether the deck is empty by accessing that property, the empty property. Because we're not really doing anything very interesting with this deck empty property, it feels kind of wasteful to declare a variable to hold it. So here's a shorter and still very obvious way to print out the same information. Instead of accessing the property and shoving it into a variable, we can just access the property as part of our console write line. So if I control F5 again, we see exactly the same behavior that we saw before. I'm going to save all. And that's it for what we're trying to do today in C# code. We used a constructor to create a new object, and we used a property access to get access to the state of that particular object. So we've already practiced with constructors and properties. Next time, we'll take a look at methods and start using a couple of different methods on the deck object to actually access the deck's behavior. Last time, we talked about how to use C# constructors to instantiate a class to create a new object, and we also talked about how we could access properties of the object that we created. This time, we're going to talk about how we use methods to get at the behavior that the object provides to us. Before we start talking about the details, here's a reminder of the module learning objectives for this module. We're still working on the first one. We'll handle the second one next time. We'll immediately start with an in-lecture quiz, so you can tell me whether or not you remember how we actually access the behavior of an object. To figure out which methods we want to use, we read the documentation. So we're going to continue working with our deck class. And as we look at this documentation, we see that there's a list of 4 different methods with the description of what those methods do. So we're going to interact with 3 of those methods. We won't worry about the print method today, but we'll try the other 3 to get some practice in how we actually call a method on a particular object. We'll start with the shuffle method so that we can tell the deck to shuffle itself. So let's talk about what this documentation tells us. First of all, we know the method is public. And all the methods we're going to look at are public. So we will be accessing them from external to the deck class. The next thing is we have this indicator of what data type the method actually returns. So sometimes the method will return something to us, and we'll see that before we finish the lecture. But sometimes it doesn't. Sometimes it just, the deck shuffles itself, but what would it give back to us? There's nothing to get back. And there's a special word that we use in C# to say this method really doesn't return anything to us, and that word is void. So the shuffle method doesn't return anything to us. The next thing we see, I won't bother underlining it, is the method name. So the method name for shuffling the deck is shuffle. And then finally, just as for the constructor, we have parentheses that say what kind of information needs to be provided to the method. And for the shuffle method, there is no information that needs to be provided. So let's go to our environment. Now, I basically saved our project from last time and we'll build on it this time. Sometimes when you open up a Visual Studio project, you'll see something like this, where there are no classes open and you have a big blank blue screen, especially if I've provided some code to you. You might see it this way. The easy thing is, all along the right-hand side here, we have all the classes included in our solution. So for a console application, program.cs, we double-click it, it opens up our C# file, we zoom in, and so this is where we were working before. After printing the deck empty information, let's tell the deck to shuffle itself. And of course, we don't start comments with single quotes, we start them with // Now, just as here, when we wanted to find out whether a particular deck was empty, we had to first provide the object, the variable, for the deck we cared about. So we do the same exact thing with the method call. So the first thing I type is deck, and then I put dot, and then I put the method name. In this case, shuffle. Now, methods, the way we call methods, is different from the way that we access properties because we always put parentheses, just like we did with the constructor. When we called the constructor up here, we had to provide parentheses even though we didn't provide any information. Down here, same thing. Calling a method, we always have parentheses. Accessing a property, we never have parentheses. That's the rule. Okay, so I will Control F5, even though there's nothing really interesting here. So in fact, I won't say I lied, but let's actually print the deck both before and after the shuffle, just to see that there was a shuffle. And we'll even add a blank line between the two so we can easily see where that shuffle occurred. We won't necessarily keep this code throughout the whole lesson, but we'll use it for now as sort of temporary testing code. So we'll tell the deck to print itself. And you'll notice I called this method in exactly the same way I called shuffle. I just changed the method name. And then we'll shuffle it. And then we'll tell the deck to print itself again. And in fact, we better add that blank line I promised you. Like so. So when I Control F5, I've created the deck. I'm going to scroll up in this window. And we'll see, here's the empty access. And then we see the deck is printed out in order by rank and then by suit. We look for the blank line. There it is. And now we look at the contents of the deck from top to bottom. And we see that it's shuffled. So we have assurance that I have, in fact, shuffled the deck properly. Now this was temporary testing code, so I'm highlighting or selecting this line and clicking up here that says commented out. I'm going to select these lines and say comment them out. So that's a really useful development environment thing to be able to add code and comment it out when we don't want it anymore. Eventually we would get rid of this code, but we'll leave it there for now. And that's it for telling the deck to shuffle itself, our first call to a method to actually make the deck object do something. The next method we're going to look at is cut, because that's slightly more complicated in terms of the way we call the method. So let's move on to the cut. And here's what's different. It's still public. It's still void. The method name is different, as you'd expect. But the big difference is right here in the documentation. For the first time, we're seeing something that we call that has something between those parentheses, something that we're supposed to provide to the method. And in this particular case, it says the location at which to cut the deck. That's what we're supposed to provide. Now, from the method's perspective, this piece of information is called a parameter. From the calling side, the side where we're going to call it from, it's called an argument. The good news is the only thing that we really care about is not the name of the parameter, but we do care that it's supposed to be an int. So when we call the cut method, we're going to provide an int as an argument. So let's actually do that. Let's put it right, that testing code is handy for us. Let's put it right here. We'll say cut the deck. And we're going to tell the deck to cut itself. And so we'll say cut. But when we go here, we open the parenthesis, and it actually tells us in this little pop-up box, it tells us you're supposed to provide a location. And so let's cut the deck right in the middle. We'll do it at location 26. And the reason I said it's nice that we saved that testing code is I'm actually going to uncomment this again. And I'm actually going to comment the shuffle as well. Why am I commenting the shuffle? Because the shuffle adds a sort of randomizes the order of the cards in the deck, and I'd rather just see that the cut occurred properly. So I meant to uncomment this, so I'll click that twice. In fact, I'll do this one again too. So basically we're going to print the deck in order as the deck was produced by the deck factory, if you will. And then we're going to cut the deck. We've commented out the shuffle. And then we're going to print the deck again so that we can confirm that it actually got cut. So Control F5, and we'll scroll up to the top just to remind ourselves that it starts with clubs and diamonds and then goes to hearts and spades. But after the space, we see that the hearts and spades are on top and then the clubs and diamonds are down below. So we've cut the deck properly. Great. So this debugging code that we added just to make sure, or testing code if you will, to make sure it's working, is coming pretty handy so far. So now we've done two different methods. Both of them returned void. So the first one returned nothing and we didn't have to provide anything and it just shuffled the deck. The second one, it returned nothing and we had to provide one piece of information to it. So let's look at one more example of how we call methods. The next method that we want to take a look at will be take top card. Because it's fairly common for us to actually want to take the top card from a deck, whether we're flipping it over into a pile or handing it to a player or something like that. So we want to take the top card. Again, it's a public method. This time though, we can see here that it doesn't return nothing. It returns a card object. So that makes sense, right? If we're going to take the top card from the deck, we want to put it somewhere or print it or something, and so we would want to take that card. So let's actually comment out our testing code one more time. I'll even comment out the cutting the deck so that we know which card we really expect to get. We should get the ace of clubs when we take the top card. So let's actually take the top card, take top card, and print info. So this time, the method actually returns something to us, and we want to hold it in a variable. We know it returns a card, so this variable we hold it in needs to be of type card. I'll just call the variable card, and then we tell the deck that we want to take the top card, like so. And then we're going to print the rank and suit of the card by accessing the properties of the card, just like we accessed the property of the deck to see if it was empty. So we'll do a console write line, and we'll access the rank, and then we'll concatenate a string that says of with spaces on both sides, and then we'll concatenate the suit. So now when I run the code, the deck is not empty and we get the king of spades. So I lied to you. When we print the deck, we actually print it from bottom to top, not from top to bottom. So we got the top card, which is the king of spades. And actually, if you take a look at the book, it talks about why, for efficiency's sake, we want to do it that way. Okay, so I got to the king of spades. Now, a caution for you. It is in fact possible, comment out this code, it is possible, even though the take top card method returns a card object, we can still call the method without putting the result into a variable. Basically what happens is we call the method, it hands an object back to us, and conceptually anyway, we just throw it on the ground and say, oh, I don't need that card after all. The problem is, of course, that if I've done that, now I can't print out information about the card. So this is useful sometimes, being able to call a method that returns something without storing what it returns, but it is not generally useful. Usually when we call a method that's going to return something, we want to store whatever it returns. And that's it for the C# calling three different kinds of methods on the deck class. One that doesn't return anything and doesn't have any parameters. One that doesn't return anything and does have a parameter or an argument from the calling side, that cut method. And one that does return something but doesn't require us to provide any information. So, to recap, we learned how to call various methods, and that completes our how do we handle the C# things with classes and objects. We now know how to create objects using the constructor. We know how to access the state of the objects using properties. And we know how to access the behavior of those objects by calling their methods. Next time, we'll finally get to that second module learning objective where we will in fact go through a design process for a class. Here we are in the last lecture for Module 4 about classes and objects. And as a reminder, here are the module learning objectives. And we've finally gotten to the one where we're going to design a new class together. So at this point in the module, we've discussed the foundational ideas behind the object-oriented paradigm, and we've discussed how to use those ideas in a C# program. Now we're going to step back from the programming and do a higher level design activity to design a class. Before we actually do that, you should take this in-lecture quiz. So before we can design our rubber chicken class, we have to think deeply about our game design and really decide what role does the rubber chicken play in our game. Now you might think that the player avatar would be an awesome thing to use the rubber chicken for. Sadly, not this time. This time, we're going to design the rubber chicken as a weapon. So it won't be a very limited weapon, of course, because rubber chickens are pretty flexible. I hope you got that. Rubber chickens can be either melee weapons, as you might be able to imagine, and they can be ranged weapons as well. So the way we're going to approach this is first, we're going to think about the state. What kind of information do we need to store to capture the characteristics of the rubber chicken? And then we'll move on to behavior. Now it's important for you to realize that as we design real classes for real games, we end up iterating between state and behavior as we go along. We might discover we need some new behavior as we're developing our game, at which point we probably need to go back and add some more state as well. So this is sort of an atypical small example. We'll cover state and then we'll cover behavior. So you should now go to the in-lecture quiz, which really has you pause and think about the state of the rubber chicken for a while, and then come back and we'll talk about it. Okay, so there is some reasonable state information that we might store for a rubber chicken that we're going to use as a weapon in our game. First of all, we're going to need location. We need to know where the rubber chicken is so that we can do collision detection. Especially if you're good at using your rubber chicken weapon, you're going to actually collide that rubber chicken with other stuff. And the way we actually figure out that that's happened is by using the location of the rubber chicken. Rubber chickens also have velocity, especially when they're used as a ranged weapon. So if we were to throw the rubber chicken, it has a particular velocity. And so we're going to need that velocity so that we can change the rubber chicken's location over time. We also have a range for the rubber chicken. How far can you throw it, for example? And so, you get upgrades, you get rubber chicken upgrades as you work your way through this fictional game that hopefully no one will ever build. So you get these upgrades to your rubber chicken, and so you can fling your rubber chicken further if you increase the range through those upgrades. Accuracy, you also have accuracy with your rubber chicken. You can't just fling it in any direction and expect to hit stuff. You need to actually be good at aiming your rubber chicken. Wow, there are some weird things I'm saying today, but that's okay. You have to be able to aim your rubber chicken with some level of accuracy, and again, you might be able to upgrade that stuff. Rubber chickens, when we do get that collision with something, rubber chickens inflict damage. Now that damage could be variable. right? It could be based on how far away the rubber chicken was, its velocity when it strikes whatever it hits, because if you use it as a ranged weapon towards something close, it will probably do more damage than if you use it as a ranged weapon and you throw it far away. So there's some damage that's probably variable, unless we stuff our rubber chicken with a C4, in which case it probably always inflicts about the same amount of damage when it hits something and explodes. The last thing we probably want to store, which you may not have thought of, is who is the owner of this rubber chicken. And it's not because we need, somebody to feed and care for this rubber chicken. It's because usually what happens, especially in games with weapons, especially in games with ranged weapons, is if you inflict damage by throwing your rubber chicken towards something, and the rubber chicken hits and destroys, I don't know, something, imagine something, hits and destroys something, usually the owner of that particular projectile, in this case, will end up getting points or upgrades or something, right? So you actually need to keep track of who is the owner of the rubber chicken so that we could allocate those benefits to whoever damaged something with the rubber chicken. Okay, so if that hasn't been disturbing enough to you, that's great. Hang with me. We'll see how much more damage we can do. So you should now go do another in-lecture quiz where you really think about what kind of behaviors should this rubber chicken have, and then click continue and we'll move on together. Okay, so there are a number of reasonable behaviors that this rubber chicken could have. For example, we're going to want to update this rubber chicken. Remember we haven't talked yet, but we will talk soon about a game loop where we update the game world so that we sort of update the status of everything in our game world and then we draw it. So we will want to update the rubber chicken periodically, every frame in our game in general, so that the location changes based on the velocity. So we definitely want the rubber chicken to expose an update behavior so that we can change its location as we go along. We might also want our rubber chicken to exhibit an explode behavior, so we could call a method telling the rubber chicken to explode. That really only applies if we're using the whole C4 rubber chicken approach, but it's worth thinking about. We also may, if we have a more interesting game, we may have the rubber chicken play an animation. It could play one animation as it flies through the air, another animation right before it realizes it's going to explode, because rubber chickens are pretty self-aware and they know that's going to happen. And a variety of other animations just for humor. If you're building a game with rubber chicken weapons, you probably are keying into the humor idea, so playing some animations might be interesting. I have in fact done this class design exercise in a sort of normal, well, not a normal classroom, a classroom of my game development students, let's put it that way. And so I felt compelled to tell you that there is one unreasonable behavior, at least for the rubber chicken, and most rubber chickens are not going to in fact turn into a live chicken sometime in the game. That would just be wrong. This is not Pinocchio with rubber chickens. So we probably are not going to convert our rubber chicken into a live chicken. Okay, so that was sort of a short and sweet, what thought process do we go through to actually design the classes in our game? And that's probably enough for sort of the informal figuring out what you need as you build classes in your games. More advanced object-oriented analysis and design uses much more formal tools to actually figure out state and behavior and so on. And so in later classes that I teach at UCCS, we actually cover those kinds of things. But this sort of informal thinking about it kind of process, including understanding that you're probably going to iterate and practice, is a reasonable first taste towards how we actually design stuff. So that's the end of Module 4. Next time, we'll actually move on to talking about the XNA framework. As you've seen from the notes that I've put in some prior videos, I recorded these lectures using Visual Studio C# 2010 and the XNA framework from Microsoft. What we're actually using for the course, though, is Visual Studio Community 2015 and Monogame 3.4. There is a minor difference between those two environments, and that's in how we actually create new game projects. And there's a major difference between those two, and that's how we include content into our games. And so the videos in this module will use Visual Studio Community 2015 and Monogame, so you can see how we do those two things. But the differences are minor enough that I haven't gone back and re-recorded all the videos for the entire course. So all the code that I provide to you for all the lectures in the course are using the new environment. But the videos have some slight differences that you should be able to understand after seeing it the sort of modern way in this particular module. In this module, we're going to start talking about how we use XNA to develop games. The module learning objectives for this module are provided here. So first, we're going to understand the different methods that are contained in the Game 1 class, and that's what we're going to talk about today. And then we're going to, over the course of the next couple lectures, we'll learn how to draw sprites, load sprites, develop games using existing classes, design for use in XNA, and so on. So in the previous module, we learned a lot of stuff about classes and objects, and I made the claim that object-oriented analysis and design and implementation is very useful in the game domain, and we will see that here as we start dealing with XNA. As we're talking about XNA, you should understand, though, that even though we'll talk about some XNA specifics, there's lots of stuff that we're going to talk about that is about game development in general. It will be applicable to any game development framework you use, not just XNA. With that said, you should start off with an in-lecture quiz. Okay, so ignoring XNA, there are a number of general things that we do in any game that we build. The first thing we do is we initialize the game. That could include setting score to 0. That could include sort of initializing some information that we're going to need throughout the game, but we do something to get the game into its starting or initial state. We also load content. So when we talk about content, we mean things like the graphical assets that you're going to use in a game. If you're using a 2D game, those graphical assets are typically called sprites. If you're building a 3D game, you might have models and textures that you're importing. So, and audio, of course, if you have music and sound effects in your games, those are also considered content. So usually, not always, but usually, we think of content as the thing that comes from artists and designers, not programmers. Programmer-developed art is always interesting, but not necessarily what you want in your high-quality game. So one other form of content is things like level specifications. If you have a level building tool and you have level designers building levels, you might load that content. You have to load that content before you actually run your game. Now, content loading, generally we do some upfront early on, and regularly we will find ourselves loading more content as we go through a game. So for example, we might load the initial level, and then once the player has completed that level, we're going to need to load the next level. We don't usually load all the levels all at once because that takes too long and players get bored as they wait for that to happen. So we load content throughout the game too, but we're going to find that usually there's some content we need to load up front. So we do this initialization stuff, and then we load content that we're going to need, at least initially, in our game. And then we enter what's typically called the game loop. And this game loop basically runs until the player quits the game. So the game loop is, the game loop is update the game, change the game world. So that means moving a rubber chicken through the game world if the rubber chicken happens to have velocity. It means having non-player characters do planning for how they're going to come get you. It means all kinds of stuff where we update the game world. And then we draw it, because updating the game world without actually showing the player those updates to the game world leads to a fairly boring game, right? It's all invisible. So we update the game world, then we draw it. You will sometimes hear that called rendering. And then we update the game world, and then we draw it, and we update and draw until the player quits the game, essentially. Now sometimes, we move between playing the game and dealing with the menus and those kinds of things, but we're still updating, drawing, updating, drawing, updating, drawing as we go along. So those are standard ideas that happen no matter what game development framework you're using. However, let's fire up XNA and look at how XNA supports those things. So I open up the environment and I select New Project over here on the left, and then I get a set of possibilities for the new project. None of these are monogame games, but if you look under the Visual C# templates here, there is a monogame section. So I'll select that, and I'll select Monogame Windows Project. I will rename the project Intro to XNA. And then I'm going to browse to a reasonable location to save it and click OK. And then we'll come back and look and see what template gets generated for us. You may find when it generates the new project for you that there's no code actually shown over here in the blue pane on the left. So we can just click on game1.cs and it will show us the game1 class that we actually want to look at. Okay, before we actually look at these details, I would like you to go do an in-lecture quiz just to make sure that you internalized those ideas of the game loop. Okay, so let's talk about the first few things that get supported in XNA. I am going to zoom in, of course. And you saw this template before, though I didn't zoom in before, because this is what XNA gives us when we say we want to do a Windows game. Right here is the constructor. We know about constructors. They're used to instantiate objects. So if there's stuff that we want to do when this game object gets created, then we do it here in the constructor. However, that's a trade-off because we can also do those things right here in the initialize method. So we talked about initialization, setting the score to 0, those kinds of things. That's what you would put here in the initialize method, because what happens is the sequence of events for XNA games is the constructor gets called to create a game object, then initialize gets called to initialize the game world, then load content gets called to load that content we were talking about, graphics, sound effects, those kinds of things, and then XNA enters the game loop. So these first three things, constructor, initialize method, and load content, support those pre-game loop activities that we do in pretty much every game we build. So this is a good opportunity for you to go do another in-lecture quiz to make sure you understand what load content is all about. The next thing we'll do is we will go to the update method. We're going to skip the unload content. For the games you do in this course, you'll never have to use that. For larger games, of course, you would unload content so that you didn't have everything in memory as you went along for the 23-hour play session or anything like that, because that will slow people's computers or consoles down. So there are certainly periods in which we unload content in games. We're not going to need to ever do that in this course. So we move on to the update method. And the update method gets called every frame in the game, no matter what. So even if the game really starts to slow down, what will happen is the update method always gets called And the draw method, which we'll look at soon, the draw method gets called as it's possible to call it, as long as it's not going too slow. Again, unless you do something really nuts in this class, you're never going to end up with a slow running game where you see frame drops and stuff like that. Okay, so here in the update method, there's some pre-built stuff. Notice it, well, it may not be clear yet because we haven't even talked about how we use the Xbox controller, but this basically lets you press the back button and leave the game if you choose to do so. And then we're going to add all our world updating logic here. And we don't need any of that right now, but this method will get called every frame, so we know whenever we need to update the game world, this is where we do it. So you should go do another in-lecture quiz that asks you an XNA specific question about updating. And then finally, because we're inside the game loop now, we update the game world and then we render or draw it. And so here's where we draw our game. So update gets called and then draw. And this by default clears the screen to a cornflower blue. That's why we get that cornflower blue when we run it. Here, let me run it just to remind you. So we get a cornflower blue screen drawn. And then we'll add some drawing code here when it's time for us to actually draw stuff. So the draw method will draw all the visible entities in our game. So there's one more in lecture quiz that will ask about your understanding of pixels in general. We're going to focus, in fact, I will say we are exclusively going to do 2D games in this class. Stepping to 3D is absolutely possible once you've built a good foundation of expertise, but is definitely not beginning programmer stuff. So we'll do 2D games here, and 2D games we regularly think about, therefore, two-dimensional sprites that we're going to display, and two-dimensional sprites have 4 components, as long as we're going to support transparency or opacity. Those 4 components are a red component, a green component, a blue component, that's the RGB stuff you've heard of before, and an alpha component. And so you should now go do the in-lecture quiz to tell me if you understand what alpha means. Okay, I am not going to save that particular project. Don't worry, we'll build one next time that we actually end up saving. In fact, I've already pre-built it. So to recap for today though, the standard game stuff that almost all games do include initialization, loading content, updating the game world, and drawing the game world. And that update and draw is contained in what's called a game loop, and it happens until the player ends the game. We also took a look at how XNA supports those different activities within the template that it's provided to us when we, in Visual C# 2010 Express, say we want a new Windows game. And so next time we'll actually use XNA to build a, I hate to call it a game, so I'll put it in quotes, to build our first game in XNA. This is the second lecture in Module 5 where we're exploring XNA and how we can use it to build games. So here are the Module 5 learning objectives, and today we're going to address the second one, where we're going to load and draw some sprites in our XNA game. So last time, we talked about the basic concepts about how games in general and XNA games in particular work. This time, we're going to build our first XNA game, and at the end of last lecture I said I hesitate to call it a game, so you should take this in-lecture quiz to tell me why I have that hesitation. I should tell you, based on one of the options in that in-lecture quiz, that I am not a hardcore traditionalist about programming. When you program, you are allowed to drink any flavor of Mountain Dew. It doesn't have to be the original green stuff. Okay, so let's actually start up the IDE. I've already built a project, and we'll get to work loading and drawing sprites. When we create our monogame Windows project, from within Visual Studio, we end up with a folder structure that's automatically built for us. And so later on, you might need to go open your solution again, or you might have downloaded it from the Coursera website. And so how do you actually open it up? Well, when you navigate through the folder structure, you'll end up at a folder that includes a file. I'll expand this so you can see it's Microsoft Visual Studio Solution. That's the file you double click to open up your project. And so you wait patiently while it opens, and we've discussed what happens when you just have this blue screen over here with no code. So let's click on game1.cs because that opens up our game1 file for us. And we'll start off by running this and seeing that it gives us that cornflower blue screen. And we'll keep the blue, but that aspect ratio is just crazy. So let's actually make this build an 800 by 600 game. And we can do that. Remember I said some of our initialization can happen in the constructor. So we're going to change the resolution to 800 by 600 because that's an awesome, amazing resolution for games these days. The way we do it is we access, remember there's this graphics device manager. We didn't really talk about this before, but there's this graphics device manager that is for managing our graphics device. So we will set the graphics. So this is an object reference followed by a dot. Preferred back buffer width. So no parentheses. So object dot something with no parentheses means we're accessing a property. And we'll set the preferred back buffer width to 800. And we'll set the preferred back buffer height to 600. So there's all kinds of sort of underlying details. Just so you know what a back buffer is, basically what happens is stuff gets drawn to the back buffer first, and then it gets slammed to the graphics card to be displayed on the screen all at once. And that actually helps prevent flickering and all kinds of weird things that happen if you don't actually use a back buffer. So we'll run it with F5 and we see now, awesome, we have an 800 by 600 screen. So that's great. The next thing that we want to do is we want to actually declare some fields in this class. These are just variables for loading and drawing a couple of sprites. Let's do 3. Teddy bear drawing support. So we'll start with 1 actually, and we'll add the rest of them. How about? So texture 2D. It turns this light blue color because this is a class. Texture 2D is a class that is provided within the XNA framework and the graphics namespace. And really it's for holding two-dimensional textures, right? Pictures, think of it as pictures, 2D pictures. Now, it turns out that if you read any of the documentation, it talks about texels inside of these things, which for our purposes, we can think of as pixels on the screen. They're called texels because they're textures and we could wrap them around models and do all kinds of weird stuff, but we're not going to do any of those things. Okay, it's not weird stuff, it's logical stuff, just in the 3D world. So we're not going to worry about that. We'll just think of them as a two-dimensional texture or a picture. And so we'll say, let's call this bear 0. Now it turns out when it's time to draw bear 0, we're going to need to provide some additional information for the drawing, where we want it drawn, how big we want it drawn, those kinds of things. So we're going to provide, there's lots of different ways we can do this, but we're going to provide a rectangle in which bear 0 gets drawn. So we'll call this draw rectangle 0. I started at 0, by the way, because programmers start counting at 0. There are lots of really both logical and historical reasons for doing so. So you should just practice and get used to that. That's what we do. We start counting at 0. Okay, so I have declared 2 fields here that I'm going to use for loading and drawing my teddy bear. Now we've reached the point where we need to actually include some content in our project. And we get a content folder by default in our Windows game project, but there's nothing in it at this point. I've provided Appendix B from the Monogame book to you in the selected book chapters link. So Appendix B actually talks about how to use the content pipeline tool for Monogame. Let's take a look at doing that for this particular project. I'm going to add another folder here at the same level as my Visual Studio Solution file, and I'm going to create a new folder, and I'm going to call it first XNA game content. And you could call it anything you wanted. I just find this to be helpful that I include it right here. So if I ever zip up this folder, I've got the content in it. And I like to add content at the end of the folder name because it is in fact content. Next thing we do is we start up the pipeline tool. I of course have a shortcut for that. So I just double click it. And I'm going to say I want a new content project. I will navigate to the place where I want to save that project. And this is the folder I just created. So this is where I'm going to put it. And I can call the project anything I want. But I'm going to call it first XNA game content, because that's what this project is for. At this point, you can see that you can select a variety of different characteristics for this particular pipeline project. I'm going to make sure it's for Windows because I'm building this for Windows. But if you were working on a Mac, for example, you would pick Mac OS X instead. But I'm going to leave it as Windows. And I'm going to leave it the reach profile. If you know you're actually building for a strong graphics card platform, you can set it to high def. But it defaults to reach because reach is the most commonly supported even with low power graphics. I'm going to put an additional folder inside this project. So I'm going to add a new folder and I'm going to call it graphics. As you build games, you will discover that you have a whole bunch of different kinds of content, including fonts and audio and all kinds of stuff. So I like to separate them in separate folders. Not required, just something I like to do. Okay, so now if you come back here, I can see that I have this graphics folder, but there's nothing in it. So now I want to actually add some PNG files to this folder. I'm going to go up where I know I saved them, and I will just cut these and I'll bring them in to that graphics folder. Like so. They're still not included in my project, so now I'm back in the pipeline tool. But if I right click on the graphics folder and say I want to add existing items, it will let me select all three of these. And I'll say open. And we're almost there. I can expand this folder and you can see that they're there. The last thing I need to do is build. So what I'm doing is I'm converting these PNG files into a special format called XNB, which is the format for all of our assets, all of our content using the XNA framework. So I can just say build. And yes, I want to save the project first. And so you wait while it goes through and builds, and as long as they all succeeded, you're all set. So we've used the content pipeline tool to actually build our content into XNB files. And as you can see, there's the XNB files right there in our bin folder near our content project. Now we go back to Visual Studio. And I'm going to also add a graphics folder here in my project in the content folder. So I right click and I say add new folder. And I'm going to call it graphics. And now what I can do is I can right click that graphics folder and I'm going to say add existing item because the XNB files have already been built. I just want to add them to my project. And now I navigate to where I saved those. So it's up one, here's that content folder I built, all the way down to bin, into graphics, And then this is empty, and you say, what's going on? I built some XNBs, and where are they? It's because the file type filter here doesn't include XNB. So if you click the down arrow and you select all files, there they are. I'm going to select them, and I'm actually going to click this arrow next to the add box, and I'm going to say add as link instead. This is how we always did it in our game company, because then if somebody actually changes the assets over in the content folder, next time we build our project, because we added them as links, we're going to get access to the new assets. And that way it's easy to integrate those new assets as the artists and other content builders provide them to us. I'm going to click on the first one, and we can see that it gives us some information down here. We are going to, I'm deliberately making a mistake because you may deliberately make the same mistake, but I have added these as content. We're not quite done, but I'm going to continue with the lecture, and then we'll see a fairly common error that you might run into. I will point out that the asset name, which we'll need when we try to load this content, for this first one is Teddy Bear 0, the second one is Teddy Bear 1, and so on. So the asset name is the name of the file without the file extension. Okay, so we said that we will load all our content here. Let's say we'll load teddy bears and build draw rectangles. Now, loading, we're going to load the texture 2D into Bear 0. And we do that using content with a capital C. And that's what's called a content manager. And the content manager manages content. And so we use content with a capital C. And now we want to access one of the methods in content. And we want the load method. Now this is new, these little less than, greater than signs. We won't worry about the details of it. It's actually something called a generic, which we'll address when we get to lists and so on. But the content manager can load all kinds of content. So we need to tell it between the less than and greater than what kind of content we want it to load. In this particular case, we want it to load a texture 2D. We are calling a method, even though this is a slightly different way of calling a method. So we're going to need parentheses. And you can see from this IntelliSense help that we need to provide the asset name. And so the asset name for Teddy Bear 0 is, in fact, Teddy Bear 0. So this should load our content just fine. Let's run it. And unfortunately, we see that the code has crashed. And here's the problem. It says could not load Teddy Bear 0 asset as a non-content file. And that is the deliberate mistake I made so that I could show you this fairly common mistake that you might make as well. So I'm going to stop the debugging. And I'm going to come back over here to the content. And I'm going to select all the XNB files that I imported. And I'm going to make two changes. Down here in the properties pane, the first thing I'm going to do is I'm going to click in this box that says none. Then I'll click the down arrow and I'm going to say this is content. You should build this as content. Don't just do nothing. The other thing is in the copied to output directory. I'm going to click again in the do not copy side, click the down arrow, and I'll say copy if newer. And that makes sure that this is actually copied into the appropriate location. And now when we build, we see it fails again. We're still working towards our solution. This one was an unplanned error on my part. So the issue is that it's trying to find Teddy Bear 0 in the content folder. But in fact, Teddy Bear 0 is in the graphics folder inside the content folder. So we need to actually include that in the folder path. So it's graphics // is one way we can do this, or we can say at graphics /, which is my preference. So now, and you might be wondering, right, why do we build this if we're just trying to load the content? Well, this actually helps us to discover that we have made some mistakes with our content. Either we have not set them to be content, or we don't have the right folder path to them. So there are a number of different possible errors we could discover just by loading our content. I'll stop debugging. We'll do this one more time with an F5, and we do get the blue screen. So when I got into post-production for this lecture video, I discovered it was a massively huge 22-minute long lecture. And while my students in my actual classroom would kill for me to give such a short lecture, that's way too long for a MOOC course. So I'm going to stop this lecture here, and I've broken it into two parts. So I'll stop it here and then go watch the other lecture to see the continuation to the end. This is the continuation of the previous lecture, so we'll get all the way to actually drawing those teddy bear sprites in this lecture. So let's continue. Okay, so let's actually go down to draw and see if we can draw our teddy bear. So I'll say draw teddy bears with the expectation that later on I'm going to draw all three of them. Okay, so it turns out that the way we do this drawing thing is we have the other field that we get for free, if you will, in our game class is the sprite batch. And the sprite batch is used to draw stuff. So the way we do this is we start or begin the sprite batch by calling its begin method. And if you look carefully at what this is telling us, what this IntelliSense is actually telling us is that all of the parameters or the arguments that we provide when we call the begin method are optional. So in fact, we have control over some of the characteristics of the way the sprite batch works, but we can simply provide no arguments and it will work in the default way. We'll also, after we've drawn all our stuff, we'll do a sprite batch.end. We'll call the end method of the sprite batch so that it ends the sprite batch. And this is a really good time for you to go take an in-lecture quiz so that you can guess, if you have to, when stuff gets drawn. Okay, the answer is when we call sprite batch end. So it's a batch of sprites that all get sort of put into this set of things that should be drawn. And when we call sprite batch end is when we actually draw them. We could override this behavior if we choose to do so in our XNA game, but there's no need for us to do that right now. So I'm going to, for those of you who don't believe me, please believe me, I'm going to deliberately make a mistake here because you may find that you make the same mistake. So I want to draw that first teddy bear. So I call the sprite batch draw method, and it turns out that there are 7 different ways that I can call the sprite batch draw method, but I'm going to take the very first one here. So I start with a texture 2D, and that's bear 0. That's the texture 2D that I had the content manager load for us. I provide a destination rectangle, which I called draw rectangle 0. And I provide a color. So I can in fact tint this if I choose to do so, but I want it to be drawn in its actual original colors from the image, so I'm going to pick white. I will tell you that I had a student who regularly gave me wheat tinted stuff because she got to the WH and hit tab and it was always wheat colored. But white is what you want if you want it drawn in actual color. So at this point, you could reasonably expect that we're going to see something drawn when we run the program. And I press F5 and we don't see anything drawn and we're very sad. But that's what debugging is about. And I was telling my wife earlier today, we were talking about debugging, and I said, well, debugging is like solving a mystery. We gather some information and we form a hypothesis and we try to figure out what's going on. It's very exciting. And you better get excited like that because you'll debug. Okay, so how do we debug? Well, what I'm going to do, watch my cursor way over here. I left clicked in this gray column right here, and I got this red ball. What this red ball is called is a breakpoint. So when I run my code using F5, not Control F5 because that just ignores breakpoints. When I run my code using F5, it's going to execute the program until it gets to this breakpoint, and then it will stop. And so that's good because then I can look at stuff to see if I can figure out what's going on. Okay, so I press F5 and it runs. And then it's got to this breakpoint, and we can tell because it's all highlighted and the red ball has a little yellow arrow inside it. And so now we can look at some things and try to figure out what's going on. So the two possibilities, one much stronger than the other, is that we don't have a sprite loaded, and we're pretty sure we do, but we'll take a look to make sure. Or that our rectangle isn't the way that it should be. And it turns out that the problem is that the rectangle isn't the way it should be. So we look at bear 0, I hover over it, and you can see that there is in fact a texture 2D there. So okay, that's great. It's not null, it got loaded. But when we look at the draw rectangle, look at X, Y, width, and height. So we have this rectangle, and this rectangle is a structure in X and A, and it has an X and a Y location, the upper left corner of the rectangle, and it has a width, how many pixels wide it is, and it has a height, how high is it. So what we're saying is we should draw this sprite inside a rectangle with 0 width and 0 height. And that's a really small rectangle. There are no pixels to be drawn in width and no pixels to be drawn in height. So that's why we're not getting any output, even though we expected it. So go do the in-lecture quiz about the rectangle structure and then come back so we can fix this. Great. So I've taken out the breakpoint and I'm clicking debug, stop debugging. So we need to, up here where we loaded the teddy bear, we need to also build its draw rectangle. So draw rectangle 0. We're going to call a rectangle constructor, just like we've seen as we construct instances of classes. 2 overloads. I don't want to use this one because this just builds me a rectangle with 0, 0, 0, 0, which is not helpful to me. If you click the down arrow, you can see that there's a different one for which we can provide X, Y, width, and height. So let's actually provide X, Y. Let's say we'll put it at 150 in X. We'll put it at 100 in Y. And for now, let's give it a width of a couple hundred and of a height of a couple hundred. So now we've created that rectangle so that when we run this thing, now we get a very scary output with a fat, big, pixelated teddy bear that scares us. So in general, scaling is cool. If you want to like feed teddy bears and they get fat and fat and fat until they explode, which is a fun game. What we might want to do is draw our assets in their original size. And so instead of using 200 and 200 here, if only there were a way, now that we've loaded this bear 0 texture, if only there was a way, given a bear 0 or a texture 2D object, that we could find out that texture 2D's width and height. And of course there is, otherwise I wouldn't have built it up so much. So the bear 0 dot, so object dot access a property, let's access its width, and bear 0 dot access its height. And so now when we F5, it draws that bear in its actual size. So now that we've tested that to make sure that that works, I will add the rest of the teddy bears, copying and pasting, which you'll hear me complain about lots, but we're going to do it right now because we don't know a better way. And you'll notice that I'm getting some errors as I do this, which we'll take care of soon. But basically, I'm changing all this so that it's going to handle all the teddy bears. Now, if I leave all these draw rectangles with the same XY, then they're all going to get drawn in the same place. So it will look like we only have one teddy bear. So let's change these a little bit. We'll just do a row of teddy bears, like so. Now these errors, if I hover over this, it says the name bear1 does not exist in the current context, which really means I don't have a bear1 field. So I'll add those. I'll get it so it can compile and run again. I press F6 to compile. Build succeeded. That's great. We're very excited. It compiled. And I press F5 to run it, and I still only have one teddy bear, so I'm sad again. However, this is an easy fix. I did Control End, by the way, to bang my way all the way down to the end here. It's because we've only told it to draw one of the teddy bears. So let's tell it to draw all three of those teddy bears. Like so. When I run it, we get that row of teddy bears that we hoped for. And you'll notice that I loaded all those teddy bears, or I actually loaded the content for the teddy bear and built the draw rectangles here in the load content method, which is exactly where you'd expect me to do it. So that's really it, right, for today. So let's recap. We've learned about how to do some initial stuff. We initialized by changing the resolution of our game. We loaded content so that we could bring in some texture 2Ds, some sprites for our 2D game. And we did some drawing. And, that way we get to see some output from our game. The sad news is we never used update because our game world never changes, which makes for a very boring game world. The good news is that next lecture we'll actually have a game world that changes over time. This is the last lecture in Module 5, where we've been exploring the basics of XNA and how we use XNA to develop games. Here are the learning objectives that we're finishing up on in this particular lecture, and we're focusing on the third one, where we're going to use a provided class in XNA. So last time we built our first XNA game, but it didn't actually update based on time elapsing in the game world, and so this time we're going to solve that by having a different game, still in quotes, that actually updates as time goes by in our game world. So you should go do an in-lecture quiz to tell me why this one isn't a game either. The class that we're going to use is a custom-built teddy bear class that I wrote for us to use for one of the labs as well as for this lecture. So the teddy bear class has a variety of different things that we're used to seeing from Module 4, where we dealt with classes and objects. There is a constructor, where we can build the teddy bear object, which we're definitely going to need to do. And there are two methods. There's a draw method, because if we're going to use XNA, we're going to want most of the objects, not invisible triggers in our game, but most of the objects to be able to draw themselves. So the teddy bear exposes a draw method, and it exposes an update method, so that in fact we can have the teddy bear update itself as time goes by in the game. So the first thing that we're going to need to do in our game is we're going to actually need to create a teddy bear object, which means we need to understand more how to use the constructor. When we click on that constructor link, though, it brings us to this page, which has two different constructors. Constructors can be overloaded just like other methods can. They have the same name for constructors as the class name, and they have different sets of parameters. And so the compiler knows, based on the arguments we provide when we call the constructor, which constructor we're trying to access. In this particular case, we're going to use this constructor, We'll just let the teddy bears get a random direction and speed. But in the future, we'll probably use the other one to actually have more control over how the teddy bears are moving. We're still not quite to the point where we can actually use the constructor though, because we don't know what each of these parameters is for. So if we clicked on the link for that top constructor, we end up here where we finally get sufficient information about the information we need to provide to the constructor to actually build the object. So we need to pass in a content manager, and this is the same content manager, that content with a capital C, that we used in our previous game. Same content manager for our game. We're going to pass in a sprite name because we're actually going to have 3 different teddy bear sprites, and we'd like to be able to control which sprite this particular teddy bear object uses. We're going to pass in a location, X and Y, for the center of the teddy bear. And the last 2 things we're going to pass in are window width and window height. And the reason we need to pass those in is because the teddy bear actually is going to bounce around inside the window. And so the teddy bear needs to know how big that window is so it can bounce around appropriately. Let's actually go to my desktop now. As you can see, I've already built the project for this moving teddy bears solution. I've also used the pipeline tool to build my content. I have graphics of 3 teddy bears, and I've already built those into XNB files. The other thing that I have is within the moving teddy bears folder, I have the teddybear.cs file that I'm going to need for my project. So let's actually start up the Visual Studio project. And as you can see, this is just our template project. So let's add our content. I'm going to create that new graphics folder that I like to use for graphics assets. And I'll right click. We'll add existing items. We'll navigate to the place where we stored those XNB files. Remember, we need to change the filter to show all files. I'll select all 3 and add as link. Remember also that I need to change these so that the build action is content and the copy to output directory is copy if newer. So we're almost all the way there. I'll Control S to save. But we still don't have the teddybear.cs file as part of our project. It's in the folder, but it's not in our solution yet. So I go up here and I'll right click and I will add an existing item. And now I'll have to navigate to where that teddybear.cs file is, and there it is. So I'll double click that one. I didn't add it as a link, I just added it as an actual item instead of the link. So if we look at that teddy bear class, I could expand these things and we could look at the internals, but we're not actually going to need the internals. We're just going to use the documentation to actually use the teddy bear class. So let's go to game 1. And I'm going to do something slightly different here. I'm going to actually declare 2 constants for the window width and the window height. And the reason I'm doing that is because we're actually going to use those values in multiple places. And it's easier to just declare them as constants so that if we decide to change the resolution, we can just change it in one place and it works fine throughout our game. That's the power of using constants. So again, we'll set resolution to 800 by 600. And remember, that's by doing the graphics preferred back buffer width. This time, instead of hard coding 800, we use window width. And the same for the height. I'm actually going to, in addition to these constants, I'm going to need variables or fields in the class for the 3 teddy bear objects. But this time they're not texture 2Ds and draw rectangles. They're sort of first class objects. They're teddy bears. And we'll start with one and then add to the others as we figure out how it all works. Okay, so now I'm going to go to load content. And I'm going to say here that I'm going to create the teddy bears, plural, because eventually I'm going to do that. So bear 0, The reason wow, I'm horrible typing today. var0, the reason we looked up the constructor documentation was so that we could call the constructor appropriately. So I'm going to call it new teddy bear. The first thing I have to pass is the content manager. That's the capital C content. I need to pass a sprite name. Let's make this one teddy bear 0 for the sprite. I need to pass an X and a Y, and I'll just make it 100, 100. And here's why it's useful for us to, in fact, have the window width and window height as constants, because then I can just use window width and window height here, like so. Okay, so I've created the teddy bear. I'm going to F5 to run it. We got our standard cornflower blue screen, but it's 800 by 600, and the teddy bear actually loaded its own content. So it's possible to create the object and then have to call a load content method on that object, but we don't really want to do that. Once we've constructed an object in our game, we want that object to be ready to go. We want to be able to draw it and update it. So we're not going to generally expose a load content method for the objects that we're creating. So you should go do an in-lecture quiz to tell me about, to make sure that you were paying attention to why I just said we don't have a separate load content method in the teddy bear class. Okay, the next thing that we're going to do is we're going to use the draw method. And as a reminder, it's actually kind of nice to implement the draw method first before we implement the update method, because we get that instant feedback of actually getting to see something drawn to the window. And that's nice. As we're developing games, it's nice to see actual visible progress. So we're going to do the draw method, but before we do, I clicked on the draw documentation so that we could look at it here, and we see that we just call it with one argument. There's a parameter on this end, and that parameter is a sprite batch. So when we call the draw method on our teddy bear object, we're going to have to pass a sprite batch as the argument. So I will try to get some mouse control, and I will say draw teddy bears, like so. And of course, we still need the sprite batch begin and end like we had before. We're always going to have at least one sprite batch begin and end in our draw method. So we'll do that. But inside here, we will just tell teddy bear 0 to draw itself. And we pass the sprite batch as an argument. So this is different from the way we did it before, right? Before we passed in, we directly called the sprite batch draw method, and we handed in a texture 2D and a draw rectangle and a color. This time, because that behavior is encapsulated inside the teddy bear object, we actually just tell the teddy bear to draw itself, and it goes off and does that. So when we press F5, we see that in fact, we get a teddy bear drawn on the screen. Now the teddy bear is not moving. And the reason for that, of course, is we've just said to draw the teddy bear. We have not said to update the teddy bear's location in the game world. So if we want to do that, we have to go to the update method here in XNA, and we need to update the teddy bears. Well, that's a very nice comment, but we don't actually know how to update the teddy bears or how to tell the teddy bears to update themselves unless we go read the documentation. And so if we look at the documentation here, we can see this is a really straightforward method. This is a method that doesn't return anything and doesn't have any arguments, so we're just going to call update. I will say that the internal implementation of this teddy bear just moves it a certain amount every time update is called. Later on in the course, we will do more physics-based movement where we'll in fact do the distance moved between updates is based on the velocity and the elapsed time, which is a much more physics-based approach. This time we're just going to say every update move 5 pixels or whatever. So at this point, we only have one teddy bear, and we'll tell it to update itself, and it does. And when we press F5, we see that now the teddy bear actually moves around in the game window. Well, that's all very exciting, but I want to have 3 teddy bears. So I'm going to add the other 2. So we have to do a number of things. We have to declare the fields or variables for them. We need to create them here. And so I'm going to do multiple things. I'm going to change the names here in a reasonable way. I'm going to use different sprites for each of them. So I'm going to use teddy bear 0, 1, and 2 for the 3 different teddy bears, and I'm not going to start them in the same place. I will start them at 200 and 300 or something like that. Now, I've created them, and you might be like, oh, good, I'm all done, and then you run it, and there's only one, and you're sad, because this is the manic depressive process we go through when we program. And you say, oh, it's not drawing them. So you come down here and you say, well, I better draw bear 1 and bear 2 also, or more precisely, tell bear 1 to draw itself and tell bear 2 to draw itself. And then you press F5 and you're still excited, except only one of the teddy bears is moving. And you say WTF, which means what is going on here? And you go up here and you say, that's not what WTF really stands for. It stands for what the heck. So bear 1 update and bear 2 update. And finally, we see we get teddy bears bouncing around. Now, you might have noticed, I'm going to run it again just to show you that in fact we get different velocities. They're going in a different direction. But all 3 teddy bears actually have the same direction and speed. And that is a side effect of us calling the random number generator really quickly in succession. The book talks about this a little bit, but basically what happens is that random number generator goes and reads the system clock. It says, hey, it's, time 3, let's pretend. And so it generates random numbers, and then the next time we call it for the next bear, because computers are screamingly fast, it says, oh, it's time 3, so it uses the same exact seed for generating the random numbers for all 3, essentially, and that's why they all have the same velocity. We regularly solve this problem by using a single random number generator across the entire game instead of creating a new one every time, but for this example, that wasn't the point of the example, so that's what we did here. And that is it for actually building an XNA game using an existing class or a custom class that I built for letting us actually do this. So to recap, we have now done an XNA game that actually does change as time elapses in the game world. So we used the update method. So now we've seen a couple of examples where we used XNA to initialize, load content, draw, and in this particular case, update as well. So that is the end of Module 5. Next time, we're going to move on to talking about strings, a new data type that we haven't really discussed in any detail, even though that we've been using them in our console.writeline and so on. Well, here we are in Module 6, where we're going to learn about strings. And here are the Module 6 learning objectives. We're going to move back away from game development for a little while to cover some more core programming topics, but don't worry, we'll get back to it soon. So in this module, we're going to be looking at an incredibly useful data type called string. And so the core idea is that strings are sequences of characters, those Unicode characters that we actually talked about before. So let's just jump right in and start using strings. I have already built a small project, a console application, that we're going to use to explore some of the fundamental ideas behind strings. So one of the things that strings are really useful for is getting user input and processing that user input in some way. So that's what we'll be doing today, is we'll be getting input from the user and processing it. So let's actually prompt for and read in gamertag, print out values and that extra line that I always like to add. So, to prompt for and read in the gamertag, the first thing is the prompt. We're going to ask the user to input something. And the way we'll do that is we'll do console.write. Now you'll notice that I didn't do WriteLine here, because when we prompt users for input, it's much nicer for them to be able to enter that input right after the prompt instead of on the line following the prompt. So all the prompts you ever do in console apps should use write, not WriteLine. I'm going to say enter gamertag. Now you'll also notice that I haven't been polite at all. You'd think I'd say please enter gamertag because I'm asking them for a favor to provide input to my program. However, what happens is all your prompts end up having to start with please if you go down this road, and that's really actually far more irritating than you might think. So this will be your opportunity to be impolite in your prompts. Go ahead and just prompt away without any pleases or thank yous or any of that stuff. Okay, so we've done the prompt. We've displayed this prompt, and what the heck? Let's actually Control F5 for console apps. Let's Control F5 to see what happens. Okay, it prints the prompt, but it doesn't actually give us that blank line yet. It's because it left the cursor right here, and then the right line moved it here, and then we get the press any key. So we'll get to the point, don't worry, where we have that blank line, but it does print out the prompt properly. So now we want to read in the gamertag, and the gamertag is a sequence of characters. So we want to take this gamertag and we wanted to put it into a string variable. Now, you might have noticed I didn't say, string is a class. String is a reference type. It's not a value type. That's why we haven't covered it, why we didn't cover it way back in the value types. But this format of a lowercase and it turns it bright blue for a keyword instead of light blue for a class is because strings are so commonly used that we get sort of two ways to think about them. This and this, string the class, string the data type, they're the same exact thing. So I tend to use lowercase string when I'm using it as a data type, and uppercase string when I'm accessing properties of the string or methods of the string class. But it's either personal preference or it's, coding standards you have to follow in your game company or whatever. So string, I have a string. I'll call it gamertag because it's going to store the gamertag. So let's use a good variable name for it. Now, we've seen this use of console before. We've used console.write. We've used console.writeLine. Here, we can use console.readLine to actually read in a line from the user. So it will read in whatever keys they type up until they press enter, and then it returns the resulting string to us. So you should go do an in-lecture quiz to demonstrate to me that you understand that idea. So we've done that. Now that we've read in this value, let's actually print it out. So console.writeLine. This isn't a prompt, it's output, so we'll just do WriteLine. We'll say that we're printing out the gamer tag. I might as well capitalize that. And then concatenate the actual gamer tag to it. So now when I Control F5, it asks me for the gamer tab. Here's my gamer tag. It's an awesome one. It prints out that gamer tag, and then I get the press any key to continue. So we've now used console.readLine to read in a string. We haven't done any processing to it, but we've read it in, and we printed it out. The next thing will be a little more interesting. So let's prompt for and read in their level. Whatever that means and whatever genre of game we're building here as a console application. So let's console.write. Here's the prompt. And I'll say enter a level. And now we have a problem, because a level should be an integer. There are no level 83.7 paladins, so, or mages, depending on your game, right? So we want to put this into an int. But if I say int level equal console.readline, we have a real problem. And the real problem that we have is that we're getting this compilation error that I will F6 to show you. And it says we can't implicitly convert from a string to an integer, which makes sense, right? We've talked about data types, we've talked about type conversions and typecasting, and there's no way that the compiler can figure out that a string is an integer, because a string's a bunch of characters. An integer is a bunch of bits that represent a number. So we need to turn this string into an integer. And you might think, based on our conversation about typecasting, that we could just do this, but we can't. We cannot do a straight typecast, so we're going to have to do something else. And the something else we're going to do is we're going to take advantage of the fact that the int data type, in fact, even though we've called it a value type and we use it as a value type, it actually has hidden behind the scenes, if you will, a reference type as well. And that reference type exposes a method called parse. Now, the term parse comes from compiler stuff, but basically what this parse means is take the string of characters and turn it into its representation as an integer. And that's probably good enough for now. Compilers, total side topic. Building a compiler in a compiler class is probably one of the most useful things you will end up doing as a programmer, because there are so many ideas that apply throughout computer science and programming in particular. But we're not going to build a compiler today. We're just going to parse this input string into an integer. And then we'll print it out. So console.writeLine level like so. So I'm going to control F5, so it asks for the gamer tag and it asks for the level 30. Noob. And there we go. It prints that stuff out. So printing this stuff out, I'm starting to get irritated that there's no space between the input and the output. So I'll add an extra line here. But I will also point out that that int parse thing makes an assumption about the user. And the assumption it makes about the user is that the user is not an idiot. So in fact, if I run this and I enter a gamer tag and it has level and I say Bob, bad news, crash, horrible thing, close the program, should we debug it? No. Go online? No. There is no online solution for the user being a moron. I'm sorry, that should, unfortunately, searching the web won't solve this problem, right? So a user who does not enter an integer when we're expecting an integer, given what we know now, can crash our program. So you should go do an in-lecture quiz about users and their behavior, and then come back. Okay. By the way, there are ways, of course, to keep the program from crashing. We just don't know those ways yet. And we won't learn them in this course. We'll learn some data validation stuff, but not that particular one. But as you explore C# programming more, you'll learn about something called exceptions, and we can actually handle the exception where the user is a moron and doesn't enter an integer when we asked for one. So let's actually do one more thing though. Let's extract the first character of the gamer tag. This might be useful if in fact we, had a friends list and we wanted to sort it into all the gamer tags of your friends that start with G or J or whatever. And so this could be a useful thing. And we're going to actually use Well, we know a string is a sequence of characters, so when we extract one, we'll put it into a character variable. First character. Actually, let's make that an even better variable name. It's the first gamertag character. And so it feels like, and there is, it feels like there should be a way that we can extract from the gamertag a character at a particular location. And there is. We use these square brackets, and between the square brackets, we enter the index of the location in the sequence of the character we want to extract. And so ignore everything you ever learned about counting. The first character is at location 0, because programmers start counting at 0, by gosh, and that's where the first character is. So we can extract a character using these square brackets from the bad English sentence. From the sequence of characters that are this string, we can extract a character using these square brackets. And let's print that out as well, just to show that we've done that properly. But before I finish typing this and we run it, go to the in-lecture quiz about extracting characters from strings. Okay, so first gamertag character is this. I control F5. That started with F. Pay attention to that. I'm level 1. And so the first gamertag character is in fact F, just as we expected. Okay, so that's it for our programming for today. I'll Control S to save all that stuff. Before I finish, I want you to go do one more in-lecture quiz. But before you do, I want to say that strings are what's called immutable. So go take the in-lecture quiz to see if you know what that means. Okay, immutable actually means that once we have a string object, we can't change it. We can form new strings from it, and we can extract characters from it, and we can parse it into integers, and we can do all kinds of other stuff. But once we've made a string object, it can never be changed. It can't be mutated. It is immutable. Okay, so to recap for today, strings are sequences of characters. They're really useful for getting and processing user input, and strings are immutable. Next time, we'll take a look at doing some other useful things with strings. Last time, we talked about the string data type, and just as a reminder, a string is simply a sequence of Unicode characters. This time, we're going to look at a couple of more interesting processing things that we can do with strings. As a reminder, here are the module learning objectives for Module 6, and we're really working on the second one in this case, where we're taking a look at string processing. So you might ask yourself, what might we want to actually do with strings? We've already seen how we can read them in using console.readline. We've already seen that we can convert them to a value type. We did that last time. We might need to look for a particular character in the string. So for example, it is very common for people to export CSV files, comma separated value files from Excel or something like that. You could also separate them by tabs. You can use any separator character you want when you export. So it might be the case though that we want to write a program that reads in such a file and finds the location of those separators so that we can do interesting stuff. So we might have to find a particular character. And in fact, once we've found that particular character, we might want to extract part of that string into a new string to sort of gather the information from each line in that CSV file. And we might do something else. And that's so vague, right? What something else? Whatever you discover you need to do with strings. And the way we move forward as programmers in programming in general and game development in particular is we can't learn everything as beginners. We learn what we need, and then as we need to learn new stuff, we learn it. And so you may discover lots of things you want to do with strings, and when the time comes, you'll look at the documentation and you'll try to figure it out. Okay, so let's actually start with an in-lecture quiz where I ask you how we can do that, find a particular character in the string, and then we'll actually go do some code to do it. I will open up the project that I already created, and we'll say read in CSV string. Prompts, remember, are console.write with no politeness whatsoever. Enter name. Well, okay, we can't use worty. It has to be right. Enter name and percent. So imagine this is for a class or something like that. And it makes, if we're expecting a particular format from the user, even though we know users are going to mess with us no matter what, we should tell them the format. So let's say name, comma, percent, like that. So there's our prompt, and we'll read in the CSV string using console readline. Now, once we have a comma-separated string, we can extract values from that string, and the first thing we're going to do is find out where the comma is. So find comma location. And we can do that. Let me just declare a variable here. We can do that by using, hopefully you got this right on the in-lecture quiz, we can use that, do that using the index of method. So all we have to do is say CSV string dot index of, and we'll look for the comma without any extra parentheses, hopefully. Okay, and by the way, I did this as a string, but we can of course look for a single character as well by using single quotes around the literal rather than double quotes around the literal. So let's actually use the debugger to explore a little bit more how index of works by setting a breakpoint, and I'll run it. And first I'll enter something like my last name or name, Bob, comma, and my percent, I'm stupid, so we'll say 0. Think for a moment about what you think index of will return. And then we can look at comma location, and it's 3. So remember, we start at 0. Character 0 is B, character 1 is O, character 2 is B, and the comma is at location 3. The other thing we can do, I'll press F5 and that will just finish the program for me. I'm going to, and notice by the way, that because I'm using the debugger in this particular case, I'm actually using F5 in this console application instead of Control F5. That's why I said when I said go all the way to the end, it actually just flashed that screen. Okay, I'm going to do it one more time, and I'm going to enter something without any comma at all. And when we get to the breakpoint, the comma location is -1. So if index of finds what we're looking for, it returns the location of the first occurrence of what we're looking for. So if we'd had multiple commas in our string, it wouldn't matter. It still would give us the location of the first one. The other thing that happens is if what we're looking for does not appear in the string, then it just tells us, well, it returns -1. Okay, so now we know where I'm going to get rid of the breakpoint, and I'll F5 to finish off. So now we've found the location. Let's extract name and percent. We'll also print name and percent, and then of course that blank line that we know and love. Okay, before we extract what we need to extract, go do the in-lecture quiz to tell me if you have a good guess about that. All right, so we actually extract using substring. And the substring takes a piece of the string we're extracting from and puts it into a new string. Remember, strings are immutable, so we can't modify the string we have, but we can create new strings from it. So I'll say string name is equal to, and now we need to use substring on our CSV string to extract a piece of the string. Now we've talked about overloads. Substring has two overloads. One, we give it the start index, and it goes all the way to the end. It starts at whatever we've provided as that start index. Remember, the thing between those square brackets when we accessed a single character in the sequence of characters that are the string is called an index. So we can give it the index, and it'll go all the way to the end of the string, but that's definitely not what we want here. What we want here is we want to start at the beginning of the string and go up to the comma. So we're going to use the other overload. We're going to use the overload where we provide a start index and a length. So the start index is 0 because we want to start extracting the name from the beginning of the string. And the question is how long? How many characters do we need to grab? And it turns out that having 0-based strings and having index of work the way it does is awesome because the length is actually comma location. We want to extract 3 characters, the B, the O, and the B, from the example that I used. So I'm going to print this one to show that we've extracted that properly before we move on. So the name is that. We will control F5 now because I'm not debugging anymore. I'll still do Bob. I'll do 10 now because Bob's getting smarter over time. And the name is Bob. So it extracted it properly using substring. The next thing we want to do is let's extract that percent. Now you might be tempted to say string percent because I know I'm doing string processing, but that would be wrong. It would be wrong morally. You're a bad person. Don't do that. So in fact, percent is a float. So let's store percent as a float. We'll do CSV string, substring. And this time we actually want that first overload where we start at a particular place and go to the end of the string. And that particular place is not comma location. It's comma location +1. And you might find that you need to actually use those archaic things, pencil and paper, and write down a string and look at it and number all of the characters starting at 0 and see why it needs to be comma location +1. You should check that out. However, I am getting a compilation error here and I can't implicitly convert string to float. You should say, wow, I remember seeing that last time. Because if I want to convert a string to a numeric data type, then I need to parse it. And this time it's not an int, it's a float. But that's okay. We'll just do float parse instead of int parse. And we'll print it out again. Well, not again. We'll print this out for the very first time. But we will print out the percent as well, just to demonstrate that we have in fact extracted it properly. Like so. And so control F5, I'll enter Bob, comma, and this time I'll do 20.0 because Bob realizes a percent should be a float as well. And it prints out Bob and 20, and we're in good shape. Okay, so here's the thing. We have, and that's really it. That's the exploration of the string processing that we're going to do for today. Index of, there's a corresponding method called last index of, and substring are 3 methods that you are likely to use to process strings regularly to do the stuff you need. When you discover there's something else you need to do to strings, you go read the string documentation. Each method tells what it does, and you find the one that will work for you. So that's it for our string module, module 6. So next time, in the next lecture, we will move on to module 7, where we'll start talking about how we can make decisions in our programs. Well, we're moving on to the next module, where we're going to learn how we can make decisions in our programs. Here are the learning objectives for the module. So, I said we're going to learn about how we can make decisions in our programs. So what kind of decisions do we need to make? What does our program have to decide to do? So, here are some examples. We might decide, based on the user input, which direction we should move the player's avatar. So for example, if they're using WASD, then you want to move up with W and left with A and so on. So movement based on user input is one of the things we decide about. Another thing we decide about is when a collision has occurred. So we actually do some form of test to determine that a collision has happened. That's the detection part. So collision detection uses what's called selection, decision making, in our program. So let me back up for a moment and say the control structure we're talking about here is the selection control structure. That's what it's called because we're selecting between multiple courses of action in our program. Okay, so we use the selection control structure to detect collisions, and also we use it to resolve collisions. So the resolution of a collision may be based on a variety of different factors. Are we wearing enough armor that the rocket-propelled grenade bounces off when the collision occurs? Or do we not have that level of protection so that something else happens when that collision occurs? Okay, players do stuff in games, right? That's why they're fun to play. And based on the player's performance, say whether they're playing a mini game and they have to have a sort of minimal bar of performance, we can use selection to decide whether they get loot or not. So we might need to decide that. Players navigate menus in most games, and so based on their selection of which menu they want to go to, we might do that as well. By the way, menus, people do not get at all excited about writing menus, and virtually every single game you'll ever play has them. So it's one of the things that you'll end up doing as a game developer that is not nearly as exciting as some of the other things you do. You can actually build some really interesting menu systems if you choose to do so, but you're going to have to build them, just like tutorials, which has nothing to do with the selection control structure, but tutorials are another thing that people tend not to get too excited about, but everyone builds into their games. And lots more. There's lots more stuff that you might need to do in terms of deciding how your game performs. So you should go take an in-lecture quiz so that you can tell me about the statement we're going to look at today for doing that decision making. Okay, so this is a graphical representation of the if statement, and this graphical representation is what's called a control flow graph because it graphs how the control flows through the program. Looks something like a flow chart for those of you who have heard of such things. We don't tend to use these things as design mechanisms anymore, but we do use them to help visualize what the program will do. And so let's pretend, because we're going to do it soon, let's pretend that we're going to ask the player for some input. We're going to ask them a yes or no question. And if they answer yes, we want to print an appropriate yes message. And so this is sort of a picture of how that flow through the program would work. We'll ask them the question, and then we'll check their response. Let's put it in a variable called answer. And we'll check their response to see if it's equal to Y for yes. And if it is, we'll print that message. And if it's not, we won't. So those things, those edges, if you will, that come out of that top node are called branches. And so you should take an in-lecture quiz to tell me about what you understand about branches. And now you should go do another in-lecture quiz to tell me what you know about that answer equal yes part that we labeled the node with. So that expression, the answer equal yes, is called a Boolean expression. Remember, our Boolean variables can have values of true or false, and a Boolean expression is merely an expression that evaluates to true or false. And we use that result, the value it evaluates to decide whether or not we should do the thing, the branch, on the true side. Let's fire up the IDE. I already have a template built. You notice I remembered to zoom in this time. So we're going to look at some forms of the if statement. And so the first thing we're going to do is ask for and get an input from the user to a yes or no question. So we know how to ask for, we do a prompt. And let's give them something interesting to answer about. Pick up the shiny thing. And we'll tell them. They should tell us either yes or no. So there's our prompt. And then we're going to read this in. Now, this is a single character we're trying to read in. So let's call it answer. And I've declared it to be the char data type. And of course, I try to do a console.readline. And I get a compilation error that says I can't implicitly convert a string to a char. I've specifically chosen to put this into a char for two reasons. First of all, a character is the right choice, right? They're picking something with a single character, so we should in fact store it in a single character variable. The other reason I've decided to do it this way is because I wanted to show you that at this point, after this call to console.readline, we know we're holding a string of characters. A string, in fact, a string object. And we also know that we can access particular characters in that string by indexing using the square brackets. So I wanted to show you that we can take this call to the method and then add at the end square bracket 0 square bracket, and that will take that string object that the method returns and index into it to extract the 0th character in the string. So now we're holding the answer. Let's add that extra blank line that I like so much. And let's run it now before we actually add the if statement to make sure that's working properly. Pick up the shiny thing, yes or no. You'll notice that I can type a whole big long thing here, and it's just going to extract the D from the very beginning. We'll learn later that there are other ways that we could take care of this, but for now we're going to focus on the if statement, so we're going to let that happen. And that's the read line. Press any key to continue, so I have. So let's print an appropriate message. Let's print a message for the yes. So this looks much like the control flow graph, where I'll put a Boolean expression between the parentheses here. So if in fact the character the first character of the string they enter is in fact a lowercase y, then we'll print something. You have the shiny object. So now let's test our code. So we're going to try it with, we want to go down the true branch. So we'll make sure we enter a lowercase y. And we want to go down the false branch from that picture, which won't print any message at all at this point. Okay, so let's run it. And I'll just enter y. And I get the you have the shiny object. I'll run it again and enter anything other than y, like h. And I don't get that message, so that was the false branch. The only thing you might notice is that if I run this and I enter a capital Y instead of a lowercase y, because I've got caps lock on, because cruise control for cool, oh, I don't get a message, and it feels like I should. Right? So there are a variety of ways that we can do this. We can make sure that by the time we get to the if statement, we've capitalized or lowercased whatever character they entered. But I'd rather actually build a more complicated Boolean expression here to show you how that works. So we're checking if answer equals lowercase y here. And we learned that we have this OR Boolean operator. So we can check if it's lowercase y or uppercase y. And so that way, when I control F5, we'll try all three again. Y still works the way it should have. H still works the way it should have. But now when I enter a capital Y, I get that message again. So we've looked at the first form or variant of an if statement where we just have the if clause or the if block, this part right here. And we've built a not really complicated, but more complicated than just testing one thing, Boolean expression. So let's go back to the slides and look at another form where, in fact, if they say no, we can do something else. So at this point, we have both a print yes message along the true branch and a print no message along the false branch. So this is a pictorial representation of an if statement that has an else clause in it. So now we add the code for that. And we add the code by saying else and we'll write now, whoops, sorry, something really compelling, you don't have the shiny object. So now we have an if statement that will do this part if the Boolean expression evaluates to true. And if the Boolean expression evaluates to false, it will go do this part. So when we control F5, I'll test Y again. And I'll test N. Oh good, that's what it should have done. However, you might also realize that if we enter H, we still get you don't have the shiny object. And that may be acceptable for what we're writing right now. However, let's actually we're tired. We're tired of the user being a dork. And so we want to be a little abusive if they don't pick yes or no. Other than being mean to the player, there's a good reason for this because it lets me show you one more piece of the if statement. So let's actually say that we want the else to be something mean. You are a noob. And here we want to print the no message. What we can do is we can add an else if, and I will check both lowercase n and uppercase n, like so. And here's where we'll write, you don't have the shiny object. So, thinking about how this will work, what happens is when we're running this code, we get to this point right here. And we check the Boolean expression. If this Boolean expression evaluates to true, it will print this line, and then it goes all the way down here. So it goes all the way past this very last curly brace. If this evaluates to false, it goes down and checks this one. And if this one evaluates to true, it does this, and then comes all the way past the whole if statement. If neither this nor this evaluated to true, it'll come to the else and tell the user they are a noob. Let's try it. I pressed F5 and I crashed it because I just hit enter because the user is in fact a moron. So let me do Control F5. We'll check yes. Yes works fine. We'll check both lowercase n. Oh dear. It says we're a noob. So now we have this debugging thing, right? We have to go look at that Boolean expression and say, what's going wrong? And if we look at this Boolean expression, we can see that in my frenzy of typing, I said for this Boolean expression, if the answer is this is an and, not an or, I said if the answer is both lowercase n and uppercase n. And that is, in fact, impossible. So this should have been an or. See, even in a well-polished, well-prepared lecture, there can be mistakes, just like programming happens in general. That's why we're testing it. Okay, so I'll try the lowercase n. You don't have the shiny object. I'll try the uppercase n. You don't have the shiny object. And finally, I'll try my favorite not search for something. I'll try my favorite H. And I am, in fact, a noob. So that's it for the sort of different variants of the if statement. We looked at 3 different ways we can use this. We looked at an if that just has a true branch and nothing on the false branch. We looked at the if else, which has both true and false branches. And then we looked at adding else ifs as well, in case we have a more complicated sequence of Boolean expressions that we want to test. You should know once we start adding else ifs, we can add as many else ifs if we want, as we want, and the else part is in fact optional. We can just have if, else if, and that's it. And it will behave exactly as you'd expect. Next time, we're going to look, so that's it for today. Next time, we're going to look at another statement in C# that we can use to make decisions in our programs. In this lecture, we're continuing our discussion of the selection control structure. Here are the module learning objectives for the module. Last time, we talked about the different variations of the if statement we could use to make decisions in our program. This time we're going to look at another C# statement we can use to implement the selection control structure in C#. And that statement is called the switch statement. So now you should go do an in-lecture quiz to see if you paid attention to my previous sentence. I have already built a project that demonstrates the switch statement, although it doesn't really do any of the demonstration stuff yet. If I control F5, do you want the shiny thing? Yes, no, H, whatever. Press any key. So this is exactly as before. This is exactly as before. This is the part that we're going to do slightly differently. So the new statement we're looking at is the switch statement. And the way the switch statement works is we type the word switch, which is a keyword. And then in parentheses, we put the name of the variable or an expression if we choose to that we want to switch on, basically, that we want to evaluate its value and take appropriate action. So before we had answer as a key portion of our Boolean expressions, and it turns out that answer is exactly the variable that we want to switch on here. The syntax is a little different, well, maybe a lot different from the if statement. So for the different values that the answer variable can have, we add cases. So we have case, lowercase y. I'm going to compare this to y, and I'm going to print that message that we used before that I probably won't remember verbatim, but will remember close enough. You have the shiny thing. Now, it feels like we should be all the way done here, but we're not quite, because as you can see, we're getting an error message. And that error message says we can't fall through from this case to other cases. Other programming languages let you do that, and sometimes that's really useful, and other times it leads to horrible bugs that take hours and hours to find. So C# doesn't let us do it. So at the end of every case we do, we're going to type the word break. When we do that, that compilation error goes away. And now we have a form that will behave exactly like our first if statement worked last time. When I control F5, if I say lowercase yes, I have the shiny thing. If I say H, nothing. And sadly, if I say uppercase Y, I still get nothing. So it turns out that we can list multiple cases, multiple values for the answer variable in this particular case, that will do this stuff here. And so if I just stack these values like this, then I can check both answer being lowercase y and answer being uppercase y, and it will do this in both cases. Let's check it to see. Lowercase y still works the way we expected. Now uppercase y also gives us the shiny thing. And finally, we'll check that H, nothing. So we can do the same thing for no, where we don't have the shiny thing. And I pressed F5 by mistake, so it flashes right away. Let's try that again. Lowercase n, don't have the shiny thing. Uppercase N, don't have the shiny thing. Still showing you that Y works in both cases. And of course, H still doesn't give us anything. Now, so this sort of works in a similar way to the if, else thing, where it figures out which of these things matches, if you will, and does the appropriate stuff inside. I'll point out that I cannot down here decide, oh, I want to do another thing with lowercase y, because that has already been included. We've already used that value in a case, so we can't use it again. You might wonder, though, how we can go about doing that "you're a noob" message, because we sure don't want to have to say case A, case uppercase A, case B, all the other possible characters that are not Y or N. What we really want is something that corresponds to the else in our if statement. And luckily, we get such a thing in the switch statement. We type the word default, which really means if none of these other things match, then do this instead. And here's where we can do our noob message. And we're still going to have to add a break, because we add a break at the end of every clause we include in a switch statement. And now when I control F5, I'll still check Y. I'll still check N. And I'll try H, where I get my noob message. So, you might wonder why we care. If we already have this if, else structure, why would we want a switch statement instead? And it turns out that I covered it here because it's sort of the other statement we use for selection in C#. We find it to be most useful in our game development when we're using something called an enumeration. An enumeration is basically a data type that has specific values. Don't worry, we'll look at enumerations and see how they all work, so no worries that we haven't talked about it yet. But we'll discover that when we're using an enumeration, we find that switch statements tend to seem a little more intuitive as we implement them. I'm going to have you, if you do the optional lab, I'm going to have you do some practice with both if statements and switch statements, because they're both useful tools for selection, and you'll pick the most appropriate one as you continue on with your programming. So next time, we will start talking about, we've talked about two different C# statements. Next time we'll show using selection in actual game situations. This is our last lecture for Module 7, where we've been talking about the selection control structure. Here are the learning objectives for the module. So over the last two lectures, we've talked about the different variants of if statements and about switch statements, and how we use those to implement the selection control structure, how we make decisions in our program. In this lecture, we're actually going to look in detail at how selection works when we actually implement games. So I'm going to start up a project that I've already built to demonstrate this. We won't be building code today. We'll be looking at code that I've already created. So when I F5, we see that we have teddy bears moving outward and then bouncing off the walls. So let's immediately go to an in-lecture quiz where you tell me about how you feel about bouncing off walls. If we look at, now this is not a screenshot of what you just saw, this is a screenshot using slightly different sprites that show the draw rectangles around these teddy bears as well. So if we think about what it means to bounce off the walls and how we might do it, one way we could think about it is if in fact this guy comes all the way over here and the edge of his draw rectangle goes outside the edge of the window, whoops, sorry about that, goes outside the edge of the window, then in fact we should bounce him, right? He's leaving the game world. Same with this one, except that this is the edge we'd worry about, and of course he might bounce back and forth and so on. So the big idea behind how we can do this is we can check the draw rectangle for each of the sprites and see if they're outside of the window. Now let's go back to the code. When we talked about the teddy bear class last time, sorry, not last time, when we were doing a more XNA practice, we had to hand in the window width and window height to the teddy bear when we constructed it. And we did that and we saved it into these fields here. So let's look at how one of the bounces work. We'll do left, right, because that's the one that, that we just saw. And I'll zoom in and we'll look at bounce left, right. So this is the method that actually bounces the teddy bear. So let's see how it actually works. Here's an if, else if. Remember we said if we have else ifs, we don't necessarily have to have else's. They're optional. But if the draw rectangle.x, so that's the upper left-hand corner of the draw rectangle, if that is less than 0, that means that the draw rectangle is at least partially outside the left-hand side of the window. And what a horrible comment. Let's add an E there. So we're going to bounce off the left side of the window. We will immediately do this. Remember, draw rectangle is a rectangle structure which exposes an X property that we can set. So we set it to 0. If the teddy bear has gone off the left-hand side, we immediately bring it exactly to the left-hand side. Velocity in the X direction, we're going to multiply by, whoops, let me not do that. We're going to multiply by -1. So in other words, if the X velocity was negative when it went outside on the left, and we actually know it was negative when it went outside on the left because it was moving to the left, we then multiply by -1. So now we've turned the velocity into a positive component in the X direction. So now the teddy bear is at the very left edge of the window and has started moving to the right, which is exactly how we bounce it. We have this else if because the teddy bear could also be going out the right-hand side of the screen. Here it gets a little more complicated. This code says drawRectangle.x plus drawRectangle.width, which is an intuitive way to think about it. right? So the left-hand side, draw rectangle.x, plus the width of the draw rectangle gets us to the right-hand side. And if that's greater than window width, we do this other stuff. Now I will tell you, just because you ought to know, that draw rectangle also exposes a right property, which is the x location of the right-hand side of the draw rectangle. So that might even seem more intuitive to you, is that we're checking if the right-hand side of the draw rectangle is greater than window width. If it is, we're going to bounce off. Notice we have to change the upper left-hand corner of the draw rectangle to be at window width minus the draw rectangle width. We can't just set it to window width, because then we'd be guaranteeing that the entire draw rectangle is outside the window on the right-hand side. So we start at the window width and we back up the full width of the draw rectangle so that now the whole draw rectangle is still in the window right up against the right-hand side. And then we reverse the x velocity again. So that's the first example of using selection. We've got this if, else if in our game, where we're in fact doing the bouncing off the walls thing. I very carefully stopped the game when I did before. Now I'm going to let it go a little bit longer so you can see what really happens. Oh my gosh. Very sad. So you should now do an in-lecture quiz about collision detection. Back to our picture of these two bears again. You should be able to realize, I guess, that when the bears ran into each other, we detected that they had collided. That's the collision detection thing. And then we played the explosion. That's called collision resolution. It's how we resolved that particular collision. So how did we detect that the teddy bears had collided with each other? Well, the easiest way is to say, well, how do we know that this guy is colliding with this guy? Well, the easiest way is to say, well, if their rectangles overlap in any way, then we'll call that a collision. Now, that is not perfect, because you'll notice there are some spaces inside these sprites where they're transparent, even though it's inside the draw rectangle. So that's not a perfect way to do it. And of course, there is a perfect way to do it with 2D graphics, and it's called pixel perfect collision detection, because we do it pixel by pixel. Beyond the scope of this particular class, but not rocket science either. I mean, this is a solved problem. We're going to just handle the rectangles overlapping because that lets us just use what we know at this point. But obviously, there are more complicated and better ways to do, ultimately, collision detection. Although almost all of them, even pixel perfect collision detection, uses the rectangle overlapping test first. Because if the draw rectangles don't overlap, there's no way there can be a collision. There's no need to do any extra complicated math. Okay, so let's go look at the code and see how this actually works in practice. So we need to go to the part where we have the collision detection in our code. And that happens in game 1 in this particular instance. So zooming in. And by the way, here's where I created those game objects. Notice that I used the other teddy bear constructor overload where I get to provide a velocity. Otherwise, we have two teddy bears with random velocities and we watch them for a long time potentially before they finally run into each other and explode. And I wanted that gratification as quickly as possible. Okay, so in update, here's where we're doing that collision detection. Now, both teddy bears expose a property called active. So this property is true if the teddy bear is active and false if the teddy bear is not. And this is a fairly common pattern you'll see in game development where we activate and deactivate particular objects. So we only want to check for a collision if both bears are active. If one or both of them are inactive, we don't care if they collide. Here's the part where we check that overlapping of rectangle things. So bear 0 is a teddy bear object. He's exposing the teddy bear class, exposes a collision rectangle object. And notice that the property is called collision rectangle even though we're just providing the draw rectangle. Why? Because it's really going to be used for collisions outside of this class. And we can call this property anything we want. And in fact, we could calculate this property in here every time if we wanted to. And because we have information hiding, it's great. The consumer of this class doesn't care. All they care is they get a rectangle that they can use to check collisions. So we've called it collision rectangle here to hide the fact that it's also the draw rectangle inside the class. Okay, so this is therefore a rectangle object. We call the intersects method. You'd have to go check the documentation, but intersects is a method for the rectangle class where we hand it another rectangle and it returns true if the rectangles intersect and false if they don't, which is exactly what we need. So if the rectangles intersect and both bears are active, we're going to deactivate the bears. We don't care about their collisions or anything anymore. And we're going to play the explosion. And we're going to play the explosion approximately at the point where the collision occurred. So this is actually a really good time for us to go back and do an in-lecture quiz about what collision resolution means, because that's what this whole block of code is collision resolution. This is the detection part. Sorry, all 3 lines. That's the detection part. That's the resolution part. Okay, so now we're going to play the explosion. You should look at that. I'm going to post this code on the course website, so you can just look at this part of the code here. Basically, it figures out where the collision rectangle is, the whole overlap between those 2 rectangles. You should read the intersect, not intersects with an S, the intersect without an S method documentation to see how that works. And then we play this explosion. And that's all well and good, but what does it mean to play the explosion? So let's actually step back and think about how animations work in 2D games. So here on the right, you see something called a sprite strip. It's a strip of frames for an animation that we will use to play the animation. And given that cool term sprite strip, you should do another in-lecture quiz. So how do we actually use a sprite strip? Conceptually, before we look at the code, how do we use this sprite strip to actually play an animation? Well, clearly, we don't put a semi-transparent magenta box over it. However, that's just for us to look at how we really play animations. And the way we really play animations is, this is just a sequence of frames. And what we want to do is, we want to display the 0th frame for a while. And then when we should move on, we want to move on to the 1st frame. And then once we should move on, we want to move on to the 2nd frame. And then to the 3rd frame, and so on throughout the animation. So what we do is we display a particular portion of the sprite strip for some period of time, and then we move on to the next one and move on to the next one and move on to the next one and so on. So that's the idea behind playing animations. And it turns out that this magenta thing right here that I've been moving over different parts of this texture 2D, because that's what it's going to be. It's going to be a texture 2D we load into our game, is something called a source rectangle. So let's go take a look in the code itself. So we need to go to the explosion class in this particular case and make it bigger. And what we're going to care about, we'll look at a number of different things. We have a draw rectangle. That's where the explosion actually gets drawn. Here's a strip name. I just have one explosion. The texture 2D for the strip, like I said. We keep track of frame width and frame height. We're not going to cover all the details in this class, but you can look at it later. And here's the key part based on the conceptual stuff I was talking about. We have this source rectangle, that magenta rectangle we move around on the sprite strip. We keep track of our current frame. We keep track of how long we want each frame to last. And we keep track of how long we've been showing the current frame. So there's this sort of deeper, more generally applicable idea here that we're going to sort of have a timer. And when the timer goes off, we're going to do something and restart the timer. In this particular case, what's going to happen is when the timer goes off, we're going to move to the next frame in the animation and start the timer again so that we know when it's time to move on to the next frame and so on. But the approach we're going to use, which is an update, is going to be generally applicable whenever you need a timer. Okay, so we're only going to update if it's playing. This is a Boolean variable. And here's what we do. We take the elapsed frame time, how long the animation frame has been playing so far, and we take this game time parameter, and we extract from it the elapsed game time since update was last called. So this is sort of the delta between the last time update was called and this time. And we'll convert that or extract the milliseconds property, which will tell us exactly how many milliseconds it's been. With a fixed frame rate, it's going to be 16 milliseconds all the time, but it's worth checking just in case. If you write your code generally applicable this way, then it will work whether you're running fixed time step or not. Okay, so we add to the elapsed frame time, and here's, wow, another if statement. If the elapsed frame time is greater than how long we should show each frame, it means it's time to move on to the next frame. So we reset the frame timer, because now we're starting to display a new frame, and we advance the animation. And we advance the animation with another if statement, just to make sure we don't try to run past the end of the sprite strip. So we set the current frame, well, we check to see if the current frame is less than num frames minus 1 because it's 0 based. If it is, there's another frame to show. So we add 1 to the current frame counter, and then we call this method that you can go look at on your own, but this method right here is the thing that moves that magenta rectangle. So that's what happens if there's still more frames to show. If there aren't, here's the else part. If there aren't, we set playing to false because we're done showing the animation. So, one more in-lecture quiz for you. And to recap, we looked at numerous different uses of the if statement here. We looked at bouncing. We looked at collision detection. We looked at how we can play animations. In this particular case as part of collision resolution, but we could do it sort of anytime we want. There are actually some other if statements in there as well that you may have noticed that, if something is active, we do something. If the animation was playing, we update it. So we saw a whole bunch of different ways that we can use selection in actual game scenarios for this very small, still no user interaction game. Good news, we're at the end of Module 7. Even better news, in Module 8, we'll finally start learning how to get user input in an X&A game so that the player can interact with the game world. Okay, so we're ready to start Module 8, where we finally start getting user input in our X&A games. Here are the learning objectives for the module. So as you can see, we're going to learn how to use both the mouse and the controller as input devices in our X&A games. In this lecture, we're going to focus on using mouse input, and in particular the mouse location input in our games. And over the course of the next few lectures in the module, we'll learn how to use mouse buttons and controller thumbsticks and buttons and so on. So you should start with an in-lecture quiz telling me how you feel about using mouse input in games. I've already created a Windows game project that we'll use to start doing the mouse input, so I'm going to open that up now. So I've done some preliminary stuff. Here's the idea behind this game we're building today. We're going to generate a character, a texture 2D, And we're going to move that character around the screen by dragging the mouse around the screen. And we'll use this as the basis for later projects and later lectures as well. So as you can see if I zoom in, I have the window width and window height. And down here in the constructor, I have set the preferred back buffer width and height to those. And I've also said I want the mouse to be visible. If you're using the mouse for input, you really want the mouse to be visible. Otherwise, the player has no idea where it is in the game window. You can certainly build a customized mouse cursor if you want, but I'm just going to use the standard arrow cursor here. We have our standard, we've got a texture 2D we're going to draw and a rectangle in which we're going to draw it. I've called the texture 2D current character because in fact we're going to let the user click between 4 different characters as they play. Not today. Today they'll just have the character follow the mouse around, but next time they'll be able to click and change it. Planning ahead, I've included a random number generation object that we'll use to randomly pick the next character when they click, and I have 4 different character sprites. So when we go down to load content, you can see that I have loaded all 4 different characters because I have them over here. So I've loaded those just like we typically load texture 2Ds, and then I've said we're going to start at character 0 and we'll set that character into the center of the window. So this part says the current character will be character 0. And this next part says the draw rectangle for that character is located at the horizontal center of the window minus half the character width, at the vertical center of the window minus half the character height, and we're drawing actual size, so we're using the width and height properties of the texture 2D object, the current character variable, to set the width and height of the draw rectangle. So when I run this right now, I get a character drawn in the center of the screen. And by the way, this is one of the characters from the Colorado History arcade game that Peak Game Studios built. So we should go back to the slides so that we can talk before we start doing our update stuff. I'll move to the update method. We're going to make the character follow the mouse. And the way that we're going to make the character follow the mouse is we're going to grab the current mouse state and use information contained in that mouse state to make the character follow it. So go do the in-lecture quiz about a particular method we're going to use, and then come on back. Okay, so we are going to now use the mouse state, the current mouse state, to move around. So I want to make the character follow the mouse. Now what I need to do is I need to extract the current mouse state, and hopefully you realize from the in-lecture quiz that the mouse getState method returns a mouse state to us. So I'll call this mouse, and I'm calling the mouse getState method. So the mouse getState method returns the current state of the mouse. It returns a mouse state object. So we should go take a look at the help to see what that mouse state object really has in it. And as we can see, there are a number of interesting properties that we have available to us. So we have left button, middle button, right button. We can get the status or the state of those buttons. We have the scroll wheel value if you happen to have a mouse with a scroll wheel. We can get it X and Y, the horizontal and vertical position of the mouse, and X button 1 and X button 2 in case you have one of those fancy mice that actually has a couple of buttons on the left-hand side so that you can go back in your browser, which, by the way, if you use that twice, you feel like you can never live without it again. So let's actually take a look at least at first, I guess we'll come back to the buttons later on. So for now, let's look at the X and Y because those are going to be very useful to us. So I'll click on this property and it says, okay, it's an int. So it's going to tell me basically which pixel location in my game window the mouse is located at. And that's going to be useful to us here because what we want to do is we want to adjust the draw rectangle so that the draw rectangle is aligned. Let's center it on the mouse location. So what that means is we need to take the draw rectangle and modify its x. And we modify its x by saying, well, we'll make it mouse.x, which would anchor the draw rectangle, the upper left-hand corner of the draw rectangle, on the mouse x position. And then we'll subtract half of the width of the current character. And that will make the character stay centered horizontally on the mouse location. And we'll do something very similar for height. So now, when we run our program, we see that the character is following the mouse around. Now it turns out that this is probably bad, letting the player drag the character outside the screen. We probably should not let them do that. So let's do what's called clamping the character inside the window. So the term clamping means if in fact a particular value is outside its valid range, we clamp it, we set it to either the minimum or maximum, whichever side it's outside. So we're going to actually clamp the character inside the window. So to do so, we have to check 4 different things. And we've actually seen this with the teddy bear bouncing left and right. We're going to do it again here, but we'll do it from scratch just as a reminder. So let's say we want to check if the draw rectangle left, so we'll check if the left part of the draw rectangle is less than 0, which means that at least part of the draw rectangle is outside the window. If that's the case, we'll set draw rectangle x equal to 0. We will clamp, we will make the draw rectangle stay at the left side of the window. We'll check the right hand side of the draw rectangle as well. So if that's greater than window width, so here's another great benefit of using window width as a constant rather than hard coding it in multiple places, because this code will continue to work even if we change the resolution. So now it's outside the right hand side. We still can only change x. It might be kind of interesting actually to change the width of the draw rectangle instead to sort of squish the character against the right hand side, and you can experiment with that if you'd like to, but I'm going to shift the draw rectangle left again so that the entire draw rectangle still stays in the window. So to do that, I have to start at window width, which would put the draw rectangle totally outside on the right, and then back it up to the left, the width of the draw rectangle. And that will clamp. Let's go ahead and check clamping left and right. I'm trying to go past on the right and I can't. I'm trying to go past on the left and I can't. Moving up and down, I'm still not clamped. So we'll do that now. But it's reasonable to write a few lines of code and test before moving on. So now I need to clamp top and bottom. So if the top is less than 0, I'll just set y to be 0, not 90. That would look kind of weird. And if the bottom is greater than the height, then I will do a similar thing to what I did on the right. I'll start at the height, which puts it all the way outside the window, and then I'll subtract the height of the current character. So now the character stays clamped inside the window, and I can move it around in the window. It follows the mouse, but it stays clamped in the window. So you should go do an in-lecture quiz. And by the way, that's all the coding we'll be doing for today. But go do the in-lecture quiz about clamping. And now we can recap. And this is our first step in using user input inside our X and A games. And we started with the mouse, obviously. We learned how we can use the mouse location to move something around on the screen. And we also learned that clamping is a valuable technique that we can use to keep objects or game entities, inside particular boundaries. Next time we'll continue working with the mouse, although now we'll start working with the mouse button. In this second lecture in Module 8, we continue using mouse input. And before we talk about the details, here's a reminder of the learning objectives for this module. So last time, we learned how to use the mouse location to move a character around in the window, including clamping that character so it stays in the window. This time, we're going to learn how to use a mouse button for input to change the character to some other random character. So let's go to the project. Sorry, let's not go to the project quite yet. Let's have you do an in-lecture quiz first, based on your recollection of the things that are contained in the mouse state object that gets returned when we call getState. Now let's go to the project, and we are going to just be starting from where we were before. And so we've got a character. I'll run it again so we can see how it works. We've got a character that follows the mouse around the screen, staying clamped in the screen so they can't go outside the bounds. Let's actually talk for a minute or two through the documentation to see how we can use a mouse button. So I'm going to search on mouse state again, just like I did last time, although perhaps I'll spell it correctly so that we actually get a hit. So we have these mouse state members, as we saw before. 5 different buttons is what X and A provides for us, and some other stuff to the location that we used last time. So let's look at the left button, because this description says it returns the state of the left mouse button. And when we look at that, we see that it returns something called button state. Now, button state is an enumeration. And an enumeration, let's go look at button state so we can see how it really works. An enumeration is a new data type that only has specific values. So if we have button state, which is what gets returned from left button, the left button property of the mouse state, then that returned value can only be one of 2 different values. It can be button state dot pressed, or it can be button state dot released. So I mentioned in passing in one of the previous lectures about enumerations and how they are going to be very useful to us in the future. Well, now is the future, and so you should actually answer an in-lecture quiz about enumerations, and then we'll go back to the code. So now that we know that the left button property of the mouse state gives us either button state.pressed or button state released, we see that we can actually compare the current mouse state to, for a particular button, to pressed or released and do something interesting. So I want to be clear that this code is commented left mouse press code bad, so that you don't think I thought this all worked and everything. But here's what we're going to do. We're going to take the current state of the mouse. We'll access the left button. We'll access the left button property, and then we'll compare it to pressed. And if the left mouse button is pressed, then we're going to randomly generate another character number. And by the way, the next method in the random class, the number we provide is in fact not, it's exclusive. It will not ever return 4 for this call. It will only return 0, 1, 2, or 3. So that trips people up sometimes, so be aware of that. This upper bound, if you will, is a maximum, but it's an exclusive upper bound. Okay, and then we use if statements like you've seen before. So if the number we generated is 0, we're going to set the current character to that sprite. Otherwise, if it's 1, we're going to do 1, otherwise 2, otherwise 3. So that's how that code works. Now it turns out that the character sprites that we're using here are of not all the same width and height. So after we've picked the new texture 2D, we want to modify the draw rectangle to make it match the character's texture 2D, the new one we just picked. So this is bad code, and let me show you why. So we still get the drag around, but if I press left, oh dear, I'm getting a bunch of different characters, and that's kind of fun, and I can drag them around and so on. However, the problem is as follows. This update method right here in our Game 1 class gets called 60 times a second. And so if I'm holding the mouse down, every 60th of a second it's saying, yes, the left mouse button is pressed, so I should change. And that's why we're getting all those changes that are happening. So what I need to do instead is, well, I'll tell you what, go do an in-lecture quiz, and then come back, and then I'll tell you what we're going to do. So what we want to do is we want to change on a click, not on a press. So how do we know about a click? What is a mouse click? What a philosophical question. What is a mouse click? Well, a mouse click is a sequence of two things. It's the mouse was pressed previously, and now it's released. And so our if statement cannot just be if it's pressed. In fact, it won't be if it's pressed. So what we really need is we need if it's currently released and it was previously pressed. And here, I'm poised to type, but there's nothing to type because there's no way for me at this point to know whether it was previously pressed or not. The good news is that we know how to store information. We store information in variables. And so if we declare another variable to keep track of what the previous button state was, then we can use that to determine or to detect when the mouse has been clicked, the left mouse button has been clicked. So I'll declare a new variable here at the top of the Game 1 class, and it's going to be a button state variable. These enumerations are a data type, and so we can declare variables of this data type. So I'll call this previous button state because it's the previous button state. Some of you who type slowly or are lazy, programmers are lazy in general, but those of you who type slowly or are lazy might say PBS means, previous button state. Don't do that. Use descriptive variable names because it really helps with readability. All right, so we can pick between one of two possible values to start with here. We can start the previous button state as pressed or released. Well, it is reasonable to assume when somebody starts our game that they're not holding down the left mouse button. So let's say we start at released. Okay, so we are now going to keep track of the previous button state so that here in update, we can now say if the button state is released and previous button state was pressed, so now we've detected a click. It's now released and it was pressed on the last update, then we'll do this stuff. So not too much of this stuff, we'll do this stuff. So I'll copy and paste it here. And I'm going to comment this bad code out because otherwise it will obscure what's really happening for us. So now I'm checking. If it's currently released and it was previously pressed, change the character. So now when I run the code, drags around like usual. Oh dear, I'm clicking away and nothing good is happening. This is a debugging problem, right? And the debugging problem is that something's going around here, obviously, right? It's not catching or detecting that mouse click. Well, you should realize with some thought that previous button state is never going to be pressed because because we can find out why, I'm going to right-click on this variable, and I'm going to go about halfway down, and I'm picking the option that says Find All References. When I do that, this window down on the bottom gives us every single reference to this particular variable. And so we're here at this one. If we double-click the other one, we see we're checking against it. But if we look at those two things, those are the only two places in our entire game where this variable is accessed. What that means, though, is this is the only assignment, which in turn means this variable always says the button state is released. So what we need to do is we need to update that previous button state on every update, and we'll do this outside the if statement. Really what we're saying is we want to store this variable, we want to store the current state into previous button state. Let me explain that in a minute. So previous button state is equal to mouse.left button. So basically what we're doing is, think of this as on the first update. We come here, we get the current mouse left button, and we store it into previous button state because we're going to leave this update method. And then on a 60th of a second later, we're going to come back here again. And the previous button state stores what the button state was last update. And so in this way, we can store basically the button state from the last call to update so we can look at it on this call to update. And now when I run the code, you'll see if I click, I get a change to a different character. Now, if you're listening carefully to the clicks, you may say, well, sometimes you're clicking and it's not changing. And that is, it's actually not true. It just appears to be that way. Here's the thing. When we generate a random number here, say we currently have displayed character 1. It's certainly possible, with a chance of 1 in 4, that we're going to generate a 1 again. And if we do this part, and then we move on. And so it's possible that on a click, we get the same character we're currently displaying. The code is not broken. It's doing what we've said it should do. It randomly picks a character, but sometimes that random pick of a character is the same character we currently have. The randomness is really an interesting thing in games, because when we do things purely randomly from a math perspective, it is easy sometimes for players to perceive that the game is broken, that it is not random, that there's a bug. And if you had a coin flipping game, it is certainly within the realm of possibility that you'd flip 10 heads in a row. And no gamer playing that game would believe that you did it right. They would say it's broken, that can't be done. And they'll post on the forums and you'll jump on and you say you obviously don't understand math, and that's just a ridiculous approach as a game developer, right? So what we do as game developers is we actually don't do pure randomness. We do the appearance of randomness such that players like our game. And math purity can be saved for the mathematicians. We fake randomness a lot. I'm not going to fix that here. That's sort of something that you could figure out on your own. And in fact, once we learn about iteration in the next week of lectures, we'll actually see a way that we could, in fact, make this better so that it doesn't pick the same character. But for now, we'll just live with it, but understand that those things can, in fact, be a problem. All right, and that's it for the code for today, too. Right? And in fact, we're done with mice. We have learned how to use the mouse location. We've learned how to use the mouse buttons. We've learned that mouse clicks and mouse presses are in fact not the same thing. And so we are next time going to move on to using 360 controllers for input in our XNA games. Continuing on, learning about how we can use player input in our XNA games. We finished up with mice last time, and we're going to start on 360 controllers this time. Here are the module learning objectives. So we want to start using a controller for our input in our X and A games. And normal people use a controller like this, perhaps even not with a wire on it. Super geeky people like me use a controller like this, with hyper-responsive buttons and, in fact, tension adjusters on the thumbsticks so that you can modify how much resistance those thumbsticks provide to you. Yes, geeky, but, you know, you got to do something, right? Okay, so we're going to look at how we can use, we'll start with using a thumbstick, the left thumbstick, to drive the character around the screen. Remember last time when we were using a mouse, we used the mouse to use the mouse location to move the character around. Now we're going to use the thumbstick instead. So let's go to the code that we had before, and we will gradually convert this code to using a controller instead of a mouse. So this time, we're going to use the thumbstick to move the character. Next time, we'll use the A button to change the character, just like we used the left mouse button before. Okay, so we want to make the thumbstick move the character. So as you can see here, I commented out the code we had before. And I've moved the mouse get state thing down here. So this will be a really weird game where you move with the thumbstick, but you change with the left mouse. That is a temporary thing. We would never make a game like that all the way to the end. Okay, so the issue though is instead of getting a mouse state, we need to get a gamepad state. And I'll just call it gamepad. And we'll call the gamepad get state. We'll call the gamepad get state method instead of the mouse get state method. As soon as I open the parenthesis though, we discover that we have to provide one argument when we call the get state. And that argument needs to say, well, which gamepad do you mean? By default, when you plug a 360 controller into your laptop or PC of any kind, it is player index 1. But of course, if you're building an Xbox game or if you have multiple 360 controllers plugged in, it is, you know, there's a broader range. By the way, gamepad and controller mean the same thing. So within the X and A framework, it's always gamepad, but most people call it a 360 controller or a controller. So I will interchange those different pieces of terminology, but they're the same thing. So we're going to do it for player index 1. So one of the things that we haven't really talked about, even though we've been using it a lot, is this syntax that I'm using to call getState, and the syntax I use down here to call getState on a mouse. Because we've talked about calling methods by providing an object name, some lowercase variable, dot, and the method name. And so those are what are called instance methods, because we're calling the method on a particular instance of the class, on a particular object. And by and large, that's what you're going to use all the time. However, all the time is a little too strong, because we have discovered ourselves using this other syntax, even all the way back on our first C# program, where we use console.writeLine. Console, we weren't holding a console object. We were providing a class name, not an object name. And so there are these special kinds of methods that we call that are called static methods. And we call static methods by putting the class name followed by the method, followed by a dot, followed by the method name, rather than a particular object's name. So I just said a whole bunch of words. You should go do an in-lecture quiz to see if you figured out what those words mean. I jumped ahead a little bit. So the in-lecture quiz you're about to do is about static methods, and that's awesome. So we'll talk about those, and then I'll have you do another in-lecture quiz about actually using a 360 controller. So if we look at this slide, I've extracted from the documentation information about the gamepad members. So the gamepad members are these three things. We can call get capabilities, we can call get state, and we can call set vibration. How do we know if a particular method is static or not? We know because on the documentation there's a big S. That doesn't stand for super method, that stands for static. And so if we ever see S on a particular method in the documentation, that means we call that method by using the class name rather than an instance name. Let's take a look at another example where the documentation actually shows us both kinds. So let's look at rectangle. So we've got a whole bunch of rectangle fields, so I'm going to navigate around for a little while. Rectangle structure, I want rectangle members, so here we go. You'll notice if you look at the public methods here, and this applies to properties too. If we look at the public method, remember we used intersects with an S on a particular rectangle object to see if it intersects with another one. But we could use intersect without the S. Notice it's a static method because it has that S. So we'd call this one rectangle.intersect, and we'd hand it to two rectangles, and it returns another rectangle back to us. So the static methods that we call by putting the class name first are particularly useful. It's just a slightly different syntax for calling them. Okay, so backing up to the in-lecture quiz that I went blasting by, tell me how you feel about using a 360 controller as an input device. Okay, so let's now fire up the debugger. Notice I do have a 360 controller plugged in right now. But let's fire up the debugger, and I've F5'd. So I am now going to extract or get the gamepad state. And if I press F10, I step over this, it executes this line of code and moves on to the next one. So now I can hover over gamepad and see that it's connected and there's a whole bunch of other stuff available to me. But this is connected thing really matters. And you should go do another in-lecture quiz to tell me about how that is connected thing really matters. Okay, now that you're back, we're going to actually start moving the character around based on the thumbstick. Well, unfortunately, the thumbstick, we don't get a location like we got for the mouse. There is no X and Y for the thumbstick. It's not a pointing device like the mouse is. It's just a device that we deflect to get action in our game. So we can't use, there's no such thing as gamepad.x and gamepad.y or left thumbstick.x or anything like that. So we can't use that to move our character around. Instead, what happens is the thumbstick, well, we can look at the documentation and see what happens. So let's look at gamepad state. Like so, because that's what comes back from our getState method. We can see we can access a structure of thumbsticks. And those thumbsticks are gamepad thumbsticks. So let's take a look at what those are. So gamepad thumbsticks, that structure has a left and a right property, so we can get at the left thumbstick or the right thumbstick. And finally, if we click on the left property, we get a vector2. And the vector2 says it's the position of the left thumbstick, and we get floating point values. So left and right, -1 is all the way to the left, +1 is all the way to the right. Up and down, so that's the X component of the vector2. Vector2s have an X property and a Y property. And up and down, -1 is all the way down, +1 is all the way up. So we're going to access some range of deflection from -1 to 1 for both X and Y on the thumbstick, and we're going to have to use that somehow to actually change the location of the character. So think of it as not following the thumbstick around so much as using the thumbstick to apply thrust to the character. So we'll use the thumbstick to push the character around because we're being that way. So we're going to push the character around instead of trying to make it follow an X and Y. So let's go back to the code to see how we can do that. I'm going to go up to the top of game 1. And you'll see we have a thumbstick deflection amount. I already declared this constant and I've set it to 100. So if the thumbstick is banged all the way to the right, for example, on a particular update, we'll end up moving the character 100 pixels to the right. We might find that I can't quite control that as much as we'd like, but we'll start there. Okay, so what we can do is down here in our update, we can change the draw rectangle's X location, and we'll add to it, remember plus equal, we'll add to it the gamepad left thumbstick, the gamepad thumbsticks left X. So here's what we have, right? We have the gamepad, that's the gamepad state. The thumbsticks is the thumbsticks structure, which lets us access the left and right thumbsticks. The left property gives us a vector 2, which has X and Y properties. And so finally, this whole big thing here is the deflection on the left thumbstick in the X direction, which ranges from -1 to 1. So we'll take that and we'll multiply it by the thumbstick deflection amount, that constant I just showed you, and we'll get a compilation error. And when we F6, it says we can't convert float to int, so this whole thing is a float. And draw rectangle.x is an int, so we have to do a typecast. And we'll do the typecast. And now I'm going to make another deliberate mistake. We'll say, great. We'll do the same darn thing for draw rectangle y. And I run it and I grab my 360 controller. And I can drive with the thumbstick very fast, as you can see, but you can't tell. But as I push the thumbstick up, the character goes down. Now, some people, right? Some gamers love that, right? That's exactly how you like to aim. You use it sort of exactly opposite of the way it works and so on. But let's actually take care of many people. And we'll have to fix this by changing this to minus equal. So remember that the real issue here is that the thumbstick negative is low and positive is high. But in our window, Y is numbered starting at 0, the pixels are numbered starting at 0 at the top, and they increase as we go down. So we have to reverse it. In this basic example, building a real game, you can actually find out from the player profile which they prefer and set it appropriately and all those things. So we can make it much more customizable for the player. We're just not going to bother to do that here. The other thing we will do is I'm going to change this deflection amount to be like 20, not 120. 20 instead. So now I can move much more reasonably, and because we actually get a floating point number in the left value, I get better control. I can move slowly or I can move quickly, and it just depends on how much I've deflected it. So that's all good, right? That is, and in fact, that is it for the code that we're writing for today. So I should point out that I just lied to you moments ago. That's not all it for the code we're writing for today, because we skipped one critical thing down here in using the thumbstick. Here's the thing. It is certainly possible that we try to get gamepad state, but this particular gamepad is not connected. So go do an in-lecture quiz about what you think happens when that's the case, and we'll come back and fix that last thing. Okay, so what we should really do in the code is we should only respond to gamepad input if, in fact, the gamepad is connected. And I'm going to get rid of this commented mouse state code because that was just temporary stuff. That was really interesting. Sorry about that. So it's important, if you're going to use gamepad input, that you make sure that, in fact, the gamepad is connected before you use any of that input. Okay, because it's invalid. We don't know what it is. It's just whatever happens to get returned. So now I'm no longer lying to you. That is all the code we're writing for today. So as a recap, we learned how to get the gamepad state. We learned about static methods. And we learned about how to use a thumbstick to move the character around. Next lecture, we'll learn how to use a gamepad button to actually change the characters just like we used the left mouse button before. Today we'll continue with our using the controller as an input device in our X and A games. Here's a reminder of the module learning objectives for Module 8. Last time, we used a controller to use the thumbstick on the controller to move our character around and keep it clamped in the window, which had nothing to do with the thumbstick itself. We just left that code alone. So this time we're going to move on and use one of the buttons on the gamepad or the controller to change to a new character when the player presses that button. So let's go to the code. We're starting from the code we ended with last time. As you recall, we moved around with the thumbstick and we checked to make sure that the gamepad was connected before we did. Now we're going to use the A button to actually change characters. And so I'm going to take this close curly brace, which goes with the if statement. Remember, we said that we only want to use gamepad input if the gamepad is connected. So I'm going to delete that from there, and I'm going to move it all the way to the end of the method. So now any gamepad processing we do will only be done if the gamepad is connected. Let's comment this out just to demonstrate yet again that we can't use a press, that we really do need to use a click, even with the A button on the gamepad. So I'll uncomment this code. We, of course, no longer have a mouse variable. So let's say we'll change the comment, A button press code bad. And so instead of checking whether the mouse left button is pressed, we can check the gamepad. Recall that this is a gamepad state object that we get by calling the gamepad getState method. So we'll take a look at the gamepad and we will access the buttons of the gamepad, and then we can pick which button we want to access. So there's a big button and there's, AB, back, start. Left shoulder is a button. Left stick means you push down on the left thumbstick. So we actually have quite a few buttons. I'll scroll here to show. We actually have quite a few buttons on a 360 controller, but we're just going to use the A button. And so when we F5, I press A, and we get the same behavior we had when we were trying to just do a left mouse press. So that clearly doesn't work for us. And in fact, I'm just going to delete all this code. Perhaps with some control, I will delete all this code. And I will uncomment this code. And we'll have to just make a couple of changes to it, and we'll be good to go. Okay, so uncomment, not cut, uncomment, wow. All that code on A button click, not left mouse click. And it might feel to you that there's no reason to fix the comments, but we want the comments to reflect how the code actually works. So not the A button press. So we don't need this anymore. because we're not using the mouse anymore. And here we'll check gamepad, buttons, A, just as before. So we're checking if A is released. We're checking if the previous state was pressed. So this is a click on the A button. Change to a random character. And of course, we need to change this as well to keep track of the previous state of the A button rather than the left mouse button. So gamepad, buttons, A, like so. If I run it, I'm clicking the A button, and sometimes I get the same one, but regularly I don't as well. And we talked about that last time, how that works. So really, if we're doing a straight conversion from the mouse left button to the gamepad A button, that's it. That's all we need to do to get the same behavior from the A button that we used to get from the left mouse button. I do want to show you, though, that there is another way that we can do this that essentially uses the same idea, but in a slightly different way. And so you might see lots of people processing buttons with the gamepad in this way instead. So I'll show you this way as well. So I'm going to comment out this, and I'm going to replace it with a Boolean variable previous I'm going to say A previous released, and I'll set it to true. So essentially it's going to do the same sort of thing. It's going to keep track of whether the A button was previously released. So since I described it that way, let's change our variable name. So A button previously released. Okay, we'll come down here back to the update code. And now we won't be checking this. We'll be checking A button previously released. Now notice there's no equal here. I could in fact say equal true, for example, but there's no reason to do that because this is a Boolean variable. And so comparing a true or a false to true or a false just wastes CPU cycles. There's no reason to do it. As I think about this, as I copied this here, I realized that I don't really care if the A button was previously released. What I really care about was it previously pressed? And so in fact, I can do something called refactoring. We've talked about refactoring as restructuring the code. I can refactor to rename this variable. And if I say A button previously pressed and say OK and apply it, it changes it here and it changes it here. In fact, it changes it everywhere throughout my code. I actually want to now start, though, with this being false. So A was not previously pressed. However, in our update, we'll check if the A button is currently released and it was previously pressed, then we'll do this stuff. And in fact, we will change this a little bit. And instead of doing that comparison to the button state, we will actually ask the gamepad, is button down? And we will have to provide it with one argument, which button we mean. So we'll say buttons.a. Buttons is just an enumeration of all the possible buttons on the 360 controller. And so this is a different way. We check and find out if A is down, but that's not what we really want. We want if A is up, so it's released, and it was previously pressed, so that's a click on the A button. We still have to change this, though, because we got rid of that variable. So I'll just comment this out and say A previously A button previously pressed is going to just be gamepad is button down, buttons A. So think about how this works. Basically, this is a Boolean variable, so it has to get a Boolean value The isButtonDown method returns a Boolean value, true or false, based on whatever button we provide it. So this question over here is the A button down? And if this method returns true, then the variable A button previously pressed gets set to true. If this method returns false, then this gets set to false. And so if we F5 again, I'm getting the same behavior as before. It's changing when I click the A button. The way that you do this, which technique you use, whether you're doing isButtonUp, isButtonDown, or whether you're keeping track of the button state of the buttons, is in many ways personal preference. I have personally found that I tend to use the isButtonUp, isButtonDown thing more regularly when I'm processing a controller, but you can do it the other way too. And if you do it the other way, it's so similar to the way we process mouse button input, that may be more intuitive to you because you do it sort of consistently across both input devices. So what we've seen at this point is we've seen how we can use the mouse, both location and button. We've seen how we can use the controller, both for the thumbstick and a button, as input devices for our X and A games. And really that concludes in this module all the forms of input that we want to deal with. However, there is one form of output that we can use with the 360 controller. It's called force feedback, and we are going to look at that next time. So we're all done with input, but we're going to look at output next time to finish off the module. The good news is that this module only has 2 lectures, and the even better news is that we're going to use some really powerful ideas that we're going to find to be particularly useful in our game development. To start, here are the Module 9 learning objectives. So one of the things that we need to deal with as we develop games is we need to handle having a whole bunch of different game objects in the game world. And we've talked about, from way back in Classes and Objects, we talked about the object-oriented paradigm and how it is a set of interacting objects in our software. Well, our game world is a set of interacting entities, and we need to do things with that set of interacting entities. We have to update all of them. We have to draw all of them. There are lots of things we need to do with all of the, at least active, entities in our game world. And having a separate variable that we use to store each of them is really problematic. That doesn't really work for us at all. We need a better way to store a whole bunch of game objects and use those game objects within our game world. That's what we're going to learn about in this module. So to start, you should take an in-lecture quiz about arrays. So it turns out that arrays are a way that we can store a whole bunch of different objects. And so it also turns out that arrays in C# are objects as well. And we'll see the syntax we use to deal with those array objects soon. But the question is, what can we store in arrays? And the answer is anything. We can store value types. We can store reference types. We can store other arrays in arrays. We can pretty much store anything we can think of, at least as a data type, in the arrays that we have available to us in C#. That comes with a caution. Darn it, there's always a but. The but is that in a particular array, we can only store a single data type. So each array that we declare and use can only store one thing. So we can have an array of ints, and we could have an array of teddy bears, and we could have an array of texture 2Ds, and we could have an array of floats. We can have each array hold a different data type. But once we have an array, it can only store a single data type. So what do arrays look like in memory? Let's take a look. Conceptually, let's take a look. before we do an in-lecture quiz about arrays and what they can store, and then we'll look. Okay, so sort of conceptually anyway, this is kind of like what arrays look like in memory. So think of all these floating point numbers as GPAs. They're grade point averages that we're storing. So we have a variable called GPAs, and then if we're storing 10 of them, as in this example, then they're numbered. They're in memory boxes, as we're used to, but they're numbered from 0 to 9. And so let's hit some terminology about how we talk about arrays and the things in arrays. So do an in-lecture quiz about what each value that's stored in an array is called. And because these in-lecture quizzes are often about joking around and being, I was going to say funny, being funny like I think funny is, it's possible that you don't actually know the right answer when you're done with this one. So the right answer is element. So each thing we store, we talk about an array of elements. So the thing at location 0 is an array element, and the thing at location 1 is an array element, and so on. So that the values that we're storing in the array are called elements. Another in-lecture quiz. The number we use to talk about the location in an array is called the index. So 0 is an index and 8 is an index. They're indexes into the array. Now, hopefully you recall that you've heard this terminology before. We've talked about indexes before, fairly recently, Module 7, because we talked about accessing a particular character in a string by using the index of that character. We were actually ahead of the game. We were actually accessing a particular item in an array by using an index. So that's why that terminology index was used there, and we will use it here too. So the index is a location in the array. So let's go to the code we had before. This was mouse input processing, right? So I press F5 to run the code, follows me around, and I click to change the character. And I only had 4 characters in this particular game. Oh, it is a game. I was interacting with it in this game, but it could have been that I could have had, hundreds of characters or something. We will see. Let's convert this to use an array instead of the 4 separate variables for the different character texture 2Ds. So I'm going to start here. And instead of having these 4 variables, I'm going to declare a single variable that's an array. And the way I say it's an array is first I put the data type of the elements. This array is going to store texture 2Ds. So that's what I put first. But then to tell the compiler I'm declaring an array variable, I put square brackets. Now I put a variable name. I'm going to call these characters. Maybe. I'm going to call these characters. And remember, because arrays are objects, I'm going to need to create a new array. And I want to create a new array of texture 2Ds. But between the square brackets on this side, I need to say exactly how many elements I want. And in this particular case, I want 4 elements because I'm replacing 4 variables. Semicolon. And that declares the variable, the array variable, and creates the array object. Now, if I were to put the debugger right here, a breakpoint, and whoops, and get rid of that old breakpoint I have hanging around. Let's stop. Let's try that again. We'll put the breakpoint here after all. If I F5, and now I look at this characters array, I've hovered over it and I know it's hard to see. You can also, by the way, click around in here to expand what's in the characters array. Maybe that's easier to see. But you can see each of these 4 elements in the array is null right now. That's the default value for a reference type, is it starts at null. And so even though I created the array object, I didn't create all those characters in it. I'll F5 and get out of here. Get rid of that breakpoint. Now I'm going to delete these 4 variables. I don't need them anymore. I have this array instead. Of course, that means I don't compile anymore, because down here where I was trying to load those sprites, I used to be loading into these 4 separate variables. Instead, I'm going to index into the array using the same notation we used to index to get a particular character from a string. And so I put the variable name, open square bracket, the index I want to access, and then close square bracket. And of course, I need the actual variable name characters so that now I can compile. I'm still getting compilation errors and we'll fix those soon. But before we do, you should go do an in-lecture quiz about accessing individual elements of the array. Now that you're back, let's finish that conversion to using the array. This is our next problem. And again, we'll just access characters 0 instead. And so far, you might not be seeing a whole bunch of benefit, right? I mean, we did in fact reduce those 4 variables to 1, and the rest of this we haven't sort of done any reduction in code or anything like that. Here's where we see a real win is here when we're changing to a random character. So we used to have all this code to actually figure out what the next character was going to be. And I'm going to comment that out. And I'm going to say that the current character gets set equal to some element of the characters array. And all I have to say is which index. But which index can be this random number that I generated between 0 and 3 inclusive. So this single line of code does what all of this used to do before. And when I run the code again, I still am randomly getting different characters with some duplicates, as we've discussed, and so on. So there's a big benefit from using the arrays. I'll close out of here. There's a big benefit from using these arrays because it lets us reduce the number of variables we have to have, and in some cases it significantly reduces the amount of code we need to have as well. We haven't even talked about it, but that array that we used here was a one-dimensional array. But arrays don't have to be one-dimensional. They can have 2 dimensionals. For a game board, for example, if you were building a game of checkers, a 2-dimensional array would be a great way to save each space, what's in it, and so on. So arrays don't have to be one-dimensional. They can have numerous dimensions. And you should go do an in-lecture quiz to tell me what you understand about that. Before I let you go, I thought you might like to see a little clip of how this array discussion goes in my regular classroom.
So at this point, I can tell, I feel the energy like pouring off you guys. You guys are like, holy crap, what a tool. No, I don't mean, okay, wait a minute. All right. No. Don't look at me and think, what a tool. Think about arrays and say, what a tool. Because now I can build games. And if I'm going to have 400 teddy bears, I don't need 400 variables called teddy bear 0, teddy bear 1, teddy bear 2, teddy bear 3. I can just build an array that will hold 400 teddy bears. And I just have to declare a variable once. And then I just manipulate, yay, huzzah, and there was much rejoicing.
Okay, so we learned how to solve a core problem here. We learned how to store and use multiple different things, all the same data type, multiple different game entities so that we could efficiently use and process them. Next time, we're going to discover an even more robust way that we can store these multiple elements to overcome one of the core limitations of arrays. I'll tell you right now, the core limitation of the array is when we created the array object, we had to say how many elements there are going to be. And so if we have a game where we spawn elements or kill elements, game entities, excuse me, then arrays are harder to work with. So next time, we're going to learn about something called collection classes that we can use to basically use many of the same ideas that we get with arrays, but in a more robust way. This is our second and final lecture in Module 9. As a reminder, here are the learning objectives for the module. So last time we talked about arrays as a way to store multiple game entities, if you will, elements that we could then process in a reasonable way. And it saved on how many variables we needed, and we saw how it could save us some code and so on. Arrays are a structure that tends to be available in pretty much every modern programming language, though in most of them, as in C#, we need to know how many elements of the array we need when we create the array object. In some cases, that works just fine, but in cases where the the number of the elements that we need to store can change dynamically, for example, in a game where we're actually spawning stuff and killing stuff off and so on, that's a problematic limitation. So this time we're going to look at something called collection classes that don't have that limitation. They can dynamically grow and shrink as we need them to as the game runs. You should immediately take an in-lecture quiz to tell me what you know about what collection classes can hold. And this slide should look really familiar to you because I basically came in and replaced the word arrays with collection classes. So just as with arrays, we can store anything. But same as with arrays, a particular collection, which is an object, just like arrays are, a particular collection can only store a single data type. And we can have lots of different collections that store lots of different stuff, but we can't mix data types in a particular collection. So the next question is, where can we find these things? And for that, we should open up the IDE and look at help. So here is the project that we used last time with arrays. This was our final product from last time. And I'm going to convert it to use a particular collection class. But before I do, I want to go to help and show you where you can find all the collection classes. So this is a namespace system.collections.generic. And we'll talk about generic again momentarily. But I'm going to click on the very first search result. And you can see here that there are a whole bunch of different collection classes we can use. And as you go through your programming career, you will discover that some of these are more effective in particular situations than others. But for us, for right now, we're going to go and use the list collection class, this one right here. But when you're going to look for collection classes, you should go to the system.collections.generic namespace. In the interest of full disclosure, I should tell you you can also go to the system.collections namespace, but the generic collections tend to be the ones that are most useful and better programming practice in general. So here we are. And what I want to do is I want to convert this from an array into a list instead. So what I'm going to do is I'll just comment this out. The first thing we need is a data type. And the data type is list, as we saw. However, it's actually a generic, so we have to say a list of what. Just as we had to say an array of what when we were declaring an array, here we have to say a list of what. And let's make it texture 2Ds, because that's what we want to store. Now, you should be, hopefully, thinking you've seen something like this before. When we use the Content Manager load method, I said this is an instance of a generic, and we had to, between the less than and greater than signs, we had to put the data type of the content that we needed to load. And that the load method is actually what's called a generic method, whereas this list class is a generic class. But the idea is the same. We have to put the data type that we want to store in between the less than and greater than. So you've seen this before when we loaded content. This is in a slightly different context. It's basically saying the data type of the elements we're going to store in the list. So I can still call it characters, and it's still an object. And in fact, it's a list of texture 2Ds. So I have now created this new list. The only other thing I need to change in this code to convert from arrays to lists is right here where I was setting these where I was loading the elements of the array. Because with the list class, we don't actually do it this way. We add things to the list. So instead of saying characters 0 equal content load that texture 2D, I'm going to say characters dot add like that. And what happens is it will load this texture 2D. The content manager still loads this content as it did before, and it will add this to the it will add it to the end of the list. And since this is an empty list, it will add it at the 0th location. And so to add each of these to the list, we just change the syntax like this. And this will work to add character 0 at location 0 in the list, character 1 at location 1 in the list, character 2 at location 2 in the list, and character 3 at location 3 in the list. And when I run this, it works exactly the way it did before, except now we're using a collection that we dynamically grew as we went along. So that's it for the conversion of the code to a collection. What that means is I have a couple of in-lecture quizzes for you to do. So do this first one that really gets at the key difference between collection classes and arrays. And now do this one, which addresses something I haven't even spoken about at all today. So the answer to that is we access elements of the list just like we accessed elements of the array. We use the square bracket notation to get at stuff in the list. Now, it might be hard to see from this example why collection classes are useful, right? Because sure, I changed some syntax here, but we really didn't see any huge benefit. Next module, we will see why this is really useful. We need one more piece of understanding about how C# works before we can see why collection classes are so much more powerful than arrays for games in general. So we'll have to wait patiently. But we did see that collection classes can also be used to store multiple elements for ease of processing, just as we used arrays for. We learned that collection classes can grow and shrink dynamically, which is something that arrays can't do. And then next time, we'll start on the next module, where we'll learn the final control structure we need to be able to solve sort of almost any problem you can imagine. It's time to move on to the next module. So we're up to module 10, where we're going to talk about iteration. And this is the only module that we're going to cover this week because there are a number of lectures that we're going to use. Here are the module learning objectives for the module. And as you can see, there are quite a few of them. So in this module, we're going to talk about the final control structure we need to solve a wide range of problems. We've already talked about the sequential control structure, where we execute statements in sequence. And we've talked about the selection control structure, where we can select between different courses of action in our program. This final control structure is called the iteration control structure, though you may hear people talk about it as the looping control structure as well. So, we'll start with an in-lecture quiz. So this module and the lectures in this module are broken up into 3 separate parts. The first part, which consists of the first 3 lectures, is about running loops when we know how many times we're going to execute the loop by the time we get to it. We don't need to know how many times we're going to loop when we write the program, because the number of times we iterate or loop might be based on user input. But by the time we get to the loop in the program, we need to know. And there are 2 kinds of loops that we're going to use for that. We're going to use the for loop, and we'll talk this lecture and next lecture about using the for loop. And then in the third lecture, we'll talk about the for each loop. So after we're done with those lectures, we'll move on to the kind of loop that we use when we don't know in advance how many times we're going to loop. So I'm going to open up the IDE, and I already started working on a game in which we are going to spawn teddy bears. That's the master plan. We're going to spawn teddy bears. I will zoom in. And so you'll see a number of different things in the code that I started with. We have an initial number of teddy bears that we have as a constant that we can adjust as we go along. We have random teddy bear support, and this includes a list of sprites so we can randomly pick which teddy bear we want to display. And we have spawning support that we will get to in a while. And finally, we have a collection of our teddy bears. Here I'm just using a list of the teddy bears. Standard initialize stuff in the constructor and the initialize method. In the load content, I'm actually loading each of these sprites into the sprites list. I'll scroll back up. So here's a list of texture 2Ds that I'm going to use to support picking a random texture 2D for a teddy bear. And so for efficiency, rather than going off and loading this content as the game runs as I spawn teddy bears, I'm going to put them into this list so I can just grab that texture 2D when I want it, instead of going out to the disk essentially and loading that content again. So this comment here says create initial game objects. So what that means is I'm going to have a list of teddy bears, and I need to create the list of teddy bears. So this is our first opportunity to use a for loop, because the initial number of teddy bears here is set to 1, but the initial number of teddy bears could easily be 20. And so I want to create however many teddy bears this is, and I do that repeatedly. I want to do the same thing time after time, and so that's a great opportunity to use a for loop. So here's how the for loop works. We type the word for. I'm going to immediately open the parentheses and open the curly braces for the for. And now I'll come back and add the different components that are required for a for loop. The first thing is the initializer. I need to initialize something called the loop control variable. So this loop control variable is, brace yourselves, it is a variable that we use to control the loop. So that's why it's called the loop control variable. And I give it a data type. And it is very, very common to use I as the loop control variable, or I and j if you're doing 2 dimensions, or row and column if you're doing 2 dimensions, or ijk if you're doing 3 dimensions, and so on. So we'll use I, and we'll start I at 0. So a lot of this syntax you've already seen before. This really looks like, because it is, this really looks like declaring and initializing a variable, because that's exactly what we're doing. We're declaring a variable I that is of data type int, and we're starting it at 0. Next thing I'm going to do is I'm going to say what the test or conditional is for this particular for loop. And I'm going to say I want to keep looping as long as I is less than the initial num teddies. Now you might think I should use less than or equal to, but since I'm starting I at 0, with initial num teddies being 1, I will be 0. It'll say, is 0 less than 1? It'll say yes. It'll go into the body of the loop and do whatever I tell it to do. And then it does that final thing, and I need to add a modifier. I need to say each time when I'm done with the loop, before I do this test, how do I want to change I, the loop control variable? So here I have said I++, which just says increment I, add 1 to I. So the way this will work, with initial num teddies being 1, the way this will work is it'll start I at 0, it'll come do the stuff that I haven't put yet, and then it will come back and it will use the modifier to add 1 to I. So now I is 1. And it compares here, it does the test, and it says, is 1 less than 1? And the answer is no. So we're all done with the loop, so we come down past the loop. So that's how the for loop works. Let's do something here. Let's take our bears collection, and because it's a list, I have an add, and I have a method that I wrote called getRandomTeddyBear. And we'll go take a look at that method, but the details of that method aren't really very important right now, but we'll go take a look. So, by the way, just sort of using Visual Studio some more, if I right-click on this, I can go to definition about halfway down, and that brings me immediately to the definition of that method. So I don't have to scroll down through my code, I can just go directly there. Remember our sprites collection? I am randomly picking one. We talked about this before in the value of using arrays and collections. And then I just create a new teddy bear object. I have a class over here called teddy bear. And I create a new teddy bear with the sprite I just picked, a random location that is within the window, and the window width and window height so the teddy bear can bounce around. I'll go back to where I was before. There are a couple of ways to do this. I could do find all references, or if I come over here to this drop down, this is a list of all the methods and the fields in this particular class. So we were in the load content method, so I can just go to the load content method directly. That's just navigating the IDE. Okay, so we've created these game objects, and if I F5, we get the cornflower blue screen with nothing shown because I'm not drawing any of these things. So let's go to the draw method. I already added the sprite batch begin and sprite batch end, but this is another place for us to use a for loop. And I'm going to use, at this point, I will fill in the parts that are the same. So I'm going to still start I at 0, and I'm still going to increment I each time. However, here, my test is that I is less than something. So it's no longer initial num teddies, especially when it comes time for me to start spawning teddy bears. So I don't want to use that constant. This is why I'm using a list, because the number of teddy bears is not going to be constant. And so I don't want to use that constant. Instead, I want to say, I want to make sure I do this action on every single teddy bear that's in that list. And it turns out that the list class gives us a property called count. And that property called count is the count of the teddy bears that are in the list. So this will start I at 0. And that was a horrible thing to do, so let me take that back and to do this instead. So we'll say bears. Remember, we index into the elements of a list just like we did with an array using the square brackets. And we'll tell bears I to draw itself. Like that. And so first time through this loop, I will be 0. So bears 0, the first element in that list, will draw itself. Then I'll come around to the top of the loop. I'll add 1 to I, so now I is 1. And as long as I is less than however many things are in that list, it'll come down here. So now bears 1 will draw itself, and so on. So for loops are a great way to actually sort of walk an array or walk a collection and do something to, or tell each element in that collection to do to itself something. right? So now if I F5, I actually have the teddy bear draw itself. He's not moving around because I'm not updating him, but he's drawing himself. And just to show you how that first for loop really works, if we change this, we could say we want to start with 100 teddy bears instead. And if I F5 now, I start with 100 teddy bears. Please don't spend time counting them. Trust me, there's 100 there. Okay, so we'll start with 1. And so the last thing I want to do is I want to get these things bouncing around. So down here in update, I'll skip the spawn teddies as appropriate for the moment, and we'll update those teddy bears. So guess what? Another for loop. And this is identical to the one in the draw. I less than bears.count. I plus plus. And this time, we'll tell all those teddy bears to update themselves. So bears, I. Update yourself. And I need to provide one argument, the game time, because I have these bears updating based on their velocity and how many milliseconds have elapsed. So this is sort of like real physics. But luckily we have game time available because it's a parameter that gets passed into the update method. So we can pass that same game time information to the bear update method. And now if I F5, I get a bear that bounces around. So let's go back to the PowerPoint briefly so that you can do some in-lecture quizzes. So go do all 3 of these coming up are about the terminology we talked about for loops. So go ahead and do this first one. And now go ahead and do the second one. And finally, go ahead and do the third one. All right, so let's add one more thing to our code here. I would like to spawn teddy bears so we don't just sort of keep the initial number forever, we actually spawn more. And this pattern that we're about to use, you've already seen before. When we were running animations and we had to decide to move from one frame of the animation to the next, that was exactly the same pattern. It's that timer that I talked about that we use all the time in game development. So I'll scroll to the top of the Game 1 class again just to show the spawning support. So we have elapsed spawn delay milliseconds. So how long has it been since we spawned something? 0. And we have total spawn delay milliseconds. So this will spawn a new teddy bear every second, every 1,000 milliseconds. So we're going back to the update method. First thing we'll do is we'll update the elapsed spawn delay milliseconds. We'll say plus equal, that shortcut for just adding to elapsed spawn delay milliseconds. And we'll access the game time. And we'll say how long since this update method has been called. And we want the milliseconds for it. So now we've updated how long it's been in milliseconds since we spawned a teddy bear. And now we check to see if it's time to spawn another one. So if the elapsed spawn delay milliseconds is greater than or equal to the total, then it's time to spawn a new teddy bear. Be sure to reset the timer. Otherwise, we're going to spawn a whole bunch of teddy bears really quickly. Maybe I'll show you that in a second. And to spawn a teddy bear, we just add it to the list. So let's add another get random teddy bear. If I F5, every second, I get a new teddy bear spawned. If I forgot to reset the timer, if I F5, nothing happens for a second, and then suddenly we're spawning, 60 a second, basically. So it's important to remember to reset the timer, and that's what we've done there. So let's go. That is for loops. Right? That is what we need to know for loops. We're actually going to, in the next lecture, we're going to do another thing with for loops. And it'll be a slightly different way that we're going to use for loops. And you'll just have to sort of wait and see what's going to happen then. But that's it for the code that we're going to write today. So let's go back to the PowerPoint slides so you can do another in-lecture quiz. So that in-lecture quiz demonstrates to you that the loop control variable doesn't always have to start at 0. The modification of the loop control variable doesn't always have to be just an increment to add 1. And the test can be virtually anything. So you should realize that the first 3 choices were all correct. All 3 of those first loops execute exactly 10 times. It's just different forms of using the for loop. So to recap from today, we learned how we can execute a number or the loop body, a set of statements multiple times using a for loop when we know how many times we need to loop by the time we get to the loop. Next time, we're going to use the for loop in a different way, like I said, and I'm sorry to tell you that dead teddy bears will be involved. So stay tuned and make sure you come back for the next one. Continuing with our Module 10 work, where we're talking about iteration, what some people call looping, here's a reminder of the Module 10 learning objectives. So last time, we talked about how we could use for loops to iterate a particular number of times, to do the statements that are in the loop body as many times as we should based on the loop control variable, the test or conditional, and the modifier of that loop control variable. So this time, we're going to continue with our for loop work, and we're going to use for loops to solve a standard problem that we regularly encounter in game development. So we'll start, of course, with an in-lecture quiz. I lied to you. We won't at all start with an in-lecture quiz. We'll start by talking about the problem first. So, what's the problem? Here's the problem. It's sad for me to tell you this, but teddy bears don't live forever. Some teddy bears wear out. Some teddy bears have a life timer that expires and then the teddy bear is dead. And so for today's code, I've actually added a timer to our teddy bear class, which I'll show you, and we'll see that teddy bears only live for a certain period of time in the game. So what's the problem? We add them to a list and we update and draw them and all that cool stuff. The issue is that once they're dead, once they're inactive, we should not keep updating and drawing them because it wastes time. We don't want to waste CPU cycles processing game entities that are no longer active in the game. And so what we want to do is once those teddies are dead, we want to remove them from the list of teddy bears that keeps getting updated and drawn. And that will save us CPU cycles. Of course, this is a general idea, right? It's not just about teddy bears. It's about any game entities that become inactive and removing them from the list of active game entities. Now, because I know you've been waiting with bated breath, now go do an in-lecture quiz. Okay, so it is a very bad idea to actually try to go from the beginning of the list to the end of the list if we think we're going to remove stuff from the list along the way. And we're going to walk through a short, small example here to see why that's the case. So remember, this is the counter example. This is what we do not want to do, and we're looking at why we don't want to do it. Even though we often start for loops at the beginning and go to the end. Those are the only kinds of for loops we used last time. But if in fact we think we're going to remove something from the list, or there's a possibility that we'll remove something, we want to go not front to back. Okay, so let's see how a front to back loop would work on a list of 4 teddy bears, 2 of which are dead, so should be removed from the list. So the first time through the loop, we set I equal to 0. The count, the number of teddy bears, remember that count property for the list class? The count of teddy bears is 4. And we look at the 0th element, the first teddy bear, but the 0th element. And that teddy bear is alive. It doesn't have a red X across it, which is the way I'm indicating dead teddy bears. There are lots of other disgusting ways to do it, but I just used a red X. So the first one we look at is live. So everything's good. We don't do anything. And we move along the list. So now, on the second loop iteration, we have I equal to 1, count is still 4, and that magenta rectangle, by the way, is showing which element of the list we're looking at. And this time we're looking at a dead teddy bear. And so we're going to remove that dead teddy bear. What's going to happen is these two are going to get shifted over. When we take this one out of the list, that's a beautiful arrow. When we take that one out of the list, these two are going to get shifted over this way. And so I'll get rid of all that writing momentarily. So what happens is now on the third iteration, look what's happened. I is equal to 2. Count is 3 because we removed one from the list. So this is our last iteration from the loop. And we're looking at the live teddy bear that got shifted into element 2. And the big problem, of course, is we have a dead teddy bear here that we missed. So if in fact, because we shifted them, right? Because we slid those two over, we ended up missing the dead teddy bear that I've circled here. And so if we're in fact going to modify the contents of the list, front to back is definitely not the way to go. So let's look at the right way to go after you do another in-lecture quiz. Hopefully you did not pick the last answer. The rest of them were right. The way we do this is if we're going to remove stuff from the list, we start at the back and move toward the front. And in case you don't realize why that works correctly, let's look at the example again, except this time we're looping from the back to the front. So we're starting I at 3, which is the last element in this list. Count is 4. And we're looking at a live teddy bear, so we don't need to do anything on this iteration. We go to the next iteration. So we're subtracting 1 from I to go backwards each time instead of adding 1 to I. So now I is 2. And we're looking at a dead teddy bear. And we're going to remove it just like we did before. And what will happen is this guy right here is going to get shifted over 1. Like so. So he's going to get moved over. The reason we don't care is because on the next iteration of the loop, we see that I is 1, so we're looking at the one in the middle. We don't care that we shifted that other one because we'd already looked at it anyway. We'd already processed that teddy bear, so we didn't care that it moved, and we aren't missing any. We're now looking at the other dead teddy bear. And so with I equal to 1 and count equal to 3, we're looking at that dead teddy bear and we're going to remove it. And so now we go one more iteration. I is 0, count is 2. And really our test here is actually making sure that I is greater than or equal to 0. So we really don't care about the count changing if we go backwards. But I've included it just because I included it in the other example as well. And so now, last iteration of the loop, you'll notice we do 4 iterations, which is good because there were 4 teddy bears. In the previous example, where we went forward, we only did 3 iterations with 4 teddy bears. And that was what caused the problem, really. The shifting and the not doing enough iterations for all the bears. Both of those combined to indicate that we didn't process all the teddy bears in the list. So going backwards is definitely the way to do it. So let's actually go look at some code. So first, I promised you I would show you the code that looks at or makes the teddy bear expire. So in the teddy bear code, I have some life support. So I have total life milliseconds, 3 seconds. Teddy bears live for 3 seconds. That's how it works. And I have elapsed life milliseconds, so a timer. We've seen timers, right? We use timers all the time. And so when I update the teddy bear here, one of the things I do is I check for death. And so I'm doing the elapsed life milliseconds. I'm adding how many milliseconds have elapsed since the last time the update method was called. And then if the time that the teddy bear has been alive is greater than or equal to the total time it stays alive, I make the teddy bear inactive. That's how we're identifying dead teddy bears, is because they're inactive. So back here in the Game 1 class, the only place we're going to add code today is here where we're going to remove the dead teddy bears. So it's going to be a for loop still. But this time it's going to go backwards. So we have to start I at the end of the list, and the index for the element at the end of the list is bears.count -1 because it's 0 based. Remember, if there are 4 things in the list, the index of the last thing is 3. So that's why we subtract 1. We're going to check, as I said, I greater than or equal to 0, so that we make sure we go all the way to the front of the list but no further. And the modifier, as I also said, is I minus minus instead of I plus plus. So we're going to reduce I by 1 each time through the loop rather than increment it by 1. Decrement is the word for reduce by 1. Okay, so inside the loop, I need to see if the teddy bear is dead. So the way I'm going to do that is I'm going to say if bears I dot, well, I'll show you the wrong way and then I'll show you the right way. If bears dot active equal false, we're going to do something. But there's a cleaner way to do this, and that cleaner way to do it is to say if not bears dot active. So I don't have to compare it to false. I'll just not the property. So if this is true, if active is true, not true is false. So we've identified a dead teddy bear. Let's get rid of it. The way we get rid of it is we use the method for lists called remove at, and we provide the index of the element at which we want removed. Wow, that's not English, so here's what I mean. We give it the index of the thing we want to remove, and it will remove that thing. So now I'm going to F5 and show you it spawns teddy bears, and they're going to start disappearing. If you watch them, they disappear. And we always end up with 3 on the screen because it's 3 seconds and it's spawning every second and so on. So that's why there's 3, but they're a different 3, as you can see by the colors changing. Now, you might say, well, you claim that you're actually removing teddy bears, but I don't know if that's true. So let's put a breakpoint here. And so now when I F5, the first time I go to remove the dead teddy bear, it's going to stop at that breakpoint. So as you can see, I'm actually removing the teddy bears as we go along. And we'll F5 all the way to the end and then stop. So that's, again, all the code we're going to write. But this is, boy, this is a standard problem in game development, is how do we maintain these lists of active game entities and make sure we remove the ones that are no longer active for efficiency. So go backwards through the list when you're going to take something out. Next time, we're going to learn about the for each loop, which is another way that we can iterate through an array or collection to do processing on the elements of that array or collection. We're halfway through Module 10 already. Here's a reminder of the Module 10 learning objectives. So last time, remember we used a for loop to clean dead teddy bears out of a list. This time we're going to look at a different kind of loop called a for each loop that we can use to iterate over the elements in an array or a collection. Starting with an in-lecture quiz. So it is the default in C# that we use the for each loop whenever it's possible. It's not always possible, and this really isn't even a C# standard. It's just sort of, in general, you will find most C# programmers using a for each loop whenever they can. So what are some of those situations in which a for loop is the only thing we can use? Go ahead and do another in-lecture quiz. Now I'm going to start up Visual Studio and zoom in. And what we're going to do is we're going to go through the code we used for loops for last time, and we're going to convert the ones that we can convert into for each loops. So we'll start at the top and scroll our way down. This first one is a for loop that needs to go a certain number of times, specifically initial num teddies times. adding a new teddy bear each time. So we do not, in this case, have an array or a collection over which we're trying to iterate. So that's one of the cases where we need to use a for loop, not a for each loop. So we can't use a for each loop here. We need to leave this one as a for loop. Down here, where we're going to update, I say and blow up, not quite yet, relax. We'll blow up teddy bears, of course, just not quite yet. So the question is, can we in fact update and blow up these teddy bears using a for each loop instead? And the answer is yes. In this particular case, we are iterating over a collection or an array, in this case a collection, a list of bears. And in here, we're not going to remove anything from the collection. That's actually another place where we can't use a for each loop, is if we're going to change the contents of the collection. But we're not changing the contents of the collection here, so let's convert this to a for each loop. So we say new syntax, we say for each, and the first thing that we put is the data type of the elements in the collection over which we're iterating. So this is a list of teddy bears, so it's teddy bear, the data type. Next thing we do is we put a variable name. I'm going to call it teddy bear with a small t. And so this, well, we'll talk about how this works in a moment. So and now we put the collection name. So data type of the elements in the collection or array, a variable that will access inside the loop body, the keyword in, and then the name of the array or collection over which we're iterating. So I said for this, it's a variable that we're going to refer to in the loop body. So basically, instead of talking about bear's eye, notice we have a red squiggly under the eye now because we don't have an eye anymore. Sorry. So now we're going to actually access teddy bear, that variable, instead. So here's how it works. The first time through this for each loop, the variable teddy bear is set to bears 0. Same exact thing. So this first time through the loop, this is really bears 0 update. We come around again. If there's more stuff in the collection, teddy bear gets set to the element at index 1. So now it's bears 1. So bears 1 gets updated, and so on. And we don't have to sort of worry about the less than or equal on a count or anything like that, because the for each loop automatically just basically touches each element starting from the beginning going to the end. So that's a conversion of this for loop to a for each loop. Removing dead teddy bears, we cannot convert to a for each loop because we are removing from the collection. And it's interesting, if you try to do a for each loop where you change the collection you're looping over, it will compile and it will run and it will blow up when it hits the part where you actually change the collection. So this is one of those cases where the compiler won't catch it for you. You're going to end up with a crash at runtime. Okay, so we can definitely convert the drawing into a for each loop. Same exact way. Teddy bear. And this becomes teddy bear draw. Because, again, we're not changing the contents and we're going across the collection. And that's it. I thought I skipped one, but I didn't. So the ones we could convert were here in update and here in draw. But there were a couple that we could not convert because of the way for each loops work. So let's go back to the slides, or really just back to my talking head while you do an in-lecture quiz to make sure you understand a very important constraint of using for each loops. And then another in-lecture quiz where you actually evaluate another for each loop, this one over an array, not a collection. So in case it wasn't clear, the last two answers there are correct. It will update each of the array elements However, we talked about why collections are sometimes better than arrays, and this is one of those cases. If one of those array elements is actually null, you're going to have a crash, or it's going to blow up. I mean, it doesn't literally blow up, but that's the terminology we use. Okay, so speaking of blowing up, you have what you need for for loops and for each loops at this point. So you could sort of stop this lecture and say, there, I know about those kinds of loops. However, I would like to interact with these teddy bears by blowing them up. And so I'm going to blow them up by sweeping the mouse over them. I know it's cheesy and it's easy and that's all okay. I'm going to blow them up by sweeping the mouse over them. So let's add that structure to the game as well. So we'll blow up teddy bears. I've been waiting so long to blow up teddy bears explicitly during a lecture. Okay, so first of all, remember up here in the Game 1 class, we have a list of teddy bears. I have now added a list of explosions because I want a list, not just one, because we could have multiple teddy bears blowing up at the same time. Oh, that'll be awesome. Maybe I'll figure out a way to do that before we're done. And so I'm going to need a list of explosions as well. Now, this is really uncommon. If we got to sort of a commercial level game, having different lists for every single data type for the different game entities is crazy. Unfortunately, we haven't learned about something called inheritance yet. So really what would happen is we'd have a whole bunch of game objects, and then we'd have specialized kinds of game objects like teddy bears and explosions. And our list here would be a list of game objects. We're not going to hit that in this course at all, but inheritance is a very powerful capability that we use in object-oriented programming to make stuff like this not necessary. We'll just live with it because all we have are teddy bears and explosions. Okay, so we load content. I've added one more. I snuck by it before. I'm saving the explosion sprite as well. That way I just load it once. And now I'm going to get user input. So if I'm going to sweep the mouse across teddy bears, I'll need the current mouse state. So here, inside this loop, I'm still not going to change the collection of teddy bears. I'm just going to change whether they are active or not and add an explosion as appropriate. And the way I'm going to do that is if, in fact, the collision rectangle for the teddy bear contains the mouse, the X and Y location of the mouse. So I'll have an if statement accessing the current element of the collection right now by using this variable, just like I did here. I access it here as well. And just as I could access the update method, I access the collision rectangle property. Now rectangles have a method called contains, and it's overloaded. There's a whole bunch of different things we can provide. And one of the things we can provide is the mouse X and the mouse Y. So this test, this method here will return true if the collision rectangle for the teddy bear contains mouse X and mouse Y, which means that X and Y is on top of the collision rectangle for the teddy bear. It's not pixel perfect, but it's close enough for this game. Two things happen if I sweep the mouse across a teddy bear. First of all, the teddy bear dies. So we'll make the active property of the teddy bear false. So the teddy bear is no longer, it's a dead teddy, and it'll get cleaned out soon when we remove dead teddies. And I also want to create a new explosion and add it to the explosions list. So explosions.add, and I need a new explosion. And this custom explosion class that I wrote and included in this project requires 3 things to be handed in. The explosion sprite, which is really a sprite strip for the animation, and an X and a Y for where we want the center of the explosion to play. And I want the center of the explosion to play at the center of the teddy bear. So that is teddy bear, collision rectangle. Rectangles have a center property that have an X and a Y. So if I access those in this way, then I can play the explosion in the center of the teddy bear. Like so. And at this point, if we in fact run the code, we'll see that when I sweep across teddy bears, they disappear, they're dead, but there's no explosion, which is very disappointing for me personally, but they are dying and getting cleaned out. So this technique of writing a little bit of code and then writing a little more test is absolutely the right way to go. We have 3 more things we need to do. We need to update the explosions. We need to remove the dead explosions, which may seem really freakishly weird to you, but once they're inactive. And we need to draw them. So let's actually draw the explosions here so that we can at least start seeing those explosions. So this time it's for each explosion, and I'll call the variable for inside the for each loop body explosion with a small e. In the collection explosions, I'm going to do something, and I'm going to tell the explosion to draw itself. So now what we're going to think about, stop for a moment and think about what you think is going to happen, and then I'll run it and show you. So there, I'm basically creating the explosions, but I'm not updating them, so they're not playing as animations, and I'm not ever making them inactive when the animation fills. So we have all these first frames of explosions. It's fun, I like it, and we could even add, if a teddy bear runs into an explosion, then it explodes, and that would be awesome too. But we're not gonna. Instead, we're gonna come here and update each of the explosions, and that's gonna be very similar to updating the teddy bears. We don't blow up explosions, that makes no sense, but we will update them so that they're playing through the frames in their animations. Same kind of for each loop that we saw below in the draw. Except this time we're going to tell each explosion to update itself using game time. F5'd again, so now when I do it, they play and disappear. So the only thing we have left is an inefficiency, and the inefficiency is that I haven't cleared out the dead explosions. And I can do that in the same exact way that I did for the bears, except this time, of course, I use the explosions collection count -1, not 12. That would be a horrible way to do it. I greater than equal to 0, and I minus minus for going backwards through the list. And this time, if the explosions I isn't active, not if it is active, so I got to go over here and put the not. If it's not active, then I'm going to remove it from the list of explosions using remove at, just like above. So now, again, you don't see this, but it is in fact removing the explosions. Now I made the claim that we could have multiple explosions playing at the same time, and I haven't really managed this, though, when I was playing. Yes, I was playing this before I did this lecture, and I did get a couple of teddy bears at the same time, but there's an easy way for me to set it up that I can sweep across multiple at a time. I'll start with a whole bunch. So now when I sweep across a bunch, you'll see I've got multiple explosions happening at the same. Wow, and now, of course, a bunch have died off after 3 seconds. That's too bad, because I was enjoying that. So let's start with 1,000 just so we can see even more. So lots of explosions playing at the same time, and then, they all die after 3 seconds, and then I only get a few. So I'll go back to 1 here for when I give it to you. So that's it for the code for today. I want to send you to do one more in-lecture quiz. So go answer this in-lecture quiz about a topic we haven't talked about today. So nested loops, which we really haven't covered. They're covered in the book, but we haven't covered them here. We can put any statements inside a loop we want, including another loop. Just as for if statements, we could have put other if statements inside the if clause of, an outer if statement and so on. We can nest loops inside each other. And this is really helpful. For example, say we have a two-dimensional array for a game board, for tic-tac-toe or something. We would want to touch every square on the board. We'd want to go first on every, it doesn't matter, the order doesn't matter. But usually we would start at row 0 and then look at each column in row 0, and then we'd move to row 1 and look at each column in row 1, and so on. And so the one really effective way to do that is to use nested loops. So we put a for loop that walks the rows, and then inside that for loop we put a for loop that walks the columns, and then inside that for loop we do whatever we want to do to each of the squares on the board. So they're not smelly, and they certainly don't have twigs and birds and stuff in them. They're actually a really useful way to, in general, do two-dimensional or multi-dimensional kinds of things, is where we usually see them. Okay, so to recap, the last 3 lectures really have been all about when we get to a loop, we know how many times we need to loop. Either because we've stored a number somewhere, like the initial number of bears that we were going to generate, or because we have a particular array or collection over which we're going to iterate, and so we know the number of times we're going to loop is the number of elements in that particular array or collection. Usually we're going to pick a for each loop, but we've seen multiple times where, in fact, based on the limitations of for each loops, we're going to need to use a for loop instead. Next time, we're actually going to start talking and finish talking about the loop that we use when we don't know how many times we're going to iterate when we get to the loop. So we've made it to the end of Module 10 about iteration, what some people call looping. So last look at the module learning objectives. So last time we finished our discussion about for and for each loops, the loops that we use when we know how many times we're going to loop when we get to the loop as the program executes. This time we're going to look at while loops, which are loops that we use when we don't know how many times we're going to iterate. So just to see if you've paid attention to what I said over the last 30 seconds, here's an in-lecture quiz for you. So I've started a program that we're going to start looking at. Before I do, I want to talk about sort of a standard problem that we solve using while loops. So input validation means making sure that whoever is using our software has entered valid data when we ask for it. And the reason we need a while loop here, rather than a for or for each loop, or even just an if statement, is because we don't know how stupid the user is. They could enter invalid inputs 10 times before they finally enter a valid one. And so a while loop is a great choice for doing input validation. So I'll open up our project. I've already added a little bit of code. So this is a console application, darned no graphics or explosions or anything like that. So we have a menu here, and the user can enter J for jump, C for crouch, or Q for quit. We have the standard prompt and reading in that we've done before. I will point out that the console read line gives us a string, and I'm calling the toUpper method on that string so that we turn all the characters in the string to uppercase, and hopefully that's only one character because we're going to do a char.parse on it and put it into this choice variable. So we know when we get here, as long as the user doesn't do something super stupid, we're going to end up with an uppercase single character. So I'm going to control F5 to run this just to show that I can do that, but I can also enter, D, and it's okay, it gets to the end. So for this example, we're not actually going to do anything with their menu choice. We're just going to make sure that they've entered a valid one so that when we get to this point in the code where this cursor is, we know that we have a valid input. So how do we validate input? Well, what we need to do is we need to make sure that as long as the user has entered invalid input, that we can, in fact, give them an error message, give them the menu again, and get a new input from them. And so we're going to use a while loop for that. And I'll put the structure in first, like that. So what goes here is a Boolean expression that when it evaluates to true, we want to go into the loop body and do whatever happens in there. So let's say we know what the valid choices are. The valid choices are capital J, C, or Q. So the Boolean expression here needs to evaluate to true when the input is invalid, which means that choice is not equal to J and choice is not equal to C and choice is not equal to Q. So if it's the case that they haven't entered a J and they haven't entered a C and they haven't entered a Q, then we know they've given us invalid input and we need to get valid input from them. So the first thing we'll do is print an error message. And you can be as nice or as mean with this error message as you want. I'll be reasonably nice and just say invalid input must be J, C, or Q. You could call them names if you want to and so on. I'm going to add a couple of lines in the output to set the error message off from the menu and from where they entered their choice. And now I need to print the menu again and get their choice again. And I'm going to copy and paste, even though I hate doing that. Once we learn how to write our own methods, we'll see that this whole copy-paste thing doesn't really need to be done anymore by us. And of course, I have to not declare the choice variable again. So now what will happen is I'm going to print the menu and get their choice. And then I'm going to check to see if their choice is invalid with this Boolean expression. If it is, I'm going to print their error message. I'm going to give them the menu and ask for their choice again. And then when I reach, we are gathered here today. When I reach this closing curly brace, I'm going to loop back to the top of the while loop and I'm going to evaluate this Boolean expression again. And if it's true again, because the user is an idiot, then I'm going to go into the loop again. So I will keep looping through this while loop until they've entered a valid input, at which point I'll get here and I'll know it's valid. So let's Control F5. I'll enter some invalid inputs, D, 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 but then when I finally enter a valid one, J, it gets past the while loop because this Boolean expression here now evaluates to false. And so it gets past the while loop and I get to the end of my program. So before we continue, you should go do an in-lecture quiz that talks about or asks you about infinite loops. And now you should do another in-lecture quiz that asks you about an acronym that can help us solve the infinite loop problem. Great. Now, infinite loops are not really infinite, right? At some point, the sun will explode or our computer will burn up or we'll get so angry that we'll, throw it against a wall or something. But they're really called infinite loops because they don't terminate when they really should, with sort of normal behavior. So let's show how initialize, test, and modify all three matter when avoiding infinite loops. It actually turns out that in this particular case, the initialize thing doesn't lead to an infinite loop, it just leads to nasty behavior. So let's say that I have in fact declared my choice variable and initialized it to some invalid choice at the beginning of the main method, and then I don't actually initialize it by getting input from the user. What happens when I run is that it immediately says that I'm a moron and gives me the message again, which is really bad for users, right? That's not the appropriate way to do it. That's kind of a poor example of how initialize leads to an infinite loop, because in fact it does not here. So just trust me that sometimes initialize is the problem. Let's actually look at test and modify, because those are way better examples here in this particular example that we're working through. So let's say we got this test wrong. Let's say we've gotten confused about and versus or. And so here we've put ors instead of ands. So we've messed up the test. The test is invalid for the loop. And this is going to lead us to an infinite loop. So I'll control F5 and I will enter an invalid input. And I say, oh darn, I should have read the menu. And I enter J. And wow, I'm looping again. So like any good programmer, I'll do exactly the same thing and expect a different result. That's the sign of madness. Except in the context of software, it's not the sign of madness, because something's different. The state of the computer, the memory, something is in fact different. We're mad as programmers, but not because we try the same thing multiple times. Okay, so now I'm stuck, right? Even though I'm entering valid inputs, I can't get out. So I'll use the red X. Here's what's happening. When I entered J, this part of the Boolean expression, J not equal to J, was in fact false. Good. The problem is, then I got to this part, and J not equal to C is true. And the way that ORs work, right, is that any of them can be true to make the whole thing true, which pushes us into the loop again. So that's how a test can, an incorrect test in our Boolean expression for the while loop can lead to an infinite loop. Let's hit the M part of the acronym. So if we forgot to modify, so I'll comment this out. If we forgot to modify the loop control variable, let's watch what happens. I'll control F5, and now I'll enter a bad one, D, and oh dear, loop, 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 forever until I rage quit. So what's happening there, I'm going to fix this before I forget. What's happening there is, if I got into the loop, this Boolean expression evaluated to true. That's the only way I got into the loop body, was because this was true. So if I don't change choice inside the loop, when I get to the end of the loop here, and I come back around and check it again, it's true again, because nothing changed. I never changed choice. So I'm stuck in this infinite loop because I didn't modify the variable that I'm using in my test. Sometimes we have multiple variables in our test, but the concept still applies. At least one of those variables has to get changed inside the loop body. Otherwise, we're guaranteed to end up with an infinite loop, because if we got into the loop body the first time, we're going to get into it forever. Okay, so one last, that's it for the code for today. Those are while loops, and input validation tends to be the most common place we use them, but there are other places we find to use them as well. So go do one more in-lecture quiz about actually testing while loops. Okay, so when we test while loops, it makes sense to run it so the loop body executes 0 times. And I did that. I may not have done that, but I meant to do that by entering a valid input right away. So then the Boolean expression in the while loop evaluated to false when we got to it the first time, so I just skipped the loop body. You should also execute it once, which we saw numerous times where I'd enter D and then J or something like that. And then you should execute it multiple times. Try a few invalid inputs followed by a valid one. The reason for this is that the sort of most common errors that people find in the while loops that they write occur because they got the test not quite right. And so when you go for a 0 run, basically you end up going into the loop instead, and so you modify your test. You might, trying it once, we'd certainly catch the you forgot to modify it thing, and you end up with an infinite loop. So if you have a test case that runs that while loop body that goes into the while loop body once, you'll catch that. And sometimes, much more rarely, we have a few iterations of the loop and then the loop breaks. But that is more rare, certainly, than the first two. So that's a way to actually test, to do a good test of code that has a while loop. So to recap, for today, we actually covered how we can use a while loop to iterate an unknown number of times because it's based on some condition rather than a count. It's not how many things are in the collection, it's how many times is the user in moron. That's the end of Module 10. So we're all done with iteration, again, what a lot of people call looping. We're all done with iteration, and you now have all three control structures you need to solve all kinds of problems in your game development. Next time, we're going to move on to the next module where we're going to start designing and building a custom class of our own. So we finally reached Module 11, where we'll actually start designing and implementing our own classes. Here are the learning objectives for Module 11. In all the weeks up until this point, we've been focused on using classes that are provided by C# or by XNA or by me in the course materials. And so that's an important first step with dealing in object-oriented systems, learning how to use classes and objects that are available to you because of work other people have done. Now it's time for us to start actually working on the design and implementation of our own classes. And so that's what we'll do within this module. We'll do a class for a console application, and then we'll do a class for an XNA game as well. You should recall from way back in Module 4 that objects have three different things. They have state, they have behavior, and they have identity. And so the state of an object is all about the characteristics of that object. So you should go do an in-lecture quiz about demonstrating that you remember how we actually store the state of an object. And now you should do another in-lecture quiz that demonstrates that you remember how we actually provide consumers of the class that the object is an instance of, how we provide consumers access to the state of that object. Okay, so the next thing that we worry about or need to be concerned with is the behavior of the object. So what can that object do? Or, interestingly enough, what can we tell the object to do to itself? So another in-lecture quiz to demonstrate that you remember how we do that part in C#. And finally, we have identity. Well, objects have identity. We do too, but objects have identity. So this lets us distinguish one object from another. And so the third thing we need for objects is, of course, identity. And we will actually get identity when we call the constructor to create a new object. So let's build a die class. A die is a thing that we roll. It has a certain number of faces, and so we'll come up with a design for a die that corresponds to a die in the real world. And so first, we'll start with state. What are the kinds of things that we need to store for state in the die class? Well, we need to remember how many sides a die has. So a standard die has 6 sides. But if you happen to be a Dungeons & Dragons player, maybe you think a standard die has 20 sides. And so we need to store within the die how many sides it has. And we'll tell it how many sides it has when we actually construct the die object, just as the die factory determines how many faces are on the die when they actually build the die in, a physical die. So we'll have to keep track of that for state, how many sides there are. And we'll also need to keep track of which side is on top, because typically people will use one or more dice for a game. And so you roll the dice and you look at the number that's on top and you do something with it, whether you pay money or you move forward on a board, or the orc has slashed you fatally or whatever. But we use the number on the top of the die for some particular reason. So we're going to need to store that as well. And so, as you know from the earlier in-lecture quizzes and your work with C# so far, we're going to store the state of the object in fields, and then we're going to provide consumers access to the state of the object through properties. Next thing is behavior, and we're only going to do one thing for behavior. We are going to tell the die to roll itself. So that's how we'll use dice. We'll tell a die to roll itself, and then we'll look at the top side and say, oh, okay, now I know it's facing up, and take the appropriate action based on the game we're playing. And finally, we of course give each die object identity, and that will happen when we call the constructor to actually build the die object. So sort of pictorially, this is what we've come up with. So remember the information hiding thing. We're going to hide the fields, num sides and top side, in the internals of the object. So a consumer of the object can't see those things. And that way, if we decide we want to change how we represent those things later, we can, without affecting any consumers of the object. So that's the information hiding part. Encapsulation, remember, is putting the data, that stuff in the inner hole of the donut, I must be hungry right now, the inner hole of the donut, encapsulating the data along with the behavior. And the behavior in our case is rolling the die as a method. And that capsule, the membrane of the capsule, also makes it so that consumers access the data through those two properties. So they get at the behavior through the method, and then they get at the data through the properties. That previous picture was not in any standard pictorial form. This is in fact the UML diagram for the class that we're going to build. So as you can see, we have the fields that we'll use to store the state internally. And then we have the properties that a consumer of the class will use to access that state. And then finally we have the method, so they can also get at the behaviors. We typically do not include the constructor, one or more constructors, in the UML diagram, so I haven't done that here, but understand that of course we'll have at least one constructor so that we can in fact create new instances of the class. So now let's actually start doing this. So I'm going to start up Visual Studio. Now we're going to start a new project. This one's going to be a console application. So I'll say it's a new project, a console application, and I'll call it die. Okay. I guess I can't. I'll call it die example. I can't bring myself to just call it die. So I'm going to create this new project. I'm going to zoom in immediately, and I'm going to save. So I will go save, and then we'll jump back into the video. Okay, so I have saved it, and I also snuck in and added comments. Almost all the comments that I should have added. There we go. So we want to actually create a new class, which means we need a new file. And so over here, where it says die example, the bold-faced, this is the project, I right-click that, and I say add a new item at the top, or pick the class at the bottom. It's so common for us to add classes that we get our very own option in the drop-down for that. I am going to add a class, and I'm going to rename it die with a capital D. And I'm going to zoom in. And so this is a die. Now, I will F6 just to demonstrate that everything still works. Now, the first thing I'm going to do is add the fields for the class. So I'm going to add a region. And remember that region, using regions is just for within the IDE. It has nothing to do with what gets executed when we actually compile and run our code. And so I knew that I needed two things for fields. I needed the number of sides for the die, and I need which side is on top. So both of those really ought to be integers. We really can't have dice with 6.5 sides. As soon as you cut it, there's an extra side. That's why diamond cutters are so rich or something. I don't know. Okay, so they're both ints. So I'll call the number of sides num sides, just as we saw in the UML. And I'll call the top side that we're saving top side, just as you'd expect from the UML. So at this point, I can compile again. But I have added both the num sides field and the top side field to this new class that I created. You should now go do an in-lecture quiz that asks about controlling access to these fields, and then come back and we'll talk about it. So a new thing that we haven't talked about yet because we haven't been developing our own classes is that there's another word that can go here before we put the data type and the variable name. Up to this point, right, this is just exactly declaring a variable because it is a variable within the class. But we can also set what's called an access modifier. So we can, if we choose to do so, we can do something like this. Say public. We could make our num sides field public, which means that any consumer of this class can directly manipulate our num sides field. And that is generally considered very bad programming practice. We don't care about it for constants. It's okay to make constants public. We don't have any right here, but it's okay to make constants public because nobody can mess them up, essentially. But making a field public, really bad idea. If we do that, we have basically taken our picture of the class and we've done this. We've said, okay, you can directly manipulate num sides, so I'm going to dig a hole. I'll break that information hiding thing so that you can tunnel your way into the core of my class and mess around with the internals. That is such a horrible idea. It is allowed by the language, but it's a terrible idea. You should never do it. Let me X this out lest you think that that's the best thing ever. So really what we want is we want all of our fields to be private. We don't want anyone external to the class to be able to see those fields in any way. And because we want them all to be private in general, and because it is such good programming practice, they're actually private by default. So really, for changing the access modifier for a field, the only way for you to mess up is if you deliberately decide to be a bad programmer. Morally bad, not just, bad code quality, just a bad person. I'll make this public. So don't do it, right? It breaks our information hiding, and there's no need to do it, because if consumers of the class need access to the state, which is what our fields are for, then we provide them access to that state through our properties, which means we should actually implement some properties. So I'm going to create another region. And here's where I'm going to implement our properties. So let's implement the numSides property first. We need to put an access modifier for the property, and because this is for consumers of the class, we want to make properties public. In general, we want to make properties public because the consumer of the class needs access to it. The numSides field is an integer, so we're probably going to want to return an integer here as well. And properties are capitalized. So just as methods are capitalized, just as class names are capitalized, properties are capitalized. We put an open and close curly bracket, and I'm going to talk about the syntax for both things that we can do within a property, and then we'll get rid of the one that's just crazy. Okay, so the two things we can get for the two things we can do for properties is read them. We say we can read the property. We implement the read capability for a property by providing a get accessor, and we can set the property. So basically, we can get the value of this state information, sorry about that, the state information, numsides, and we can set the information. So I'll implement both, and then I'll get rid of the one that's dead wrong. Okay, so to get numsides, what we're really saying is go through that picture. I'm accessing the property, and you should tell me the information that you have hidden in your core. And so that is definitely numsides. So we need to somehow get the value of the numsides variable. And we get the value of variables by just putting the variable name. But now we need a way to actually return this to the person, the consumer of the class, who's trying to access this property. And the good news is programmers are crazy, but sometimes we use appropriate words. So if we were to return something, we use the word return. And so by putting return numsides, when someone tries to access this property, we can just give them what is in that property. So that's get. That's actually get that's the read, find out. There is a write possible in properties. It's done within the set accessor. And so the way we do it is we say numsides equal, so we're trying to set the value of this field. So numsides is equal to something. And that something is a special keyword called value. When it's time, oh, you've actually already seen this, right? When you did bear.active equal false, that false part, when you are accessing a property, you are accessing the set accessor for the active property, and inside the property, which we didn't look at, but inside the property, that false that you had on the right hand side of the equal was actually called value inside. So that's how we'll see this again. Don't worry when we implement the XNA stuff, because boy, it makes sense to actually find out the number of sides on a die, but it doesn't make any sense at all to let a consumer of the class change the number of sides on the die once it's been created. What, are you going to take a file and, make new faces on the die and color them in with magic marker or something? No, definitely not. So this particular property, it only makes sense for it to have a get accessor. And we'll add a comment, gets the number of sides. Now the only other property we said we needed was the top side. So let's do that as well. And just as for numsides, it only makes sense to have a get accessor for top side. If you could roll a die and then reach over and turn it so that you got a better roll, dice games would not be nearly as interesting as you might expect. And if you want to, travel to Las Vegas and try that at the craps table, you'll probably get in trouble from the casino. Okay, so just get. We can look at the top side, but we can't change it. Okay, so same exact thing as above, except this time we'll return top side instead. And of course, we will add a comment. So that either somebody reading the source code or the documentation we generate clearly indicates what gets done. Okay, I'm going to F6. So I can build, and I can F5, or I control F5, because this is a console app and it's not exciting at all. So you might think that we should definitely test these properties right now. And while I would agree with that, the problem is we don't have any constructors yet, so we haven't created any die object yet, so we can't access the properties of a non-existent object. So we will actually start testing these properties in the next lecture. And speaking of the next lecture, this is the end of this one. So we've done our design for the die class, and we have implemented the fields and properties. So we've handled the state part of what we need from state, behavior, and identity. And next time, we'll actually build a couple of constructors for the die class. This is the second lecture in Module 11, where we're going to continue working with our die class for a console application. Here are the learning objectives for the module. So last time, we did our design on our die class. We figured out what fields, properties, and methods we were going to need. And we implemented the fields and properties, the state part of our state, behavior, and identity. In this lecture, we're going to build the constructors for the die class so that we can handle the identity part, where in fact, each object gets its own identity as an instance of the class. So that's what we're working on today. We're doing the identity thing so we can tell the difference between different objects. You've been doing this a lot throughout the class, but you should now go do an in-lecture quiz to tell me how we actually get, how each object gets their identity. So for our die class, we already did our state. We took care of the number of sides and the side that's on top. We'll do behavior next time. So this time, we're working on the constructor. Constructors, excuse me. So we'll have two. We'll create a standard die for normal people, and that has 6 sides. And then we'll have the ability to create a die with any number of sides for, I don't want to say abnormal people who need a d20, so that's unfair, but people who need dice with sides more or less than 6. So we're going to build 2 constructors. We're going to build one for the standard die, and then we're going to build one for any number of sides on the die. So I'm going to bring up the project, and this is where we ended last time. So we have the fields. I'll expand those regions. We have fields and properties. Let's add the constructors. So I'll build a region for those as well. And we'll start with the constructor that just creates a standard die. So we'll make the constructor public so that consumers of this constructor, consumers of the class, can actually create a new standard die object. Constructors always have the name of the class. Always. Always, 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 always the name of the class. So this is called die. And we've seen from looking at the documentation lots that if there's information that needs to get passed, then on this side, we would put parameters. And on the calling side, we'd put arguments. But we don't need that for this particular constructor because we know exactly what we need to do without any information from the person calling the constructor. So I'll just give a very terse comment that says this is a constructor. And we're going to do 2 things inside the constructor. And these things are very standard. When we create an instance of a class, we want to initialize important information about that object so that it's ready to be used. You know, the die is ready to be rolled or ready to have someone access the properties in the die. So we, inside this constructor, are going to initialize those 2 variables that we have up above, the fields, num sides and top side. Well, we know what num side should be. It should be 6 because this is a standard die. And top side, we can pick fairly arbitrarily. It's like somebody just took the die out of a box and set it down on a table somewhere. We kind of don't care what the top side is, so we'll just pick one. And we'll pick the number 1. And in fact, despite the fact that we're programmers, the sides on this die will be numbered from 1 through 6 inclusive. It won't be 0 through 5, even though I've been beating that into you for weeks now. It's going to be 1 through 6, because that's sort of intuitive for people using dice. Even programmers generally don't roll a die and say, I can never roll 0, right? Okay, so now, finally, we can go over to the program class and actually start testing our die. Because remember, we did the fields and properties last time, but because we couldn't create an instance of the die object, there was no way to test it. So I'll just put test standard die. And the way we'll do it is we'll declare a variable, and I'll call it standard die. And we'll create a new die object by calling the constructor. So once we've done that, we actually have a die object, so we can access the properties and print them out. And I'll just, jump around to the code for no good reason. There we go. Number of sides. And just as you did when you were printing out the score for blackjack hands, we can just say standard die dot and access the property, num sides in this particular case. And we will also console.writeLine which side is on top. And of course, I'll add a blank line at the end. So now when I control F5, we see some information, and actually I want to put a header on this because we're going to be testing a different kind of die as well. So let me say here, I'll say which die we're talking about, and I'll even yell it. Standard die. So there, the standard die has 6 sides and the top side is 1. So now, finally, we've been able to test both the properties that return the value, the number of sides or which side is on top, and also we have, in fact, tested our constructor to make sure our constructor works right. So let's actually try to test a less standard die. So let's do a D20. So we're going to need another constructor. We're going to need a constructor that actually lets us tell how many sides there are. So I'm going to do another constructor, and it looks exactly the same so far, right? It's public, and it has the class name as constructors always must as the name. And now we do something different. Now we say whoever's calling this constructor can tell us how many sides it has. And so I'll comment this, constructor with num sides specified, number of sides for die. Now, we have seen this sort of thing before where methods of this is not perfectly true, but think of constructors as a special kind of method that actually give us a new object. We've seen overloads before, right? You've seen an overload of constructors before with the vector2 constructor. So the vector2 constructor, you can either not pass it anything, and you get x and y set to 0, or you can call the constructor with an x and a y, and the vector2 object that is created will in fact have the x and y set properly based on what you passed in. So we're doing sort of the same thing here. I'm going to show you a mistake. Okay, so be ready. I know this is going to be wrong, and then we'll come back and talk about why it didn't work the way you might have expected. So I'm going to say num sides is equal to num sides. So I want to set the field for the die equal to the parameter that got passed in right here. So I'm trying to set this equal to this, which is what you'd expect to have happen if you passed in the number of sides. And I'll still set top side equal to 1. Now there is a warning here, and you should learn to pay attention to warnings. I'm going to ignore it. I'm in a big rush. Who cares about green squigglies? They're not red, so it's fine. This warning is basically telling me this code is not going to work. You might want to pay attention, but I'm not going to pay attention. I'm in a frenzy of programming, so I'm going to pretend I didn't even see it. So I'm going to create a new D20 die. But this time, I'm going to tell it, give me 20 sides on that die. I almost put 2. A 2-sided die is a coin. Okay, so 20 sides. This is the D20 die. And so just a little bit of modification here, which was quicker than me typing it all from scratch again. So now when I run it, though, I see I need a space, so let's do that right away. So now when I run it, though, we see that the number of sides is 0, and I passed in 20. So what the heck is going on? Well, let's go back to our die class. It turns out that for fields, num sides as an int starts at 0. So the field starts at 0 automatically. That's what C# does. We haven't talked about that before because it doesn't always happen that way. It always happens that way for fields, but it doesn't happen that way for other variables we declare inside of methods. So assuming something about the initial value of a variable is generally dangerous, unless you really have a deep understanding of the language. Okay, so this warning, the compiler really meant this warning. It said, well, you're taking the parameter num sides, and you're setting it equal to itself, which doesn't do anything. So here's what's happening. This, we're going to talk about something called scope. So this num sides variable is visible everywhere between the open curly bracket and the open curly bracket above num sides and the closed curly bracket, which is way down here at the end of the class. So if I wanted to, well, that's why this property can get at num sides, because num sides, the variable, the field, is visible throughout the class between this open curly bracket and this closed curly bracket. So that's called the scope of the variable. Here's where our problem is. When we get to our constructor here, we have a parameter with the same name. And this parameter is visible between this curly brace and this curly brace. So everywhere inside here, this one hides this one. So what we need to do is we gotta fix the left-hand side here somehow, right? We have to say on the left-hand side, we don't mean the parameter, we mean the field. And the way we do that is we say this dot. And what this dot does is it's really saying, this should look sort of familiar to you, right? This is kind of how we call methods on objects. We put the object name followed by a dot, followed by a method or a property or whatever. In this particular case, the object name, the object that we care about, is this object. And that sort of hurts people's heads until you sort of do it for a while. So don't worry if it's just not crystal clear at this moment. But this is the way that we actually access this particular instance of the class. I'm talking about myself, right? And that actually makes it so when I F6, the warning goes away because now, in fact, I'm assigning num sides, the value of num sides, the parameter, to the value of the field itself. So let's take a quick break and do a couple of in-lecture quizzes. So you can tell me first, on the constructor side, this is the constructor header. Sorry, the whole thing is the constructor header. Tell me about passing information on the constructor side. And now we're going to look at the other side where we actually called it here. Tell me about passing information when we call the constructor. Rather than sort of the receiving side, this is the calling side. Okay, so people sort of wantonly use this terminology incorrectly. So just so we're clear, over here in the call, this is called an argument. Over here in the header, this is called a parameter. In terms of communicating ideas, people just call them parameters on both sides, and generally everyone understands what they mean. But if you want to be correct, then parameter, argument. Okay, let's come back here because I've got to say that I find this code distasteful, right? This die class sets num sides and top side. This die class sets num sides and top side. And in fact, top side is the same. You should think about why we did not have to put this here, by the way. The reason we did not have to put this, you could. This is in many ways a matter of style. Some people like it, some people don't. Up to you. I mean, this was not a matter of style. This we had to do this way. But up here, if you prefer saying this.numSides, it doesn't hurt a thing. I tend not to personally, but it doesn't matter. But we didn't need to here because there was no numSides parameter hiding this one. But this is really ugly. They're both doing the same darn thing. And so what I'd really like to do is I'd like to get rid of duplicated code so that all the initialization happens in one of the constructors and the other constructor just calls it. So this one, this constructor is the more general of the two. So this is the one we'll keep the way it is. And we'll come up here and we'll say, no, I'm not going to do this at all. And this would be bad to just leave it like this because we do need the initialization to happen. But we can actually call another constructor from within the class by going like this. We put a colon. We put the word this. Sort of. We put the word this, and then we pass it the appropriate argument. Like that. This and that. Wow. So just as the this here with the dot meant this particular object, the this here means any other constructor you can find in this class that takes one integer argument when I call it. And it turns out we only have two, right? So now we've refactored, we've redesigned the code. We'll test it to make sure, but functionally it should work exactly the same, but we're refactoring it to make it better code. Not to make it work better, not to make it faster or anything necessarily, just to make it higher quality code. And so when we call this constructor, what it's going to do is it's going to immediately call the other constructor passing in a 6, which will set numSides to 6 and topside to 1. And we'll control F5 to demonstrate that it still works fine. So this is a really good thing, right? When we identify places where we can clean up our code or consolidate logic in our code so it's only in one place, that's great, because if we ever need to change that code, we only need to go to one place to change it, and that's a win. Okay, so to recap for today, we have done the second piece of the 3 pieces we need for an object. So we already had state when we started the lecture, and now we have the ability to give identity to objects by calling one of the 2 constructors that we have implemented in the die class. Next time we will finish off the die class by implementing the roll method. This is our last lecture in this module, Developing a Console Application class. So next time we'll move on to doing X&A stuff, but we have a little bit more work to do here first. As a reminder, here are the module learning objectives for the entire module. So you should recall that last time we added the two constructors to the die class, one that built a die with the standard 6 sides, and one that built a die with a consumer specified number of sides. So there was a parameter in the constructor, and there was an argument when we called the constructor to tell it how many sides we needed. This time, we're going to implement the single roll method that we need in our die class. So I have the project available to us. We already have, recall, fields, constructors, and properties in our class. So now we can add methods. And we needed a single method. We need the roll method. And we're going to learn something new as we develop this method, and the rest of it we've already seen before. So methods have an access modifier. And because we want a consumer of the class to be able to roll the die, we're going to make this method public. The next thing that happens, the next thing that we put as we build this method, is the return type for the method. So the deck take top card method had a return type, I'm going to type it here, it's not going to work, had a return type of card because it returned a card from the method when you took it. Other methods in the deck class had a return type of void. They didn't return anything at all. They just did their job and then were done with it. And so we need to think about, should the roll method have a return type? Should it return anything or not? And this is actually a trade-off for this method, because the way I'm implementing it, it's going to have a void return type, which means it doesn't return anything. And then it's much more like what you actually do with dice, right? You roll a die and then you look at what number is on top. So standard usage would be somebody rolls the die by calling the roll method and then accesses the top side property to see which side is on top. There is an alternative, certainly. We could return an int from here so that we rolled the die and then generated the then accessed the topside property and returned that. We could do that, but we're going to do it this other way instead. So access modifier, return type, method name. Well, not exactly that way. Method name, parentheses, even if there are no parameters, parentheses, open brace, curly brace, and we'll put in the comment momentarily. So the next question is there any information that we need from the consumer of this method to say something about the roll? And the answer is no. In this particular case, the answer is no. They're just going to roll the die. So I put the 3 slashes in, and I say rolls the die. So, how do we roll a die? Well, rolling a die means we are randomly picking some number, right? From the set of sides of the die, we are randomly picking which side should be on top. So we're definitely changing top side. And we can, well, gee, I said we need to have a random number, so I'm going to create a new random number generator right here. And this new random number generator we will use this new random number generator to generate a random number for the top side. And we'll actually use the overload of rand not next that lets us specify both the lower bound and the upper bound. Because we're numbering the sides on our die starting at 1, we'll put a 1 here as the first one. And so for a 6-sided die, for example, we want a random number between 1 and 20. So that's crazy. Here I am thinking D&D again. For a 6-sided die, we need a random number between 1 and 6. And so we need to say num sides plus 1, because remember the upper bound for this argument to the next method, this gives an upper bound, an exclusive upper bound. So if we pass in 7, it will give us, for this call, a random number between 1 and 6. So let's actually go back to our, I'll save it, and we'll go back to our testing code, and we will roll the die. We'll roll and print the results. So we tell the die, the standard die in this case, to roll itself. And then we will display the top side again. So I'll just grab these 2 lines of code and put them here instead. Put them here also. So if I control F5, we see that we roll and we get a top side of 3. And just so that you see that this rolling also works for the D20, we'll do it here as well. Although of course we'll need to change a little bit. We'll need to we'll need to tell the D20 to roll itself. And we will then tell the D20 will then access the topside property of the D20. Okay, so I'll control F5. So far, this looks pretty good, right? It looks like we're getting a random number. And by the way, let me just add the right line that we're missing here. By the way, I had to be careful over here in the roll method to not just say between 1 and 6, right? Because we could have an arbitrary number of sides on the die. So that's why I used num sides here to make sure that it would still work for the D20 as well. Unfortunately, even though this all looks great, let's roll a few times in a row. Control F5, and you will see that for the standard die, we rolled a 2, and then a 2, and then a 2. So this is actually an issue with random number generators. When we create a new random number generator, what happens is it takes the system clock time from our computer in general and uses it as something called a seed. And that seed is the start of generating a sequence of numbers using an algorithm, a set of mathematical steps to figure out the next number. So in computers, these aren't actually random. They're what are called pseudo-random because they're not actually random. If you know the seed and you know the algorithm, you can perfectly predict the sequence of numbers that would be generated. The problem is that if you start with the same seed and you're going to be using the same algorithm because that's just expressed in code, then you're going to get the same sequence of numbers all the time. And so the issue is that because computers are really, really fast, we end up with 3 calls to roll in quick succession such that the system clock is close enough to the same that each random number generator gets the same seed. So I'm going to take this random out of there and I'm going to move it up here as a field instead. That was crazy. I'll just type it in now. I guess I just, X'd it instead of C'd it. So, new random up here in the class. So, this will get created when the object is constructed. And so, each call to roll down here isn't creating a new random number generator anymore. It is in fact just using the one that we created inside the object. And I'll control F5 again, and you can see, yes, we did get 2 4s in a row, but that was not the problem I was talking about. As you can see, we are getting essentially random rolls. Now, I've solved part of the problem here. And the different dice look different because one is generating numbers between 1 and 6 and one is generating numbers between 1 and 20. But we would have the same exact problem, even with what I've done so far, if we created 2 6-sided die in a row. Because we'd be creating the objects quickly enough, potentially anyway, that they'd end up with the same seed, so both dice would end up with the same sequence of numbers. Even though the numbers changed over the sequence, the dice would always match. The optimal, robust, commercial quality solution is to have a random number generator that you create for your entire game. And every time anything in the game needs a random number, it just goes to that one single centralized random number generator and gets a random number. We're not going to do that here because we're focused on class design and implementation rather than sort of the overall game design implementation, but that you should know that because this is an important issue for random numbers. So we have created everything that we needed to create today, and in fact we have finished off our die class implementation. So over the course of 3 lectures we designed it, and we implemented state the first time, and then identity last time, and now behavior this time. So we're all done with the die class. Next time, we're going to actually start developing a class. We'll design it and implement it for use within an XNA game. So we're halfway through Module 11. Continuing along, here are the learning objectives for the module. Last time, we finished up with our console die class, and so it's time for us to move forward and to develop a class that is designed specifically for use in an XNA game, rather than in a console application. So in this lecture, we will be designing that class, and we'll be implementing the fields and properties, so the state, again, in that class. Before we do, you should go take an in-lecture quiz. Now I know we've discussed using a rubber chicken as a weapon before, way back in Module 4. I have cut back a little bit on the scope of that weapon, so it can't be used as a melee weapon. It's only a ranged weapon, so we'll use it as a ranged weapon, and we're going to focus today, well, we'll do all the design, but we'll focus on implementing the state stuff. So here are the things that we really need to keep track of for the state. We need to keep track of whether or not the rubber chicken is active, because we're going to use it as a weapon, essentially a projectile, and so when the projectile destroys something, we should probably destroy the projectile as well. So we're going to deactivate the rubber chicken just as we deactivated teddy bears when they got destroyed. We're also going to need, I'll do 2 things here. We're going to need both a sprite so we can draw the rubber chicken in our XNA game, and a draw rectangle. Now, as I've mentioned in passing before, there are actually lots of ways to draw sprites. The sprite batch draw method has lots of overloads. We're going to continue using a draw rectangle though. And I said draw/collision rectangle because inside the class we'll think of it and refer to it as the draw rectangle. But again, just as with the teddy bear, we're going to consider consumers of the class, we'll think about that rectangle as a collision rectangle. So we'll handle that when it's time to build the appropriate property. Rubber chickens that are used as ranged weapons will have a velocity once they are launched. And so we need that velocity so we can update the rubber chicken's position or location over time. And then finally, the amount of damage that the rubber chicken inflicts. So when we hit something with a rubber chicken, it causes some damage, and maybe some rubber chickens are more powerful than others, and so we'll keep track of the damage that we can apply as well. Because we're going to look at the UML for the fields in a moment, but because we're going to save all the state information inside the object as fields, you should go do an in-lecture quiz telling me that you understand our conversation about fields when we did the console class. So here's the UML, and it should come as no surprise to you that we have 5 different fields here that are going to store the 5 pieces of state that we talked about before. The additional detail that's included in here is the data types for each of those pieces of state. So active will be a bool, true or false, right? That makes sense. It's either active or it isn't. The damage will be an integer amount. We won't need the granularity that says it does, 48.2 or anything like that. The draw rectangle will be just as we've been doing before. It'll be a rectangle object. The sprite will be a texture 2D, as we're used to in XNA games. And the velocity will be a vector 2. So as a reminder, a vector 2 has 2 components or 2 properties we can access. It has an x and it has a y. So if we have this 2-dimensional vector is really what it is, then it will tell us what's the velocity in the x direction, positive or negative, and what's the velocity in the y direction, positive or negative. So those are, in addition to the field names, we now have captured the data types we're going to use for those fields, which helps us when we get to the implementation part. So I'm going to actually start a new project. So I've double-clicked my shortcut, and now I'm going to create this new project. So I say new project. It is an XNA Game Studio game. It is a Windows game. I'm going to browse to the place where I want to save it. So I'll cut here and be back momentarily. Okay, I have saved it, and we have the code here, and I'll zoom in, even though we're going to immediately go and create a new class. And so we do this exactly the same way that we did it in a console application. You need to be a little careful. Make sure you don't create the class down here in the content area. That's for content, not code. You want to create the class up here where we're storing all of our source code, all of our C# files. So we right-click. I named this namespace Rubber Chicken, by the way. I right-click it. I say that I want to add a class, and my class is going to be a rubber chicken. I'll zoom in immediately and put the class comment. And I'll add the region for fields. And I'm going to sort of group these together as we go along for, drawing support and movement support and so on. But you can put these fields in any order you want, really. And some I won't even comment. So typically I comment the drawing support fields, even though there's only 2 of them. But I don't necessarily comment the active field, for example. So I actually will put that active field. Remember, we decided it was going to be a Boolean. And to this one, we can just initialize to true. Just like at the end of the lecture last time, we had a random number generator that we made a field in the die class instead of just using a local variable That's what a variable that's declared inside a method is called because it's local to the method. Instead of using a local variable, we used a field, and we initialized it when we declared it. And so that's a perfectly valid approach to use, and so I'm setting active to true here because rubber chickens should always start as active. Okay, I'll add some drawing support. So I need a texture 2D, and I know it's hard to see and there's no way for me to zoom in on the IntelliSense, but texture 2D is not showing up as one of my choices. What that means is that I do not currently have direct access to that class. Well, we have seen this in the programming assignments where you needed to add a using statement. And so we need to add a using statement to get at texture 2D. So we need to type in using whatever the namespace a texture 2D appears in, and you may not have memorized yet what namespace that's in. Good news is we can go to help and we can search on texture 2D, and we will sort of click around for a while until we get to where we need to be. But the texture 2D class, it says right up here at the top which namespace it appears in. And so the texture 2D is found in the Microsoft.xna.framework.graphics namespace. So that's the namespace we need to add. So Microsoft, and IntelliSense will help us a little bit here, graphics. Now that I've added that namespace, when I come back here, I hit Control Space, by the way, to make IntelliSense pop back up. Now all those textures show up, which is good. So I'll need a sprite, and I'll also need a rectangle for the draw rectangle, and we say, well, that one's not showing up either. So unless you've memorized which namespace rectangle appears in, back we go to help. And I can click on any of these until I can click on the rectangle structure, and this one is found in the framework namespace, not Microsoft.xna.framework.graphics, just Microsoft.xna.framework. So back to the code again. Another using statement. And now, again, Control Space, and rectangle is the only one that fits, so it automatically filled it in for me. And we now have our draw rectangle. So that's good. We have 3 of the fields taken care of already. We still need to handle damage and velocity. So let's take care of damage first. And again, your order doesn't matter. I'm just sort of grouping them in a way that seems intuitive to me. So we'll say there's some damage field we're going to have. And I'll even change this comment to say drawing and moving support. So I can just put the vector 2 that I need for my velocity right here as well. And that's it for the fields. We need an active field that's a Boolean, damage that's an int, sprite is a texture 2D, draw rectangle is a rectangle, and velocity is that 2-dimensional vector that we talked about. So now it's time to actually start adding the properties. So first, go do an in-lecture quiz about properties. And now that you're back, you can see that I've added properties here to the UML. So these are the 3 properties that we need. We need active, and we talked about properties last time. By the way, properties can be read, they can be write, or they can be read-write, depending on the combination of get accessors and set accessors that we provide. And so in this particular case, for the active property, we've said it's going to be active with a capital A. We're going to provide both a get accessor, so the game can determine whether or not the rubber chicken is active, and a set accessor, so that the game that's using the rubber chicken can deactivate the rubber chicken when it should be destroyed. And finally, that last little piece right here says that it is in fact going to be a bool property, which makes sense, right? Because the active field is a Boolean, can either be true or false. It makes sense that the property is a Boolean as well. Our second property, the collision rectangle, remember I have renamed what we're calling draw rectangle in our field to be collision rectangle for the property, because the consumer of the property is really thinking of it as something to be used for collision detection, not something to be used for drawing the sprite, because that's internal to the class, so a consumer of the class doesn't care. It is a get accessor only. It makes no sense for the game to be able to change the collision rectangle for this thing. It's based on the sprite and all, well, it's based on the sprite and the draw rectangle. So only read access for this particular property. And then finally, we have the damage property, an integer, as we'd expect. Only a get accessor, so only a read access for this property as well. So there are no power-ups that will make the rubber chicken inflict more damage. This will be a really basic rubber chicken game, not the deep play experience that you might have been expecting. All right, so back to the code. I am adding a region for those properties that we were just talking about, and I'll add them one at a time. So we'll make them public. Remember the access modifier. This particular property, I'm doing active first, so it's a bool, and active with a capital A. And I said that we were going to provide both get and set accessors. And I'll add the comment now before I forget. Gets and sets whether the rubber chicken is active. So recall from the other properties that we have done so far that we're going to end up returning the value of the active field, and to return things, we type return. The set accessor, which we looked at before and I showed you an example and then got rid of, looks similar to the example I showed you. We're going to be setting the active field equal to whatever value is provided when the game accesses this property, this set accessor for the property. Remember, it will say something like rubberchicken0.active equal false. And so inside here, inside the set accessor, that false is value. All right, so that's the first property. The second property is collision rectangle, so public again. This time it's a rectangle. And recall, this one we're only providing a get accessor for. And here's where using properties rather than just giving consumers of the class direct access to the field is useful, because we can rename this to collision rectangle instead of draw rectangle based on how the consumer of the class thinks about this property. Gets the collision rectangle with the rubber chicken. And finally, we had one more property in our UML, and that property was damage. So it's public int damage, get accessor only, gets the damage, the rubber chicken inflicts, and get works exactly like the other get accessors we've been doing. We just return damage. So now we have the properties included inside our implementation. We, just as with the die class after we did fields and properties, we couldn't do any testing on it yet, and we can't here either because we can't construct any rubber chickens yet. But we'll be able to do that next lecture, and we'll implement the constructor, and then we can construct and make sure they work and so on. So we'll get there. We're just not there quite yet. Okay, so back to the slides. The last piece of the design, I know I sort of snuck in some implementation during the design, and that's okay too. We It is very rare to do all your design and then all your implementation. This is a really iterative thing. We design some, we implement some, we design some, we implement some, and sometimes we go back after starting to implement and say, wow, our design was not correct and we need to fix it. And so this going back and forth is a really common thing, nothing wrong with it. But now that we're back here on the slides talking about design, we have behavior for the rubber chicken too, and I have simplified that behavior as well. We talked back in Module 4 about playing animations and so on. We won't do that here. What we'll do instead is we will do two things. We will update the rubber chicken, and this one will be a fairly interesting and reasonably complicated thing because we'll move it along its velocity vector based on the elapsed time. That's not the complicated part. And we will also process mouse input. So the way we're going to launch rubber chickens, I mean, you might think we'd have rubber chicken cannons or something like that because it's really a projectile, but we're not going to have that. We're in fact going to launch the rubber chicken by clicking on it. Now this is a very stupid rubber chicken. It's not a homing rubber chicken or anything. When we click on it, it's just going to go straight up, is how this rubber chicken will work. If you wanted to, you could, of course, implement far more complicated schemes where you click a rubber chicken to activate it and then click somewhere on the screen and that's where it's going to launch itself toward and so on. You know, send the rubber chicken over there, right? And that's a perfectly reasonable thing to do that obviously people have figured out how to do in games. We're just not going to do it here today. We're not going to do it at all, but we'll do a really simplified rubber chicken goes up when we launch it. So that's this part. So we're going to have to detect a mouse click, not a mouse press, a mouse click on the chicken. And we've learned how to do that already when we were processing mouse buttons in the XNA input lectures. And the other behavior we're going to have is we're going to have the rubber chicken draw itself. And that one's going to be a really easy one to do. So if we look at the final UML for our diagram from today's lecture, we see that we've added these methods down here. And so we also have identified the fact that to be able to draw, we're going to need a sprite batch to get passed in. So we can call the sprite batch.draw method. And to update, because there's both the velocity, which needs the elapsed game time, and the click processing, which needs the mouse, we'll need both of those things. Just like our roll method had a return type of void, both of these methods also have a return type of void. So we're not writing any methods in this class that will actually return a value when we call it. And that's all we're going to do for today. We did all of our design work and we did our implementation work for the fields and properties. So we've got off to a great start on our rubber chicken for the XNA game. And next time we'll actually implement both the constructor and the two methods that we need for the behaviors of the rubber chicken. Continuing on with Module 11, here are the Module 11 learning objectives. Last time, we did our design work on our rubber chicken class for an XNA game, and we also implemented the fields and properties. So this time, we're going to implement the constructor and the update and draw methods that we discovered that we needed in our rubber chicken class. So that's what we're going to do today. You should go to an in-lecture quiz about constructors. And now we'll go to the IDE and implement the constructor in the rubber chicken class. So here's our rubber chicken class so far. These regions get collapsed sometimes. And so now I'm going to add a region. And I always call the region constructors, even if I have one, but that doesn't really matter. It's up to you. So I want the constructor to be public so that, in fact, I can create rubber chicken objects for my game. I also need to call it rubber chicken because constructors always have the name of the class. And one of the things we didn't do was actually talk about what should be provided as arguments when we call the constructor, parameters here on this side. So we know we're going to need a sprite that we can use to draw the rubber chicken. It's very common to provide the location of the center of the rubber chicken we want to draw. And so we can provide that in a variety of different ways. We've often been passing in X and Y for the center of the object we're getting ready to create. So I'm going to assume you have had enough practice with that. So instead of doing that, I'm going to pass in a vector2 for the location of the rubber chicken. And of course, given a vector2, we can extract the X and Y components from it. And we will also need to know how much damage the rubber chicken will inflict. Some rubber chickens may be more damaging than others, so we provide that information when we construct the rubber chicken. I haven't provided a velocity. We'll actually just create rubber chickens with 0 velocity because they'll get launched when we click on them in the update method. So now we have our set of parameters for the constructor, and I'm going to, if I ///, it automatically fills in the sort of framework for the comment I should provide. So constructor, sprite, location of center. We should be specific here so that somebody who's a consumer of this constructor knows that this is the center of the rubber chicken, not something else. And we can say damage from rubber chicken. Now, we saw before that based on scope, a parameter can hide a field of the same name. And so we're going to run into that right away with the sprite. So because I already recognize that ahead of time, I will say this sprite is equal to sprite. Now I want to center my rubber chicken on the location that's provided as a parameter, and I need to build the draw rectangle that will do that. So let's say build draw rectangle. And I'll do a variety of different things, right? I could. Wow, I could. I have a variety of different ways I could do this. I could use the constructor, the rectangle constructor, that just sets everything to 0 and then set each one individually. Or I can just provide the X, Y, width, and height values as I build the draw rectangle. And I'm going to choose to do it that way instead, because it just results in 1 line of code here instead of 5 lines of code. 1 to create the rectangle and then 4 more to set each of the properties of that rectangle. I'll just provide the information here when I create the rectangle. So where should the left of the draw rectangle be? It should be at location.x, which is the center, the horizontal center of the desired location for the rubber chicken, minus the sprite width property, so this tells us how wide that sprite is, divided by 2. So I'm drawing actual size, there's no scale factor here. Same thing, or similar thing, for y. The y location of the dry rectangle, the upper left-hand corner, will be at the center vertically, minus the height of the sprite divided by 2. And then the width and height will just be the width and height of the sprite. So I have now created a rectangle, and I am getting some compilation errors that say I cannot convert from float to int. So sprite.width is an int. So dividing by 2 is still an int. However, location, which is a vector 2, contains 2 floats. X is a float and Y is a float. Luckily, we learned a long time ago that we can do typecasts as necessary. And so I will cast each of these equations to ints instead, so that I can now compile just fine. And the good news is that at this point, we can now go back to our Game 1 class and actually start testing the fields and properties that we wrote last time, and the constructor. So we will in fact need a rubber chicken. So I'll declare a field in the Game 1 class for that. And we'd want to create that rubber chicken down here in load content. We'll create a rubber chicken when we load the content. So create rubber chicken. And now we have a problem, because the first thing that we need to pass in, well, maybe you don't recognize we have a problem yet. Hang on a sec. Let me show you we have a problem. A newbie rubber chicken is a new rubber chicken. And we say, okay, first thing we have to do is pass in a sprite. We haven't loaded any sprites, so there's no way for us to pass one in, so bummer. Even worse, over here in the content, we don't even have any graphical assets. That's okay. I'm here to help. So if we look at the XNA content folder, that is a beautiful rubber chicken programmer art right there. I am going to copy this rubber chicken into the content folder for the project I'm currently working in. So that's all through Windows Explorer stuff. And now I'm going to come here and I'm going to add an existing item, which is the rubber chicken that I just copied over. So now I do have a rubber chicken that I can load. And in fact, I don't even have to load it into a variable before passing it as an argument. I can just do here as the first argument, content.load texture, texture 2D. And I have to give it the name. And if you can't remember the name, you can single click here, and down here is the asset name. It's rubber chicken. So rubber chicken it is. So that's the first argument. And when I hit comma, IntelliSense says, okay, now give me a vector 2 for the location of the rubber chicken. And I will say I'll create, instead of creating a variable, I'll just create a new vector 2 object. But I need to, if I just use this overload, it will be at 0, 0. So the rubber chicken would be, partially outside the screen, and that's kind of disgusting. So I want to center it. I'll center this one, and we'll do a game soon. But we'll center this one, which means it should be at graphics, preferred back buffer width, over 2, graphics, preferred back buffer height. Try that one more time, preferred back buffer height, over 2. So now I have created this vector 2 object with X in the middle horizontally and Y in the middle vertically. And finally, I have to provide damage. Rubber chickens do 100 damage. Boy, I just can't bring myself to do that. I need a constant called rubber chicken damage, because we all know that I am going to have to tune this game eventually, and having to go look for those magic numbers is just brutal. So instead, I'll say const int rubber chicken damage is equal to 100. Okay, if I F6, build succeeds. If I F5, weird aspect ratio, I'm not going to worry about that for now. So I actually have implemented the part where we have the constructor and we're constructing it here. We should probably draw it next so that we can make sure. That is actually a really good way for us to make sure that, in fact, the draw method and the constructor are working properly. So once we start drawing it, we should see a rubber chicken, actual size, centered in the middle of the window. And that will give us assurance, other than the damage, that will give us assurance that everything else worked fine in the constructor. So let's go do the draw method. We'll implement it over here. And of course, I don't have any regions for methods yet, so let's add one. Now, I typically, in my classes, I will typically define or declare or implement, however you want to think about it. I'll implement the update method after I implement the draw method, even though in the class themselves, I usually put update first, because I think sort of mentally, update happens, then draw, update, then draw. But to get some visual reward early on, I regularly do the draw part first when it's time to implement. So public void draw. We know we need a sprite batch because that's what the UML showed us last time. I'll add the comment, draws the rubber chicken. Perhaps that's what the comment will say. And we're passing in a sprite batch. So this is an easy one-line method calling the draw method on the sprite batch object that got passed in as a parameter. And we'll use this very first overload where the texture is the sprite. And notice we don't have to put this dot sprite here to access the field because there's nothing hiding it. You can if you choose to. It doesn't hurt anything, but we don't have to. We have the draw rectangle, and we'll draw it in white so that we don't lose any of that amazingly compelling art that we've seen. So I am going to go to the Game 1 class now. I'll Control S because save often. And I'll go to the draw method. Remember, we can do this drop down if you don't want to be scrolling around the class. And I'll add the drawing code here, draw the rubber chicken. And so we will do the sprite batch begin and end as we always do, or regularly do. We always do if we want to draw something. And we will tell the rubber chicken to draw itself. So rubber chicken, draw yourself. And I know on this side I have to pass one argument, and I can just pass the sprite batch as we've been doing for a long time as we drew XNA objects. I'll F5 and we see we have a beautiful rubber chicken right in the middle of the screen, just as we expected. And in fact, you'll notice, by the way, that the mouse disappears when I go over the cornflower blue stuff, which is going to make it really hard when it's time for us to click on a rubber chicken. That's just mean to the player. So let's go here to the constructor and we'll make the mouse visible. So if I F5 again, now we see that we have the mouse within the game window as well. So that's great news. As I was going through this lecture, I realized that it was going to be extremely long. And so I'm breaking it into two parts. And so this is the end of part 1. Remember that last time I needed to break this lecture into two parts because it was going so long. And so this is part 2 of the lecture I started last time. Okay, we saved the hardest for last. So the hardest for last is that the rubber chicken needs to move along based on its velocity. in the update method. The update method is the hardest for last, so I guess I can go over there and start on the update method. We do know from our UML, let's go back and look at the UML briefly. So we do know from the UML, we just did our draw method right here. And we know from the UML for update that we're going to need to have game time and the mouse state so that we can actually do the two things, right? Move along based on velocity and detect mouse clicks to launch the rubber chicken. So given that reminder, we have a public, we have void, update, and we need a game time parameter, and we need the mouse state parameter. And we get that red squiggly stuff that says, holy smokes, we don't know where this exists. I'll save us the effort this time, but you know how to find this out, right? You can actually search mouse state in the help and find its namespace, but I happen to remember that this is in the input namespace because mice are used for input, and so I don't have to go do that. All right. By the way, I just realized as I went blasting past this constructor that I didn't actually save the damage. We would have discovered that eventually, but since I saw the error as we went by, it's worth just fixing as you go by. Okay, so down here, we're going to update. Updates the rubber chicken. Moving and launching when click. So we have the game time that's passed in, and we have the current mouse state that's passed in. The move based on velocity is a straightforward thing. We can say we'll just move the draw rectangle X and Y because that will move the whole thing. Draw rectangle X plus the velocity in X times the elapsed game time. So velocity is in pixels per millisecond. That's the units. So if we multiply it times game time, elapsed game time, milliseconds, it's going to race off the end of the screen, darn. I'll make it just a tiny bit smaller. Then, because it's in pixels per millisecond, this will work fine for us. Plus equal velocity dot y times game time dot elapsed game time dot milliseconds again. Okay. Launch on click is way trickier. And it's, whoops, by the way, we're getting some compilation up there because, again, compilation errors up there because we're multiplying velocity dot x, which is a float, and velocity dot y, which is a float, times something which gives us a float, which means that we can't put it into an int. X and y are ints. One bit smaller again to make everything fit. Okay, so launching on a click, as I was saying, is much harder. And it's even harder than the clicking we were doing with the character because we did the easy thing before, right? We had this character that we were dragging around, and we would, in fact, we were changing every time you clicked whether or not you were actually clicking on that character. Because it was following the mouse, we were always clicking on that character. But here, if we're going to actually make this behave properly, we have to make sure that a mouse click occurred on the rubber chicken. And that's trickier than you might think because, you know, people do all kinds of weird stuff. They'll press the mouse button down on the chicken and then move off the chicken and then let go and all kinds of things. So there's all kinds of stuff that we need to do. And instead of walking you through all that stuff, I'm going to take the code that I provided to you in the required programming assignment. in the required project, and I'm going to copy it here, and then we will make appropriate changes. Okay, so the first thing we're going to do is check for the mouse over the button. I'll change that to say rubber chicken. So we're checking to see if the draw rectangle contains the mouse. Now if the draw rectangle does not contain the mouse, that means the mouse is not on top of the draw rectangle for the rubber chicken. I can get rid of this source rectangle stuff because there's no highlighting rubber chickens. That would just mess people up. But there are a couple of flags that I use in this code. Click started and button released, which means that I'm going to need up here fields for those things. I'll call it click processing. Almost. So click started is definitely, wow. Let's try that again. Bool click started is equal to false. When we create the rubber chicken, we're going to assume that a click has not been started on the rubber chicken. And the other one is bool button released, and we will say that that is true. We'll assume that the player starts the game without holding down the mouse button. I'm going to be lazy, and I tried to compile so it would bring me to the errors so I could keep working. Notice these now compile. So let's come back up here. We don't have to highlight any buttons, but we do have to check for the button pressed. And let's say click started on rubber chicken. And I'm going to say that at this point, I'm going to just fix this comment, and you should look carefully through the code and make sure you understand how it works. But basically what's happening is, at this point, right here, we know that the rubber chicken is actually moving. And so here is where we want to launch the rubber chicken. Now, turns out that we actually need to be careful here, because we should not let somebody click a rubber chicken to launch it and then click it again as it's flying along to launch it again. No double jumping for rubber chickens here. Means that we're going to have to add another field here to keep track of whether or not the rubber chicken is moving. So the rubber chicken doesn't start by moving, nor do we have a data type called ball. So we'll come down here, and the only way we will launch, if not already moving, so if not moving, so the rubber chicken isn't moving, but we know it should now be because we're going to launch it, we'll set moving to true. Now remember, when we created the rubber chicken, its velocity was 0. So all those updates, once we start updating it, if it's after its creation, it just sits there. When we click it, it will start moving with the velocity we give it here. So we'll say velocity is equal to new vector 2. Ooh, this is going to be great. We're going to crash, and you'll see it, and it'll be awesome. And then I'll explain what happened. So let's say right now, we'll say 0 in X, and we'll say rubber chicken speed in Y. This will immediately give us a compilation error because we have not declared rubber chicken speed. So now that I need a little more, I'm going to break this out, say moving support. So we have drawing support and moving support. So let's go here and say const int rubber chicken speed. And by the way, I called this speed because this is just the speed of the rubber chicken. It's moving in the Y direction. That's the velocity part. So velocity is speed and direction combined in some way. Okay, so I've got the rubber chicken speed, and so this now compiles. We'll go back to game 1, and we'll go to the update method in game 1. I know I was so excited that it's going to crash. And I'm going to say update the rubber chicken. And so tell the rubber chicken to update itself is really the thing that we mean. And so we have to pass in game time. And we have to pass in mouse state, which we haven't grabbed yet, so we better do that. Mouse state, mouse equal mouse dot get state. And so now we'll pass in the game time and the mouse. So everything compiles and we're filled with excitement. And then we F5. I was wrong about the crashing. That's a shame. I'll talk to you about why I thought it would crash. So here, when we set the vector2 for velocity, many reference types, if in fact you don't initialize it, then this has a value of null because there's no object, there has been no object created for it. Let's take the debugger here, and when I F5, I'm going to create a rubber chicken, and now I can look at the velocity down here, and you'll probably have to do this in your very own environment so you can check. And it turns out that the velocity does in fact have 0, 0, which I did not expect. Let's finish this off. Which I did not expect because I didn't think it all the way through. Vector2 is actually something called a structure, not a class. And I've said that the distinction is not very important for us in this course, and that is in fact true. But this is one of those subtle places where it's different. So a structure actually gets initial values for things. Let's be explicit here. Let's actually say we'll assign it, and it turns out that we can assign it to vector2.0. So we are explicitly saying here in the code that this is 0, rather than counting on our remembering that structures are different from classes and all those things. By the way, when I clicked the chicken, not only did he go too fast, but he didn't go up, right? And he didn't go up because I set this to rubber chicken speed when in fact it needs to be negative rubber chicken speed. Now it's actually easy to, as you're reading code, this will work, by the way. So let me show you that it'll work. I'll click on him and up he goes. Still pretty fast. It's fast rubber chicken. However, for readability, I will regularly say -1 times. It's the compiler will optimize it so that it doesn't actually have a CPU impact. But when you look at this, it's easy to see, right? Rather than the hyphen right next to the R, which makes it harder. And of course, you can do this too. And that also works to make it a little more visible. So we'll do -1 times. And that's it, right? That is, in fact, the complete implementation of our rubber chicken class. Now, we didn't check the properties. We didn't test those things. But the good news is that next lecture will actually implement, although I'll put a whole bunch of stuff in it beforehand, we'll implement a game that uses rubber chickens, and we will see that, in fact, the active property works properly, the damage property works properly, and the collision rectangle property works properly. Okay, so that's it for today's lecture. We'll come back next time and build a game using a rubber chicken. We've reached the last lecture in Module 11. So as a final reminder, here are the Module 11 learning objectives. So last time we finished implementing our rubber chicken class, and it's time to actually put that class into a game. And so we're now going to build a complete game that includes the rubber chicken as one of the classes in the game. I've already written all the code, but I've also commented it all out again and captured the sequence of steps that I followed to develop the code. So I'm going to bring you through the process from start to finish, and I won't actually be typing code, I'll just be uncommenting pieces I already typed in and talking about sort of interesting things as we get to those pieces. So let's go right to the IDE. I've already got it opened up and zoomed. Thank goodness for both of those. So the initial stuff, and I'm going to try not to get dizzy. I'm going to pop back and forth between the PowerPoint and the code so that we can look at each step. But before we start doing that, I want to show you the core things that I've already included in the game. So we already have the standard constants for window width and window height. I have some information about chickens, how many chickens will be in the game, and how much damage each chicken inflicts. I'm saving the 3 sprites that we're using in the game for efficiency in these texture 2Ds because we're going to be creating bears and chickens and explosions all over the place. So just loading this content once and then saving it and using it as we need it is a good idea. We have some game entities. We have a list of rubber chickens, a list of bears, and a list of explosions. And you will notice that in this constructor for the list of rubber chickens, I've actually provided an argument, whereas all the lists we've created so far, I haven't done that. This just tells the system how large that list should be. So it's the capacity of the list. And I actually know I will always have exactly num chickens. So if I provide the capacity first, then I don't have to grow the list dynamically. We have teddy bear spawn support. I have speed for the teddy bears. They'll spawn every 2 seconds. We've seen this timer stuff before, and I will need a random number generator to generate the random X location for teddy bears that I spawn. I've set the resolution and made the mouse visible because we click on rubber chickens to launch them, and we want to make sure the player can see where the mouse is to do that. In the load content, I haven't done too much exciting here. I've loaded these 3 sprites, so you've seen that before. But I'm also calling this spawn initial rubber chickens method. That doesn't come free in the Game 1 class. I wrote this. So let's go to the definition. I right-clicked and about halfway down. So this is just writing a method like the methods we've already written to roll the die, to tell the rubber chicken to draw and update themselves. This is just another method that I've written. Now it turns out that this one is slightly different because I've made it private. Nobody outside this class should ever be able to spawn the initial rubber chickens. And so I made that private, and it can only be used from within the Game 1 class. And specifically, it's only used from the load content method. So I'm actually going to do some math here where I figure out what the spacing between the rubber chickens should be based on the window width and how many rubber chickens I'm going to have. And I then set the current X, so this is the X for the rubber chicken I'm about to create, to X spacing over 2. So this is going to be way over near the left side of the window, though not all the way up against the left side of the window. I then spawn the chickens. I'll talk about this get chicken start Y method right now. Again, another private method. And really it just returns window height, so the very bottom, minus chicken.height over 2. So this is going to put the chicken standing on the bottom of the window, basically. I wrote this method because I discovered that numerous times I needed to do this exact same calculation. So instead of doing the calculation at 3 different places in my code, I did it in this one place instead. So I get the chicken start Y, and now I do a for loop. This is much like the for loop when we had the initial num teddies a long time ago when we were learning about for loops. And so I go through the for loop. I add a new rubber chicken with a sprite, a location, and how much damage it inflicts. And then I change the current X by adding X spacing to it so that the next time around the loop, when I'm on chicken number 1, our second chicken, it will be at X spacing plus X spacing over 2. So I'm, putting them in a row across the bottom of the screen. And I do that with that for loop. And now if we go back to the PowerPoint slide, we see that I have done this step. I've spawned the initial chickens. You can't see, and by the way, this is exactly the order in which I did the steps as I was creating this game. I got to, step 3 and said, hey, I should keep track of this so I can go through in the same order when I do the lecture. So we've spawned those chickens, but you can't see them. So we should draw all the game entities. So let's go up to the draw, and I'll just uncomment this code. And you might think, reasonably, that I should just be drawing the rubber chickens at this point. Why am I drawing teddy bears and explosions? Because those lists are empty right now and I know it. To be honest, when I came here, I said I might as well draw everything right now while I'm thinking about it, rather than waiting until later and then realizing I forgot to draw the explosion and then coming down and, spending debugging time. So I did it when I thought of it. And now that I've uncommented this, I can run it. And we see a row of beautiful, beautiful rubber chickens along the bottom of the screen. Okay, so now I have drawn all the game entities. So the next thing says comments for all the updates that need to happen. So at this point, I started thinking about how the game would really work. And I went up to the update method and I put a set of comments. I said, make sure you update all the game entities, check for collisions between chickens and bears, clean out dead teddies. The sequence of steps that I knew would need to happen on every update once the full game was running. We'll just look at those comments as we go along because it's hard to see them with all the code interspersed between them. But this was stopping and thinking and not writing any code, just sort of capturing my ideas about the sequence of events that had to happen in that update method. So I did that. And now we should update all the game entities. So I'll scroll up to the update method. As you can see, there's lots of code in here. But here's the update the game entities. And so I'll uncomment all of this. And really, I wanted to update the chickens because once I drew chickens, I wanted to click on them, and I clicked on them, and nothing happened. And so I was upset. And so I went and implemented this, and because I was updating the chickens, I knew everything would need to be updated. So I just added updating all of them now. I made a comment here, by the way, that I changed the rubber chicken speed for finer granularity. So let's go to the rubber chicken. So in this field that is rubber chicken speed, I made it a float and I made it 0.8 F. The F is required because it's a float. Otherwise, the compiler will think 0.8 is a double. So I've made that a float, and I realized when I was doing that I regularly make the speed a float because we usually want to have finer control over the speed of our game entities than integers provide to us. So now if I F5 it, I can click on a rubber chicken and he flies up, and I can, click on all the, well, not all, I'll get bored, but I can click on rubber chickens to launch them. And so now we've noticed that we've noticed because I just said we're updating all the game entities. And the next thing is, when a chicken flies out of the top of the window, we should do something. We should either remove that chicken from the game, make it inactive, so that, we clean out the dead rubber chickens later and it's reclaimed. And that's a perfectly reasonable thing to do. And in fact, in the optional project, you will be, if you choose to do it, you'll be removing inactive projectiles from the game. Now, for chickens, the way I wanted this to work is I pretty much always wanted the bottom row of chickens to be full. Let's see, that's not exactly correct. For each, think of it as 20 columns. Here, why don't I run it and then we can look at it. So I wanted there always to be a chicken in this 0th column. So either he's sitting down here or he's flying his way up. But once he's gotten to the top and outside the window, I wanted a new chicken to be put here. so that you always had, each column had a chicken in it. So the problem, or one of the alternatives, was to destroy the chicken and spawn a new one. However, what I decided to do instead was this. Let's go to the check for chicken leaving window right here. Instead of destroying it, I decided to move that chicken back down to the bottom of the column. And so you'll notice I added a reset method to rubber chicken, so we can go to the definition of that reset method here. And so it puts the chicken back at the bottom of the window. It sets its velocity back to 0, and it makes moving false. And just so you know, I originally had this as a set Y rather than a reset. So I just moved the chicken back to the bottom of the window, and because the velocity was still positive and because it was still moving, it just kept scrolling up. So it would, pop down to the bottom and go up and pop down to the bottom and go up. And while that was very hypnotic, I didn't like it because it wasn't how the game was supposed to work. So I had to change this to reset. So notice, right, that it's okay. We develop, we design and implement our classes. And then when we start using them, we may well discover that there were things that we didn't know we needed, and we discover we need them as we start using the code. It's a perfectly natural part of developing games. And so I felt perfectly free to add methods as I needed them throughout the code. Okay, so why did I move the chicken down to the bottom again instead of just destroying it and creating a new one? Because this is better for memory. There's no need to throw away the chicken so the garbage collector has to go pick it up just so I can create a new chicken in the same column. I can just move this chicken right back down. And so that saves us a little bit on memory. So we've done the replacing chickens part. And at that point, I could shoot chickens, I could launch chickens up toward the top of the window, and then when they exited the window, they came back to the bottom. So let me run that to show you. So I can send a chicken, and when he's out, I get a new chicken, really the same chicken, back in that column. This has turned out to be another long lecture, so I'm breaking this one into 2 parts as well. This is the end of part 1. Remember, I broke this lecture into 2 parts, so this is the start of part 2 for the lecture I started last time. Okay, but at this point, I didn't really have anything to launch my chickens at, and these are ranged weapons. I mean, you gotta shoot them at something, and of course teddy bears are the something that we should shoot them at. So the next thing I wanted to do was to actually start spawning teddy bears. To do that, here in the update method, I implemented the timer stuff that we have seen numerous times already. Now, a couple of comments about what I was thinking about and doing as I went through this code. First of all, I added a new constructor to the teddy bear class. I didn't have one that I could pass in the sprite, the texture 2D, and a velocity. I had one that I could pass in a content manager and a sprite name and a velocity, but that isn't what I wanted to do. So I added a new constructor. When I did that, I felt horribly guilty, because if you go look at that code, there are 4 constructors that have lots of duplicated code in them. And as we learned over the previous lessons in this module, there's a better way. And in fact, it was in the die class that we discovered that there's a better way to consolidate that code even when we're dealing with constructors. We should have the constructors call each other using this. I didn't do that. I feel horribly guilty. You should, feel bad as well as you read that code. Those constructors should be cleaned up, absolutely. I just didn't do it. The other thing that I did was I turned off teddy bear bouncing. I didn't want the teddy bears to be bouncing around in the screen anymore. I just wanted them to be spawned. Okay, so because when I did the draw method, I drew all the game entities, and when I did the update method, I update all the game entities. Now if I F5, I actually get teddy bears spawned. And I'm very excited, and I shoot rubber chickens at them, and of course nothing happens because I haven't coded that yet, and I'm sad again because here are these teddies just begging to be hit with rubber chickens, and I can't do it. Very sad. But we have completed the spawning teddy bears step. We also need to, because teddy bears don't bounce anymore, we need to deactivate the teddy bears when they exit the window. So check for teddy bear leaving window. I'll uncomment. So now, if the collision rectangle for the top of the teddy bear is greater than window height, that means the teddy bear is below the window. And so I just deactivate it and we'll clean out dead teddies later. So unlike the chicken, where we wanted to just keep that chicken object around to save memory, this teddy bear, there's no reason to save it around. We'll just deactivate it and clean it up. So we've done the next step where I deactivated teddy bears outside the window. And cleaning out dead teddies is exactly the way we cleaned out dead teddies before. So you can, in fact, the way you can know that a teddy bear has actually been cleaned out is we will let one. This will be testing both the deactivate the teddy and removing inactive teddies. So there we have removed that teddy bear. I have to believe right. So the teddy bears are actually dying because of their timer. So that doesn't actually test going out the bottom of the window. So we should go change how long a teddy bear lives so that it can get all the way to the bottom of the window. So let's make teddy bears live, 15 seconds. It's very unlikely that they'll actually survive that long, especially once I can shoot rubber chickens. And you can actually add breakpoints while the game is running if you're quick enough about it. And so I've added it so that this teddy bear here, once he's left the window, he gets removed. So we've tested that. We've made sure that both the teddy bear going outside of the window deactivates it and that dead teddies are cleaned out. So let's change that teddy bear life back to 5. Again, we regularly change our code as we're testing just to temporarily test out certain things. So we've cleaned out the dead teddies. And you'll notice I've been doing this in small steps, but those small steps are sort of in larger chunks, if you will. So the first chunk was getting rubber chickens working. And the second chunk was getting teddy bears working. And now the third chunk, this is not a game development term, by the way. This is just the way I'm thinking of it. So the third thing is the interactions between teddy bears and chickens. So this is the collision stuff. So we'll go back to game 1. We'll go back into the update method. And this is absolutely the biggest piece of code, as you can see here. So this is, first of all, let me uncomment it. So these are nested loops. I made a comment about nested loops, though you hadn't seen any yet. And I talked about, processing a two-dimensional game board like tic-tac-toe or something. And by the way, the code that was in the tic-tac-toe programming assignment, now you should absolutely be able to understand those nested for loops that I gave to you because we hadn't talked about those yet. These are, in fact, nested loops anyway, although the inner one is a for each loop and the outer one is a for loop. I actually had them both as for each loops, and then we'll see that I create a new chicken. And when I added the chicken to my chickens collection right here, my code blew up just as I warned you it would, because I was changing the collection inside a for each loop. So I changed this to a for loop because I might add a chicken. So these are nested loops. For every chicken, we're going to take the first chicken and compare it to every bear. And then we're going to take the second chicken and compare it to every bear. And then we're going to take the third chicken and compare it to every bear. You can see why this collision detection thing can get pretty computationally intense if you have a lot of game objects. Okay, this is standard stuff. Both things are active and the collision rectangles intersect. So we detected a collision and I want to apply damage to the bear and I want to explode the bear as appropriate. So I added a health food. I added a health food. I added a health field to the bear. Bear starts at 100 health. And I also added a take damage method to the bear, which reduces the bear's health by the damage amount. And if the health is less than or equal to 0, I clamp the health to 0 because we don't want negative health, even for dead teddy bears. And I deactivated the bear, so he'll get cleaned out of that teddy bears list in the game 1 update method. Let me go back here, and so what I want though is I want the teddy bear to take multiple hits to die. So I make him take damage and then I check to see if he's inactive. And if he's inactive, then I'm going to start playing an explosion. This time it's going to be great. Both the teddy bears and the projectiles will blow up. Rubber chickens will blow up when we have that collision. Okay, so let me comment this out and show you this cool bug that I ran into when I tried testing with the above in place. So I put this stuff in place, but I hadn't implemented this yet because, you know, you write a little code and then you test it. And so it took me a few minutes to figure out what was going on here, because even though the chickens only inflict 50 damage and the teddy bears have 100 health, I was killing these with 1 shot. And that is absolutely incorrect. Here's the issue. Because I hadn't implemented this code yet, I wasn't making the chicken inactive. So on one update, the chicken hits the teddy bear takes damage, so now he's down to 50 health. He's still active though. And I loop around to the next update, a 60th of a second later, and because the chicken is still active, this evaluates to true. So I hit the bear, same chicken damages the bear again because, oh, this is horrible. The rubber chicken is passing through the teddy bear every update. And so that's why I was getting 1-shot kills of bears, even though I had attempted to implement 2 hits for death. 2 hits for death. How's that for a slogan? So once I put this back in, so now I've made it so the chicken will become inactive on this collision. Chickens always die on a collision. There's no 2-hit chicken death. So we explode it. And we're going to add a new chicken down at the bottom of the column. So I thought about moving this particular chicken down to the bottom again, but it made less sense to me. When a chicken leaves the window, it makes sense to me to drag it back. Once you explode a chicken, it really doesn't make sense to me to move that exploded chicken around. You certainly could do it exactly the way we did it when a chicken left the window, but I added a new one in this case. And I made sure here that the new one that I was adding was in the same column, same X location. Here's another one of those calls to get chicken start Y. This is where I added it. When I got here, I said, holy smokes, I need to write a method for that. And chicken damage like that. And so now we will see that teddy bears take 2 hits to die. 1, 2. Oh my gosh. We still aren't quite done, as you can see, because the chicken, we get explosions, but then the chicken keeps flying up. We'll figure out what's going on there momentarily. But if we go back to the PowerPoint, we can see that this collision stuff had a lot of special processing. We had nested loops, which we hadn't seen before, though we'd talked about. We had multiple hits to kill a teddy bear, which was buggy at first until we completely implemented that. We have both teddies and chickens exploding, so you get the gratuitous extra explosions. There was that cool bug, and that may seem weird talking about a cool bug, but they're mysteries, right? You go solve these mysteries, and that's part of the fun of programming. And then there was some special chicken processing. The part where I made the chicken inactive, but also added a new chicken to make sure I always had a chicken in one of those columns. Just a couple more things. So the chicken kept moving forward even after we started the explosion at the middle of the chicken, because we aren't cleaning out dead chickens. So I have come to this part in the code where we do clean out dead chickens. This is just like cleaning out dead teddy bears. And so now we will see that when I shoot a teddy bear with a chicken, the chicken does not keep going up. I'm sorry, I just got a little distracted there because I was shooting rubber chickens at teddy bears. So we've now cleaned out the dead rubber chickens, and there's just one more thing for us to do. For efficiency, you can't even see this, but for efficiency, we have those explosions that we cleaned out before when we had explosions, and we should do that again. Once an explosion has played, it becomes inactive, and so we should get it out of the list. I did make a change that I forgot to mention moments ago. When I create an explosion, if I can find it, when I create an explosion, I change the explosion class. Early on when we were using explosions, remember we had an explosion and we'd create it and then hold it around and then we'd tell it to play at a particular location. This is kind of a different way of thinking about explosions, where you just create the explosion and play it right away, and then when it's done, it's done. And sort of we know enough now for that to be an intuitive and doable thing for us. So once we've cleaned out the dead explosions, we are all done with this game. So what did we do today? We used the rubber chicken class and some of the other classes we had hanging around, and we built a small game up step by step, following the steps I used to build this small game, and talking about the concepts we've learned so far in the course as we did it. So that's the end of Module 11. We're all done with, well, we're all done learning the new ideas behind class design and implementation. And so next time, we'll actually start learning how to add music and sound effects to our X&A games. This is our final lecture in the X&A audio module. So as a final reminder of the Module 12 learning objectives, here you go. Last time, we learned how we could integrate exact audio assets into our X&A games. The problem is that as I record these lectures, Monogame doesn't support using those exact audio assets in Monogame games. So we need a different way to add music and sound effects to our Monogame games. And that's what I'm going to cover today, is how we can actually do that. So we're essentially going to be doing the same game that we did last time using exact audio, though this time we'll do it without using exact audio. I've made significant changes for the audio part of the game and then commented them all out so that I can reveal them to you as we go through this lecture. So let's go right to the code. We'll start at the Game 1 class, and I'll show you that I have some additional or different fields declared at the top. And let's start, we're going to do it in a slightly different order because music is actually more complicated this way than it was when we were doing the exact stuff. So we will do music last. We'll do our button click first. So the big idea behind doing sound effects without using exact is that we're going to use a sound effect object for each of our sound effects. So let's go to the place where we create our menu button. So I've changed over to the menu button class. And we'll see that the menu button field, the menu button class now has a field called button click, and it is the data type sound effect. So I'm going to uncomment that. And I'm also going to come down here to the constructor for the menu button and show you that what happens is we actually need to load content, and it's a sound effect this time. It's not a texture 2D, it's a different data type. This time it's a sound effect, and we give it the name of the sound effect we're going to use. Now if you look over here in the content area, my sound effects are just wave files that I've added as content. We no longer have an exact project that we add as content. We actually add the raw wave files as content to our project instead. Okay, so now because I have this asset called button click, as you can see over here with its name, I can load that asset just like I've been loading texture 2Ds, but this time it's going to load it as a sound effect, which is a wave file. So now if I go, one more thing I need to change before we actually get a click. If we go over here and we say, when they have pressed the left mouse button on top of this menu button, take the button click sound effect, which I just created the object for in my constructor, and play it. So if I F5 at this point, I get a click when I click on the play button or on the quit button. I'll click on the quit button, and as you can see, we got a click. So the next thing that I'm going to do is I will add the destroy sound effect, because that's the next easier thing to do. So back in our Game 1 class, just like I needed a sound effect for the button click, I need a sound effect for destroy. So I'll uncomment that sound effect. And the next thing I need to do is actually load its content. So I'll come down here to load content. And this particular sound effect was called zombie. That was the name of the WAV file, so that's the name of the asset. And this is unfortunately one of those areas where exact is really useful, because you don't care what the WAV files are named, you just use Q names when you're using the exact audio assets, but we don't get that capability here, so that's just the way it is. And so we'll use the zombie WAV file, and of course you could change the WAV file name to destroy as well if you wanted to. And the last thing we need to do is we need to make it so that the zombie sound effect plays when the fish eats the bear. So recall that was down in update. I'm lying to you. It was down in check and resolve fish bear collisions. And so here's where the fish ate the bear. So we're going to play that sound. And now when I F5, and this time of course I'll pick play, as I drive around eating the teddy bears, you see that it plays that destroy sound. We still don't get a bounce sound. Oh, I can dribble a teddy bear. We still don't get a bounce sound because we haven't played that one yet. So let's actually do that one next, because again we have a little extra complication. Remember, the way we implemented our exact project was we set it up so that the bounce sound randomly picked between one of two sound effects or cues. Between two sounds in the sound bank for a single cue, and it randomly picked between them. Well, we don't get that capability without using exact, so we need to implement it ourselves, but we can. We understand how to randomly pick between a few things. We did this way back when we were randomly picking a character to display when we clicked on characters with the mouse back in the XNA input module. So we know we can do this. It's just a little extra work for us. So this time I've declared a variable called bounce, but this is a two-dimensional array of sound effects. So sound effect there, it's a two-element one-dimensional array of sound effects. And so we're going to basically put a couple of sound effects into this array and then randomly pick between them. And that's why I have this random number generator here as well. Back to load content so that we can load the content for those sound effects. So bounce 0, the 0th element in the array, gets the confetti sound effect loaded into it by the content manager. And the 1th element of the array gets the pirate sound effect loaded into it. So at this point, we now have the bounce array that contains two sound effects. And again, we're at check and resolve fish bear collision. And this time we play the bouncing sound, but notice that I've added this part. So I'm going to randomly pick a number that is either 0 or 1 and use that as the index into the array to play that particular sound effect. And so that way I get that same random sound effect getting played on a bounce behavior that I want. And now we can F5 again, and I'll play, and I'll make sure I'm bouncing. And as you can see, we're getting some random bouncing sound effects each time the teddy bear hits the fish. So that's it for the sound effects that we have designed and implemented, I guess. So we button click on menu buttons. We play the zombie sound when the fish eats the bear, and we have the bouncing sound. The last thing that we need is our background music. And I said I was putting that off till last because it's a little more complicated. It's not hugely complicated, it's just a little more complicated. And here's what adds the complication. The complication is that we have no capability to make sound effects loop. And what we want for our background music is we want it to loop while the player is playing the game. So instead of using a sound effect, I need to use something called a sound effect instance. Let's go to the load content method and see how we handle that. So I'll uncomment these 4 lines of code. The first thing we do is we actually load a sound effect because a sound effect instance starts from a sound effect. So this line of code is just like the other sound effect loading things we've done. The next thing we do, though, is we take that sound effect, which is an object, and we call the create instance method on it. And what that does is it creates and returns a sound effect instance object, which we're putting into the background music field. Once we've done that, we can access the isLooped property of this sound effect instance object and set it to true. So now we've made it loop. And then we play the background music just like we played the background music, or just like we've played sound effects. This time we're playing a sound effect instance, but we just call the play method and the background music starts playing. But because we set this isLooped property, the background music will loop while we're playing the game. So I'll play it one more time. And now we see that we actually do have the sound effect playing, and that's great news. So in this lecture, that's it for the code. We've added the sound effects just like we did in the previous lecture, except we did it without using an exact project. We did it using the sound effect and sound effect instance classes. And that's what you need to do, at least at the time of the recording of this video, for if you're using monogame. And so that's it for this module as well. We learned how to, if you're using exact, how to create an exact project and integrate those audio assets into your game. And if you're using monogame, we learned how you can just use WAV files and sound effect instances to add music and audio to your game. Next time, we're actually going to talk about how we can use keyboard input and provide text output in our XNA games. Module 13 is all about doing text I/O in XNA games. So here are the module learning objectives. And just as a reminder, this is the final module in the course. So we're going to look at text I/O. I/O stands for input and output. And the text input that we're going to do we'll cover today. So in this lecture, we're going to use keyboard input to control our character in the game. And then next time, we'll do text output to display important game information, like score, which is a hugely important piece of game information. That's for next time. This time, we're going to cover the keyboard input part of the equation, if you will. So you should start off with an in-lecture quiz about keyboard input. And now we'll go to the code that I already have opened up, and we'll look at how we can use keyboard input to control a fish in the game. So the end result is this. I drive a fish around. I'm still eating bears. I guess that's a thing for me. In this particular game, I can eat bears with the tail of my fish and all kinds of stuff. So not nearly as sophisticated as that previous game that we saw, but I can still drive around. I'm using the arrow keys to drive around with the keyboard so that you know that I'm not, using a controller or something. So the first thing we do, remember when we got mouse input and processed it, we called the mouse.getState method. When we used the gamepad for input, we used the gamepad.getState method. So it shouldn't surprise you at all that here when we're going to use the keyboard, we call the keyboard.getState method and it returns to us a keyboard state object. So go do another in-lecture quiz, and I'll open up the help. Keyboard state, if we search on that and go look at the keyboard state members, we see that there are a number of methods that we're probably going to find fairly useful. We can get the pressed keys, so we can get an array of all the keys that are currently pressed. We can check if a particular key is down, and we can check if a particular key is up. Those are the three methods that you're most likely to use a lot as you're dealing with this keyboard state object that gets returned from the keyboard getState method. So back to our code, we can see that I'm getting the state here, and in fact right here, to make it so I can just exit from this game by pressing the escape key, I've used keyboard, which I just got up here. I'm calling the isKeyDown method, which returns true or false, and I'm passing in a value from the enumeration keys. So keys enumerates basically every conceivable key on the keyboard. That's probably not precisely accurate given our international student body here, but lots of keys in the keys enumeration. And so you did something similar already in the project increment, right, where you call keyboard.getState.isKeyDown keys.enter to move from the opening screen onto the actual gameplay. Now you get to see how that actually works if you hadn't figured that out already. So that gets us the keyboard state. How do we actually use it to move our fish around? If we come down here to the update method and go to definition by right-clicking and go to definition, we see that here's what we do. We check if the key is down and it's the right key. Now, I don't mean the correct key, I mean the right arrow key. Then we change the X property here, we'll look at that in a moment, by the fish move amount. So driving with the keyboard is like moving this around with the gamepad. It's not following the mouse, it's applying fish thrust, if you will, to move the fish around. And there is a little bit of extra processing here where the fish art asset is actually the fish facing both ways. That's a tongue twister. The fish facing both ways. And so I pick which way it should be pointing, to the right or to the left, based on its direction. So let's go take a look at the X property and the fish move amount. We'll do it in exactly the opposite order from what I just said. So the fish move amount just gives us the speed of the fish, basically how many pixels it would move. So this is not physics-based movement in any way. This is 5 pixels per update if, in fact, the appropriate key is pressed. The other thing that we should look at is the X property, because this is the X location of the center of the fish. And here's the interesting part for us, right? We're changing the draw rectangle, and that's fine, because we're changing the draw rectangle X based on the idea that the X property is centered. But we also are making sure that we're keeping the fish clamped within the window, so we can't drive the fish outside the window, even though we're using the keyboard. So back to the update method, we can see that we have 4 different if statements, one for right, one for left, one for up, and one for down. And only left and right change the source rectangles because I only have 2 images. We don't make the fish face up or down. So you might be wondering, because I know I would be, what happens if you press both left and right at the same time? Well, it turns around. You should actually walk through the code and see why if I'm holding both left and right down, it's turning around. And the other thing that you can do is you can, of course, move diagonally. Now, I don't know if you can actually tell from this, but if I'm moving left and right, I'm moving at 5 pixels per update, And if I'm moving diagonally, I'm moving at 5 times square root of 2 pixels per update, because of the way this is set up, that I can move by fish amount horizontally and move by fish amount vertically in a single update. This is actually a very famous bug in Doom. So it's called the Doom Strafe 40 bug, and it essentially happens for exactly this reason. Because okay, maybe not exactly, but same idea, that moving diagonally you can move faster than if you're moving horizontally or vertically. So it's not rocket science, but it's not worth spending the time it would take in this lecture to fix this particular bug. But you should know that there is in fact a bug here, a very famous bug, that you could fix if you worked at it a little bit. Just as a hint, if you decide to do that, figuring out what the move amount should be based on the keys that are currently pressed. So for example, if they're going to move diagonally, if you change the move amount to be 5 divided by square root of 2, and then move it that amount horizontally and that amount vertically, you'll have solved this bug. The speed of movement will always be the same no matter in which of the 8 possible directions they're moving. Okay, the only other, so really that's it for keyboard input, but let's actually add the capability, because you know some gamers like to use these keys that have W's and A's and S's and D's on them. So we can add WASD support as well fairly quickly. Of course, W is not to the right, so that would be a really wacky way to do it. So let's add WASD support right, left. Now I finally get to use W. And down. And so if I F5 again, you can't tell, but I'm actually driving with W, S, A, and D. And of course, both if I want to go super fast on the diagonal. So you should now go do an in-lecture quiz about getting the state and how that works. And you should do another in-lecture quiz about how we process the keys that we have extracted from the keyboard state, or more precisely, how do we process the keyboard state in useful ways? And really, that's all there is to doing keyboard input. You can see significant parallels between using a mouse for input and a gamepad for input and a keyboard for input. We get the state of the input device, and then we examine the state of the input device and process that state in appropriate ways. That's it for keyboard input. Next time, we will see how to use text output in our XNA games so we can display important textual information. Last time, we started working on Module 13, doing text I/O and XNA. So here's a reminder of the learning objectives for the module. We did keyboard input last time so that we could use the keyboard to control the player. Of course, we can use keyboard input for lots of other things as well, letting the player enter their gamer tag into a text box and so on, but we kept it pretty simple for what we're doing in this course. In this lecture, we're going to talk about how we can provide text output in our XNA games. Obviously, when we had a console application, we could just use console.writeline to output stuff, but in our XNA games, we can't use that approach. We have to do something slightly more complicated, and so that's what we're going to cover today. The first thing we need to know is to actually display text in our XNA game, we need a special kind of content that we haven't used yet. So I'm going to go over to the content project in my solution that I obviously just blasted over to and opened up. And I'm going to add a new item. And when I say I want to add a new item, I get a number of different choices. I can add an XML file, which can be really useful for saving level design information into XML files, but we're not going to do that in this course. I could save an effect file, but I'm going to create a new sprite font. So a sprite font, and let me just call this Arial. A sprite font is a font that will get used within our game. In fact, what we do is we specify a particular font name here, and this font needs to be installed on your computer so that when it's time to build, it can turn this sprite font into an XNB file, which is compiled XNA content. If you're a monogame user, you're not going to be doing any of this. You can't add a sprite font. You can't build a sprite font. There's no content pipeline in monogame at this time. So for this particular lecture, I will be providing you with a compiled XNB file for this sprite font we're building, but you should understand you can't do it, right? You have to build a content pipeline some other way at this point within monogame. But if you're using Visual Studio and XNA, then you do what I'm showing you here, and you pick the font name, and you can pick a size, and you can do, there's lots of stuff you can do. You can make them bold or italic, all kinds of things that you can do to specify what this font will look like when you display it in your XNA game. All I wanted to do is change it to Arial, so I will Control S, and I'm going to actually build right now, because this would be the point at which if you said, you know, you had a misspelling and you said Arialiosity or something like that, then it would blow up because it can't build the font because it doesn't have it installed on your computer. Okay, so now I have this piece of content that I've built, but I still need to, you know, have a variable that holds it and load it and so on. So I'm going to, just as before, I have some commented out stuff that I'm going to uncomment to sort of reveal our solution as we go. So the first thing that we will do is uncomment this sprite font field, and I will also send you to an in-lecture quiz about, wow, I don't want to give away the answer, so about content for fonts. So go take that in-lecture quiz. Okay, so I've got this sprite font object. That was the right answer, sprite font. I've got the sprite font variable or field that I've declared. And I want to come down here and I want to make sure I load it so that I have that content loaded just like we've loaded texture 2Ds, just like we've loaded sound effects. This time, of course, we're loading something different. We're loading a sprite font. At this point, though, I'm not drawing anything. And so we should now add the rest of the code we need to draw stuff. So I'll start by showing you a suboptimal way to draw, and then we'll fix it. So this is not the suboptimal part. This is a good idea. So we're going to have some position at which we're going to draw the score. And at this point, that position will be window width over 12 and window height over 12. And I shouldn't have said at this point. Throughout this entire game, that's where it's going to get drawn. So instead of using a draw rectangle for the text we're going to draw, we're going to tell it where to draw it. And XNA will take it from there when we go to draw it. So let's actually go to draw it. This will be less exciting because I can't actually score at this point, but at least I can draw a string. So I'm going to, instead of just uncommenting that, because this is the commented code is the better way to do it, let's say I decide to do this. So basically, every time I'm here, notice I'm doing this slightly differently. Instead of doing a sprite batch draw, which was for texture 2Ds, I'm doing a sprite batch draw string, which is for, not surprisingly, drawing strings. And I can provide it. There are a bunch of overloads. I see I'm going to have to open up my declaration of the score variable, so I'll fix that in a moment. I have some overloads, but they're all going to require me to pass in the sprite font because it can't draw it if it doesn't know what font to use. And then I pass it the string, then I pass it where I want it drawn, and then I pass it the color in this particular overload of draw string. Just as sprite batch draw has a lot of overloads, sprite batch draw string has a lot of overloads as well. All right, I want to get rid of this compilation error here. So I will go up to the top and start adding a little bit of score support. We're not all the way there yet. So if I F6, I get a build succeeded. If I F5, you can see up here in the upper left-hand corner, it's hard for because the mouse is invisible, nor should it be because I'm not using the mouse in this game, but you can see that it is now displaying the score for me in that upper left-hand corner. The reason I said this was suboptimal is because I am creating, remember, because strings are immutable, down here in the draw method, I am creating a new string 60 times a second and using it for a 60th of a second and throwing it away and then creating a new one. And that's really not the kind of inefficiency that we should add to our code. So let's optimize that part and then we'll actually add some real scoring. So instead of doing it that way, I want a field called score string, way back up at the top. I want a field called score string that will hold the current score string. And that string will only change when the player scores points. And that way we're not creating new strings 60 times a second. We're only creating new strings each time the player scores. When I did that, I discovered that here in load content, I needed to initialize it. And of course, now I get a compilation error because it says, I don't know what this get score string thing is, because I need to come uncomment this private method that I wrote that gets the score string. So you pass in a score, and it returns a string that includes the prefix concatenated with the actual score. Let me Control Z a little bit there. There we go. Concatenated with the actual score. I wrote this method because we'll see in a couple of moments that I need to do this multiple times in my code. And as soon as you start thinking copy and paste, stop yourself and think private method instead. All right, so now when I F5, you're not going to see any difference in program behavior. It still looks exactly the same way it did before. This is an example of refactoring to fix the quality of the code without actually changing its performance. We might have seen some performance hits later on if we had lots of objects and suddenly creating 60 new strings a second caused problems for us. So we just fixed it now and did it in a much more appropriate way. This idea, by the way, is very similar to when I said you shouldn't be creating a new draw rectangle on every call to draw. For the same exact reason. We don't want to create a whole bunch of extra objects that we use very, very briefly and then let the garbage collector go get them. All right, so the only other thing I actually need in this game is to be able to score. And so I'll uncomment these two lines of code. So this is where the bear collides with the fish. So I'm going to add some score to my current score. And this is the point at which I now need to go get a new string. And so I call that getScoreString method that I showed you moments ago. I need to uncomment my bear score constant that I had commented out up to this point. Now I can F6. Now I can F5. And we'll see that if I run into bears, I actually get score. So now, you can play the game and build up your score and try to get on the leaderboards for this amazing, almost commercial quality, but not quite game. So what we didn't do was the other in-lecture quiz, where you go tell me how you actually draw a string. So you should go do that now. And that's it for today. So as a recap, we learned how we use sprite fonts as content so that we can do XNA text output. And we learned how to actually do that text output by calling the drawString method on the sprite batch. That's the end of this module, and that's the end of all the formal modules in the course. There is one more week, and that week is for you to do the optional project if you choose to do so, for you to study for, if you decide you want to, the final exam, and for you to take the final exam. So even though there's no sort of official formal lectures with new material, nor are there assignments due, you do next week need to do your peer evaluation of Project Increment 5 for everyone. And I'll post some lectures talking about the optional project, talking about sort of the core ideas that you should carry with you into the final exam, and closing out the course with some final thoughts. So this lecture is really an opportunity for us to walk through the big ideas that you should have learned over the course of this Coursera course to make sure you've got the big concepts before you take the final exam. So these are not in-lecture quizzes because these are serious. They're not intended to just be funny. Well, as I've said before, like I think is funny. So really, these are questions for you to reflect on how well you think you understand a set of topics that I'm going to provide to you over the course of this PowerPoint show. So for all of these questions, you should think about, on a scale of none to excellent, how well you understand that particular topic. For example, for this first one, do you understand the difference between what variables and fields are for and what methods are for? So this comes back to the core idea behind object-oriented programming, where we store data, state information, in fields, and then we provide behavior from classes by implementing methods for those classes. So that's sort of the core idea here, the difference between the data and the behavior. And remember, encapsulation puts both the data and the behavior into a single thing, a capsule, the class, that you can then use. Understanding that we need to declare and initialize variables before we use them. We've been doing this all along, right? We declare variables to reserve that space in memory, and we provide a data type so that the compiler knows how much space to set aside and what operations will be valid on those particular variables. And we need to initialize them, certainly give them a value before we use them, whether that means assign 0 to a score that the player is going to have, or create a new object for a texture 2D field, for example. But we need to somehow initialize the value of that variable before we actually try to use it. So here's a core idea behind the type system in C#. We have value types that we talked about very early on, way back in Module 3. And those are the predefined types in general, don't include string, but the predefined types in general that for the space in memory that's reserved for that variable, it holds the value of that variable, as opposed to reference types that hold a reference to an object somewhere else in memory, such that the value of a reference type variable is not the actual object, it's a reference to the object. And if you want to think of that as the memory address of the object, that's fine, because that's close enough for this particular course. Another core idea behind the object-oriented paradigm is the difference between the class and the object. So as we know, because we've been using classes and objects since Module 4, as we know, the class is the template that expresses what data will be stored in a particular object that is instantiated for that class, and the behaviors, or the methods, that an object of that class exposes. So the class is the template or the cookie cutter, and the objects are the things we produce, the cookies. So how to implement and call methods is, again, our very first C# program, you were calling the console write line method. So calling methods, we understand that if it's an instance method, which is sort of what we use most commonly, we have the name of an object, variable, a reference type variable, dot, and the method name. And then between parentheses, we provide whatever arguments are required. For those less common but still used a lot methods, static methods, we put the we put the class name followed by the dot, followed by the method name, followed by, between parentheses, whatever arguments we need to provide. So that's calling the different kinds of methods. And we also know that methods can return either void or something like a card when we were taking the top card from a deck. And so in most cases, we're going to want to store that information that gets returned somehow, even if we directly pass it as an argument to a new method. So for example, in the blackjack game, where you would call the add card method on the blackjack hand object, and one of your arguments could be deck.take top card, that means we weren't throwing away the card that got returned from that method. We were just passing it along. And so when we call methods that return something other than void, we have a decision to make about whether or not to store or use that information that gets returned. And usually the answer is yes. Implementing methods is something that we did in Module 11 when we implemented the roll method for the die class and when we implemented the draw and update methods for our rubber chicken class. So how do we use these predefined types that are available to us in C#? Well, we've been doing this for a long time, right? So these are the value types. I guess that's a little strong, right? So let's say the predefined types in C# and the XNA framework, because you should also understand how to use a texture 2D, for example, or a rectangle or a vector 2. So those are predefined in terms of the framework in which we've been working, even if they're not predefined by the C# programming language. So you should understand how you declare variables of these types. If they happen to have operations like rectangles do, methods, you should be able to use those methods as well. We spent a little bit of time talking about string processing and how we could use index of and substring, and we didn't actually use last index of, but that's commonly used as well. And you should make sure you remember how you can use those string processing operations to do interesting things, like extract the values from a comma-separated value string, for example. We talked about selection, how our programs can make decisions, and how those decisions are either based on Boolean expressions for if statements, or the value of a particular variable or an expression for switch statements. And you should understand both that those statements are for making decisions and how you can actually use those statements to make decisions. So remember, we have the sequence control structure where we just do one thing after another. We have the selection control structure where we can make decisions. And we have the iteration control structure where we loop or iterate over the loop body a certain number of times for and for each loops, or while some condition is true for while loops. You should know how to do console input and output. Console output was console write line. Console input was console read line. And remember, sometimes we will read in information from the user that we need to convert to a different data type. And that's when we use things like int.parse or float.parse and so on. We talked about arrays as a good way to store a set of elements that are all of the same data type. And so you should understand how we declare arrays, how we use arrays, how we can use the index to access a particular element of an array, and how we commonly use for loops and for each loops to process in some way each element of an array. Similarly, you should understand how collection classes work, and really just the list class. I won't throw one of the other collection classes at you on the final exam or anything. Just the list class is fine. But understand the key difference between arrays and lists are that lists can dynamically grow and shrink, while arrays can't. And other than that, they have very similar capabilities. We tend to use collection classes most in our C# programs, but because almost every modern programming language has arrays, we covered both of them. And even though I interspersed it throughout the course, we covered XNA as well. So you should understand the kinds of things we do in the XNA load content method, and how the update and draw methods relate to each other in the context of the game loop. So we update and then draw and update and then draw and so on, and that you should only do appropriate things in the appropriate methods. You should never draw anything in the update method. You should never try to get the mouse state while you're in the draw method, those kinds of things. We also added some functionality into the constructor, usually setting the window resolution for our game, and occasionally making the mouse visible as well. We also, early on, we just used draw rectangles to draw stuff, and then later we started using source rectangles as well, so that we could use sprite strips to do things like highlight or unhighlight a button, or play an explosion animation by moving the source rectangle across the sprite strip as appropriate. You should understand how to use both draw and source rectangles when you draw things in XNA. We also, at the very end of the course, we learned how we can also draw strings. So you should understand how we use a sprite font to actually draw a string, and the fact that we call the drawString method rather than the draw method on a sprite batch object to do it. And then we actually let the player interact with the game. So we learned how we could get mouse input by capturing the current state of the mouse, calling the mouse getState method, and then what we could do with the mouse, how we could process the buttons on the mouse or use the X and Y to drag things around on the screen and so on, and even do things like highlight the quit button when we were using the quit button because we could use the location of the mouse to determine when it was over that button, for example. Same thing with the required project, where you would highlight the number tiles when the mouse was over them. That was based on knowing where the mouse was relative to the draw rectangle for a particular number tile. So you should understand how we can do that input with a mouse. Similarly, you should understand how we did the gamepad input. It's okay if you don't have a 360 controller. I won't be asking any questions that would require you to have done sort of deep work with a 360 controller, but there are some general ideas about using a gamepad, particularly versus a mouse, that would apply. For example, our gamepad is not a pointing device like the mouse, so we don't get an X and a Y for anything related to the gamepad. So you should think about how we moved things around with the gamepad versus moving things around by making them follow the mouse. And of course, there's lots of interesting things to do with gamepads as well. But like I said, as long as you get the general ideas, you'll be in fine shape. And last but not least, we recently covered how you use the keyboard, how you can get input from the keyboard by getting the current state of the keyboard, and some of the useful methods like isKeyDown that we can use to actually process that keyboard input. Now, this is an 8-week course, and we just blasted through all the big ideas in a fairly short period of time here. But those are the core things that you should take out of the course. And you'll have access to the archive materials and everything for a long time to come. I'll talk about that in a different lecture. But you should understand those things that have been included. And if you do, If you've managed to say, D or E for most of your answers to these self-evaluation questions, then you probably will have no significant trouble with the final exam. This is the course wrap-up lecture, where I make a few final comments and then send you on your way. First, I want to thank you for participating in this course. Being given the opportunity to open up the world of game programming to tens of thousands or hundreds of thousands of students is just an amazing thing to me. This is one of the most rewarding professional experiences I've ever had, and you helped make that possible. So thanks for coming along for what was sometimes perhaps a bumpy ride, but hopefully an enjoyable and rewarding ride for you as well. Second, as usual, people on the forums are in general really great at helping each other. This is obviously one of those environments where I can't help every student who needs it, and so helping each other was a fantastic thing. Okay, well, now that the course is over, what do you do next? Well, there are a few things you can do next. First of all, if there were things that are still not clear to you from the course material, you can always go back and review those and try them again and work on figuring out what you might not have understood to solidify your understanding. Also, you can move on and do intermediate and advanced programming courses. So it may not have felt like this to all of you, especially if you've never programmed before, but this really was a beginning course. This is based on our first programming course at UCCS, so it's certainly a beginning college course, not a beginning lower level course, but it is for beginners. And so if you've got this foundation down, now you can move forward and do intermediate and advanced things as well. Finally, now you can go build really cool games that you envision. By necessity, the games in this course were dictated by me. Here's what the game has to be, and go do this. And that was really the only way we could do this to get peer reviews done in some reasonable way. Now that you are no longer fettered by the constraints of me telling you what to build, you can go build any game that you want. And you can use the foundational stuff you've used here to start your game, and then you can learn more advanced programming topics to embellish your game to make it even more interesting and advanced. But now you've got the tools to go build amazing stuff. And lots of us have wanted for a long time to be able to do that. And now you have the chance to do it. So this has been an incredible experience for me, and hopefully it has been a rewarding experience for you. Now it's time for you to go build amazing games. Cheers.